Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly let me know in the chats with the thumbs ups. Welcome back people, welcome back, welcome back. So let me know quickly in the chats if all of you can hear me properly, if I'm perfectly audible, visible to you. I'm doing good, guys. I'm doing good. Thank you so much. Thank you so much. I'm doing good. Please take D and F block after electrochemistry. Okay. Well, I have planned some 3 chapters basically. We shall be completing first of all the electrochemistry, and after that we'll be going into the atomic structure. And after atomic structure, we shall be doing periodic classification. Maybe after that, I'll be doing the D and F block elements for you as well. Okay. I believe I'm perfectly audible, visible to everyone, yeah? So my dear students, as you all must be knowing, today we are going to start one of the most important chapters of your physical chemistry. And the name of the chapter, as you would have already seen, it's electrochemistry, right? I would say every year in your NEET examination, almost some 3 to 4 questions are asked from this particular chapter, okay? And I shall be doing this particular chapter exactly from the basics. From the scratch we shall be starting, and first of all we shall cover all the concepts, then all the problem patterns which can be asked from this particular chapter as well. The way we covered the other chapters, in the similar way we are going to start from the scratch, and slowly we shall be scaling up the things as well. Okay, so are you guys ready for it? No, electrochemistry is not difficult. It's not difficult if you know the basics, right? If your basics is clear, definitely it's going to be very easy for all of you. So before starting the session, let me tell you, I have allocated some 3 sessions for this particular chapter. So in 3 sessions, I will be covering this whole chapter, electrochemistry, and every session will have 3 hours of duration. Okay. So should we start then? Should we start? Are you guys ready for it? Are you guys ready for it? Yes. Perfect. My dear students, before starting this chapter, there are a few basic terminologies which you must know. And those basic terminologies are from the chapter Redox reactions. So I'll try to cover all the terms which are from the chapter Redox reactions, but we use those terms in this particular chapter. So let's try to cover those basics first, and then I'll be starting this particular chapter, electrochemistry, right? Because redox, electro, they are interlinked. Let's get to know all the terminologies of redox which are frequently used in this particular chapter, right? And the first terminology with which we are going to start, that is something which you call as oxidation. That is something which you call as oxidation. I'm sure majority of you guys will be already knowing what oxidation is all about. Oxidation, as per modern definition, is defined as loss of electrons. My dear students, any species which is going to lose the electrons, we say that particular species undergoes oxidation. Any species which undergoes loss of electrons, basically, which is going to lose the electrons, we are going to say that particular species is undergoing oxidation. What it means exactly? Before that, I'll tell you one more thing. Whenever in a chemical reaction, you need to check whether a substance is undergoing oxidation or reduction. What you guys are going to do at that time, just remember one simple point. Increase in the oxidation state. Increase in the oxidation state of an element is termed as oxidation. Whenever you see an element is undergoing increase in the oxidation state, you'll directly say that particular element is undergoing oxidation. Now let's get to know what it exactly means. Have a look, people. For example, I have got an element M, for example. This is the element M. I'm assuming this M is losing, let's say, 1 electron, and it is getting converted into M positive, right? So I'm assuming that this M, it has lost one electron, it is getting converted into M positive. Now, my dear students, just try to analyze one simple thing. If I ask you, what is the charge present on this metal here? What is the charge present on this element here? It is 0. What is the charge present on this M here? It is +1. Tell me one thing. From 0 to +1, what it means? Has the oxidation state of M increased or decreased? I would say the oxidation state of M is increasing from 0 to +1. And that particular element whose oxidation state increases during the reaction, we say that particular species is undergoing oxidation. So I would say this M is undergoing oxidation in this particular case, right? As simple as that. So I've taken the element M, it is losing one electron, getting converted into M positive. The initial oxidation of this M, the initial oxidation state of this M, that is 0. Final oxidation state is +1. So 0 to +1 means increase in the oxidation state. And increase in the oxidation state is something which we call as oxidation. And what is oxidation? Loss of electrons. So you can categorically say this M has lost one electron and got converted into M positive, right? Similarly, there's a term called as reduction. I'm sure all of you must be familiar with this particular term as well. So dear students, how do you define the term reduction? If oxidation involves loss of electrons, then I would say reduction is going to involve the gain of electrons. Reduction is going to involve the gain of electrons. Number one. Number two, decrease in the oxidation state of an element. Decrease in the oxidation state of an element is termed as reduction as well. Whenever you see the oxidation state of any element decreasing with time, do remember that particular species will be undergoing reduction. For example, let's say I have got an element A and I'm giving one electron to this element. This A, after gaining one electron, let's assume that it's getting converted into A negative, right? So first of all, is this process involving gain of electrons? Absolutely, this particular process is involving gain of electrons. So this particular process is something which I'll be calling as reduction, right? Now, at the same time, if I ask you, what is the oxidation state of A here? What is the charge on A here? It is 0. What is the charge on this particular A? It is -1. Check it out whether the oxidation state of A is increasing or decreasing. 0 to -1. 0 to -1 means decrease in the oxidation state. And decrease in the oxidation state is something which you call as reduction. So I must say this A is undergoing reduction over here. And reduction, as you already know, that involves gain of electrons. So I must say this A is gaining one electron and getting converted into A negative. I hope this particular basic scenario is clear to everyone, right? So you got to know what oxidation is all about. You got to know what reduction is all about. Now, my dear students, you might have heard about something called as oxidizing agent and reducing agent. Let's get to know what oxidizing agent is, what reducing agent is, and how do we identify them in a chemical reaction. Let's get to know about that. This again, completely basics only, okay? Perfect, guys. There is a term called as oxidizing agent. There is a term called as oxidizing agent. Oxidizing agent is also called as oxidant. It is also called as oxidant. Now, how do you define the term oxidizing agent? My dear students, oxidizing agent is the one, or I'll say that species which oxidizes others. That species which oxidizes others, but itself undergoes reduction. That particular species which is going to oxidize others and itself will undergo reduction, we'll be calling that particular species as oxidizing agent. What it means, you'll get the idea in some time. Before making you understand that, I'll be writing the definition of reducing agent as well. Reducing agent, or you'll be calling it as reductant as well. You'll be calling this as reductant as well. Now, how do you define the reducing agent? And how do you define the reducing agent? Let's get to know about that. Reducing agent, it is that species. It is that species which reduces others. That species which reduces others, but itself undergoes oxidation. So that particular species which is going to reduce others, but itself is undergoing oxidation, I'll be calling that as the reducing agent. Let's try to understand these two definitions over here. Try to understand what exactly I'm going to say. This is something important which I'm going to tell you now. See guys, for example, I've got a reaction and the reaction is like this. Zinc solid plus copper dye positive aqueous. Let's say it gives zinc dye positive aqueous plus copper solid. Let's assume this is the reaction. Okay. Now, if I ask you, what is the charge present on this zinc over here? It is 0. That means its oxidation state is 0. The charge present on copper right here is +2. That means its oxidation state is +2. The charge present on this zinc over here is +2. Its oxidation state +2. The charge present on copper is 0. Its oxidation state is 0. Now, my dear students, I want you to check exactly whether the oxidation state of zinc is increasing or decreasing. What do you think? I would say the initial oxidation state of zinc is 0. The final oxidation state of zinc is +2. So I would say the oxidation state of zinc is increasing with time. And any such species whose oxidation state increases with time, we say that particular species is undergoing oxidation. So you got to know the zinc, since its oxidation state is increasing, so it is undergoing oxidation. If it is undergoing oxidation, definitely it will be losing the electrons, right? It will be losing the electrons. And let me tell you, that particular species, which itself undergoes oxidation, that is something which you call as a reducing agent or reductant. So you identified in this particular reaction, your zinc solid that is behaving like the reducing agent, right? Now at the same time, check it out. Whether the oxidation state of copper is increasing or decreasing. I would say the oxidation state of copper is changing from +2 to 0. What is it? Increase or decrease? It is decrease in the oxidation state. +2 to 0. Decrease in the oxidation state. And decrease in the oxidation state is something which you call as a reduction. So I would say this copper dye positive is undergoing reduction. Yeah. And my dear students, that particular species which undergoes reduction, that will be involving gain of electrons. So I would say this copper dye positive will be gaining certain electrons, right? Now you must be thinking from where those electrons are going to come. Those electrons are going to come from the zinc, which is undergoing oxidation. Zinc is losing electrons and copper dye positive will be definitely gaining electrons, right? And dear students, that particular species which undergoes reduction, that's something which you call as oxidizing agent. I hope this particular thing is clear to everyone. Now you should be able to identify which reactant in a particular reaction behaves like the oxidizing agent and which reactant in a chemical reaction it behaves like the reducing agent. Is this clear to everyone? Quickly in the chats. Let me know quickly in the chats. This was example number 1. Let's have a look on example number 2 as well. See guys. For example, I'm writing a reaction like this. H2 gas plus 2 times Ag positive. Let's say it gives, these are some reactions which I'm writing as such, right? So let's say it gives 2 times Ag positive aqueous and 2 times Ag solid. Let's say this is the reaction which I've taken into consideration. And in this particular reaction, I need to check which particular species is the oxidizing agent and which one is the reducing agent. Let's get to know about that. If I ask you what is the charge on this hydrogen over here, you'll say it's 0. Charge on silver over here, it is +1. Charge on this hydrogen over here, it's +1. Charge on this silver over here, it's 0, right? Now check it out, whether the oxidation state of hydrogen is increasing or decreasing. From 0 to +1, increase in the oxidation state. 0 to +1, increase in the oxidation state. And increase in the oxidation state is something which you call as oxidation. So this H2 is undergoing oxidation here. And the one which undergoes oxidation, that's something which we'll be calling as reducing agent. In the similar way, check the oxidation state of this particular silver. plus 1, plus 1 to 0. Plus 1 to 0 means decrease in the oxidation state. And decrease in the oxidation state is something which you call as reduction. Decrease in the oxidation state is something which you call as reduction. And that particular species which undergoes reduction, that's something which you will be calling as oxidizing agent, right? So let me know quickly in the chats if you got to know how to identify oxidizing and reducing agent. Quickly, my dear students, in the chats. Quickly in the chats. Everyone. Yeah? Quickly. Narmata, watch the redox reaction chapter first, right? And mole concept and equilibrium, right? I think you're here for the first time. Quickly, let me know in the chats. All the things are clear? Perfect. One more example, and with this, we'll start the chapter exactly. I'm writing the reaction, for example, MnO4 negative plus Fe di positive. Let's say it's giving Mn di positive, and with this, you're writing Fa tri positive as well. Now, let me know in the chats which species will be undergoing oxidation and which species will be undergoing reduction. Quickly, people in the chats. Quickly, people in the chats. See, guys, have a look. First of all, if I ask you what is the oxidation state of this manganese over here, you will have to calculate it. It's going to be X. Oxygen shows -2 oxygen state. There are 4 oxygen atoms. Net charge over here is -1. So the value of X will come out to be +7. So I would say this manganese oxidation state is +7 in this case. What is the charge present on this iron over here? It's +2. Charge present on the manganese, it's +2. And charge present on iron right here is +3. Right? Now check exactly whether the oxidation state of manganese is increasing or decreasing. +7 to +2. Decrease in the oxidation state. Decrease in the oxidation state is something which we call as reduction. So I would say this MnO4 negative is undergoing reduction in this particular case. And that particular species which undergoes reduction, that is something which you'll be calling as oxidizing agent. As simple as that. In the similar way, check the oxidation state of iron. It is changing from +2 to +3. +2 to +3 means increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. And that particular species which undergoes oxidation, that's something which I'll be calling as the reducing agent. Quickly, let me know in the chats if all these things are clear. Quickly, my dear students. Do remember one thing, no doubt the oxidation state of manganese is decreasing, but you will never say that manganese is undergoing reduction. You will say this whole compound is undergoing reduction. You will say this whole compound is undergoing reduction, right? Okay? Perfect. Is it clear, people? One last example. One last example let me give you so that I'll get that satisfaction. You got to know how to identify the oxidizing and reducing agent. One last example with this. Let's say I'm writing the reaction like this. Cr2O7 dinegative. Cr2O7 dinegative plus Sn di positive. Let's say it gives chromium tripositive plus Sn plus 4. This is the reaction which I mentioned over here. Now, my dear students, I would want you guys to check which reactant among the two is going to be the oxidizing agent and which one is going to be the reducing agent. How exactly you guys are going to check? First of all, I'll calculate the oxidation state of this particular chromium, right? It has to be 2x minus 14 is equal to -2. So the value of x will come out to be +6, right? What is the oxidation state of this tin over here? It's +2. Oxidation state of chromium, it's +3. Oxidation state of tin, it is +4, right? Now check whether the oxidation state of chromium is increasing or decreasing. +6 to +3. +6 to +3. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as a reduction. So I would say this particular species, this Cr2O7 dinegative, it is undergoing reduction. And that species which undergoes reduction, that is going to behave like the oxidizing agent. Similarly, +2 to +4. +2 to +4. Again, it is increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. And that particular species which undergoes oxidation, That's something which I'll be calling as a reducing agent. Perfect? Yeah? Right, people? Manpreet, this is class 12th. Class 12th. I think this is chapter number 4, I believe. Perfect, people? All right. Now, if all these basic things are clear to everyone, let's try to go into the first topic of the electrochemistry chapter. Are you ready for that? Are you all ready for that? Are you all ready for that? Perfect, guys. So let's get going. Let's get started. The first topic which I'm mentioning on the screen that is electrochemical cell. Electrochemical cell. Now, what this electrochemical cell exactly is all about? What is electrochemical cell? Let me tell you, electrochemical cell, it is the device basically. The device which converts either chemical energy into electrical energy or electrical energy into chemical energy. So electrochemical cell, it is basically a device which is going to convert either chemical energy into electrical or electrical into chemical. How exactly? I'll let you know in some time, right? How exactly this is going to happen? How chemical energy is going to get converted into electrical energy? How electrical energy will be converting into chemical energy? That's something which we shall be discussing in detail in this particular chapter, right? Perfect. Now, this electrochemical cell, it's actually of two types. This electrochemical cell, it's actually of two types. My dear students, one is called as galvanic cell, or you call it as the voltaic cell as well. Galvanic or voltaic cell. Number two, that is something which you call as electrolytic cell. That's what you call as electrolytic cell. So what is a galvanic cell and what is the electrolytic cell? How do we define them? Right now, I'll be just giving you the definition and some basic points which you need to remember first of all, before going into the details of this particular chapter. So basically in this chapter, we have to see exactly how Daniell cell works, right? How Daniell cell works, how electrolytic cell works. These are two vast topics which we have to cover in this particular chapter only. But right now, I'll just give you the definition of these two cells, then we'll go into the details one by one. Yeah? Okay. My dear students, when I talk about the galvanic cell, it is a device. It is a device which converts chemical energy into what? Into electrical energy. It is a device which converts chemical energy into electrical energy. Point number one. How exactly? We shall be discussing that in some time. Number one. Number two. In case of galvanic cells, what happens exactly? Let me tell you, in case of galvanic cells, spontaneous cell reactions take place. Spontaneous cell reactions will take place in case of galvanic cell. How exactly? Again, you'll get to know in some time. Number three. For any process to be spontaneous, you must be knowing for any process to be spontaneous, delta G for the system at constant pressure and temperature, that has to be negative. So I would say if spontaneous cell reactions will be taking place in the galvanic cell, so I would say its delta G for the reaction will be less than 0. And my dear students, in this galvanic cell, I'll be using two electrodes. One I'll be calling as anode, another one I'll be calling as cathode. One I'll be calling as anode, another one I'll be calling as cathode. Dear students, remember one simple thing. The rod of the anode in galvanic cell, it will carry the negative charge, and the rod of the cathode in the galvanic cell, it will be carrying the positive charge. What is the logic behind that? Why the rod of anode will carry negative, rod of cathode will carry positive? There's a logic behind that. Again, that's something we shall be discussing in some time, right? And do remember one simple thing. At anode, always oxidation takes place, which involves loss of electrons. And at cathode, always reduction takes place, which involves gain of electrons. So these are few basic pointers which you need to know, right? Which we shall be discussing one by one in detail in this particular chapter. Related to what? Related to galvanic cell. Okay. Similarly, my dear students, electrolytic cell, this is one more topic which we have to cover in detail. But right now, let me give you certain basic things about this electrolytic cell as well. Let me tell you, this electrolytic cell, it is just the reverse. It converts electrical energy into chemical energy. It converts electrical energy into chemical energy. And in this particular cell, the cell reactions are carried out by supplying external voltage. Again, what that means, keep it as such, we shall be discussing in some time. At the same time, if cell reactions are carried out by supplying external voltage, I shall be saying that cell reactions are non-spontaneous in this particular case. So delta G has to be positive, right? Similarly, in this particular cell, I'll be using two electrodes. One will be calling as anode and one we shall be calling as cathode. But over here, there's only one difference. The rod of the anode here carries a positive charge and rod of the cathode here carries the negative charge. Why it happens? Again, there's a logic we shall be discussing in some time. But one thing that is certain, that at anode, always oxidation is going to take place, and at cathode, always the reduction is going to take place. So these are few points which you should remember first of all. Okay? Right? These are some points which you should remember first of all. Right, people? Now our actual topic in the today's session, that will be exactly how this galvanic cell works, how exactly it converts chemical energy into electrical energy. That will be our first topic actually in the today's discussion. So let me know, first of all, whatever I have discussed till now, is every single thing clear? Is every single thing clear quickly? Yeah? I just gave you the overview of the things. I did not teach anything in detail yet. Now it's the time to see things in detail. But before that, I would want you guys to let me know if every single thing is clear. Quickly, people. Everyone. All right. Now, people, let me tell you one important thing. The cell which we have to discuss, that is something which you call as galvanic cell, right? The typical example of the galvanic cell, the most common example of the galvanic cell, that is Daniell cell. So Daniell cell, what is it? It is the most typical example, it is the most common example of the galvanic cell. What this Daniell cell exactly is going to do? This Daniell cell, since it is the most common example of the galvanic cell, this Daniell cell, it is going to convert chemical energy into what? It is going to convert chemical energy into electrical energy. Now the point is how? How this Daniell cell, which is the most common example of the galvanic cell, how it's going to convert chemical energy into electrical energy, that is the discussion here, right? But again, before that, few points which you must know. See guys, first of all, before going into the details of the Daniell cell, if I ask you how electrodes are made, you should be exactly knowing how electrodes exactly are made. For example, people, let's say I have to make a zinc electrode. How do I make a zinc electrode? How do I make it? Similarly, if I ask you, how do we make the copper electrode? How copper electrodes exactly are made? Let's get to know about this. How electrodes are made first of all. Then only you can understand the concept of the Daniels. So try to understand what exactly I'm going to say. My dear students, since we are planning to make the zinc electrode. So what I'll be doing, I'll be taking a container. Let's assume this is the container. And in this container, I'm going to keep a solution. I'm going to keep a solution containing the salt of zinc. For example, I have kept zinc sulfate in the container. Let's say I've kept zinc sulfate in the container. My dear students, this zinc sulfate, since it's an electrolyte, so it would have got dissociated into its ions, zinc di positive and SO4 di negative, right? So basically in this particular container, you have got zinc di positives as well as SO4 di negatives. So these are the two types of ions which are present in the container. Now at the same time, since I have to make a zinc electrode, so what I'll be doing now? Now my dear students, I'll be placing a zinc rod. I'll be dipping a zinc rod. This is the zinc rod. This is the zinc rod. So what exactly I have done? I have placed zinc rod into a solution which contains its own ions. Own ions means which contains zinc di positive ions, right? Whenever you need to make an electrode of certain metal, what exactly you need to do? You need to take the rod of that particular metal and you have to insert that rod into the solution which contains the ions of the same metal. That's what I've done over here. I've taken zinc rod. I've inserted the zinc rod into a solution which contains the ions of zinc. My dear students, this whole setup over here, I'll be calling as zinc electrode. This whole setup I'll be calling as the zinc electrode, right? In the similar way, let's say you have to make the copper electrode. How exactly you'll be making the copper electrode? Again, you'll be doing the same procedure. You'll be taking a container. Let's assume this is the container. And my dear students, in this particular container, I'm going to keep a solution. I'm going to keep a solution containing an electrolyte, right? And that electrolyte should be the salt of copper. Let's say that electrolyte is copper sulfate. Let's assume that electrolyte is copper sulfate. So my dear students, this copper sulfate, it would have got dissociated completely into its ions. For example, its ions are copper di positive and SO4 di negative. So in this particular solution, we have got copper di positive ions. We have got SO4 di negative ions as well. Now what exactly I should be doing? Since I'm going to make the electrode of copper, so what I'll be doing, I'll be taking a copper rod and I'll be inserting that copper rod into a solution. I'll be inserting this copper rod into a solution containing its own ions. So this whole setup I'll be calling as electrode. Isn't it simple? Isn't it simple, people? Right? So for example, whenever you need to make the electrode of some metal, what exactly you'll be doing? You'll be taking a rod of that particular metal, and that rod of a particular metal that has to be introduced into a solution containing ions of the same metal. The whole setup you shall be calling as the electrode, right? Now if I ask you, can you make electrode of hydrogen? Can you make electrode of hydrogen? Say yes or no. See, I showed you how to make the electrode of zinc. I showed you how to make the electrode of copper. Can you make the electrode of hydrogen? Right? So that means you have to take the hydrogen rod. Now, how come it's possible to take the hydrogen rod? Hydrogen is a gas, right? Perfect. That's something which we have to discuss in detail, how to make the hydrogen electrode. But right here, I'll just give you the idea of how do we make the hydrogen electrode. Just the quick glimpse of how do we make the hydrogen electrode. See guys, what exactly you shall be doing? You'll be taking a rod which is going to be either platinum or graphite. You'll be taking a rod which is going to be platinum or graphite. Let's say I have taken platinum. My dear students, there is property, this platinum, it has got a property associated with it. And what is that property? If by chance you'll keep hydrogen gas molecules, in the vicinity of this platinum rod, let's assume that you're going to keep the hydrogen gas molecules in the vicinity of this platinum rod over here. What exactly is going to happen? These hydrogen molecules, these are going to be adsorbed. These are going to get adsorbed on the surface of this rod. They'll get adsorbed on the surface of the rod, right? Now, if these hydrogen gas molecules are adsorbed on the surface of the rod, what is going to happen? Can I say after some time, the whole surface of platinum, the whole surface of the platinum would have got covered by hydrogen gas? Yes, I would say the whole surface of platinum would have got covered by the hydrogen gas. Now, my dear students, if I ask you whether this rod from outside, is it looking like a platinum rod now? See, imagine this was the platinum rod. Now, H2 gas has been adsorbed on the surface of this platinum, right? This entire surface, the entire outer covering of this rod is covered by hydrogen gas. Now, from outside, is it looking like platinum? No. It looks like hydrogen rod to me, right? It looks like a hydrogen rod to me because I can see the entire surface covered by what? H2 gas. Now, what you'll be doing? You'll be introducing this H2 rod. You'll be introducing this H2 rod into a solution containing the ions of hydrogen. For example, contains H positives. So I've introduced the rod into the solution which contains its own ions. So again, I shall be calling this as the electrode. This is the hydrogen electrode, right? Just the quick idea, right? This is not something which is detailed. In the detailed way, I'll show you how to make the hydrogen electrode after some time. But right now, understand this. So I hope you got to know. I hope you got to know exactly how do we make the electrodes. Yeah. Take the rod of the metal, introduce that into a solution containing the ions of the same metal, right? The complete setup is called as the electrode. Okay. Now, guys, let's get into the details of what? Let's get into the details of the Daniell cell now. Okay, now if I ask you what is the Daniell cell? Daniell cell, it is the common example of the galvanic cell. And what does a galvanic cell do? It converts chemical energy into electrical energy. So this Daniell cell is going to convert chemical energy into electrical energy. Now, how exactly? Let's talk about that. See, guys, in case of Daniell cell, you will be using two electrodes. In case of Daniell cell, you will be using two electrodes. One is going to be your zinc electrode, and one is going to be your copper electrode. In case of your Daniell cell, you'll be using two electrodes. One is going to be your zinc electrode, one is going to be your copper electrode. Now, my dear students, if I compare zinc and copper, let me tell you, zinc is comparatively more electropositive. Zinc is comparatively more electropositive than that of what? Than that of copper. If I compare zinc with copper, let me tell you, zinc is comparatively more electropositive than copper. If zinc is more electropositive, what it's going to do? It's going to lose electrons. Electropositive metal, electropositive element, what it does? It has got the tendency to lose electrons. So I would say the cell which I'm going to make, in which the zinc is going to behave like in which the zinc and copper, these are the two electrodes, right? In that particular cell, this particular zinc electrode, since zinc is more electropositive, so it has got more tendency to lose electrons. So I would say the zinc, it will undergo oxidation. And if zinc undergoes oxidation, I would say this copper will be undergoing reduction. And already you know, oxidation, it takes place at anode, and reduction, it takes place at cathode. So my dear students, since you are going to make the Daniell cell, and in the Daniell cell, you are going to use two electrodes, zinc and copper. And you got to know easily which one is going to behave like the anode and which one is going to behave like the cathode, right? So do remember, in the Daniell cell, your zinc electrode, that will be behaving like the anode, and copper electrode, that is going to behave like the cathode, right? Okay. How exactly you got to know that? Zinc is considered to be more electropositive than copper. So more tendency to lose electrons. Loss of electrons is something which you call as oxidation, and oxidation always takes place at anode, right? This is how you can remember it. Okay. Now it's time to make the Daniell cell and see exactly how it works. Okay. It is time to make the Daniell cell and see exactly how it works. Try to understand everything in detail now, because this is the most important point over here, which I'm going to discuss. See, guys. First of all, I'm going to take how many electrodes here? Two electrodes. One is zinc, one is copper. Let's try to make the zinc electrode first of all. For example, my dear students, this is the container which I have taken. And in this particular container, let's say I have taken zinc sulfate. The zinc sulfate, let's assume it has got completely dissociated into its ions, and its ions are zinc di positive aqueous plus SO4 di negative. Okay. So in the container, I have taken zinc sulfate. This zinc sulfate has got completely dissociated into its ions. So I would say the container which I have taken, in this particular container, you have got equal number of cations and anions, right? In this particular container, you have got equal number of cations and anions, right? If there are equal number of cations and anions present in this container, so I would say the solution is right now electrically neutral, right? Since there are equal number of cations and anions present. So this particular solution, it has to be electrically neutral, and it is electrically neutral. Now people, what I'll be doing? I will be introducing a rod. Which rod I'm going to introduce? I'm going to introduce a zinc rod over here. I'm going to introduce a zinc rod over here. So try to understand. I've introduced zinc rod into a solution containing its own ions. I've introduced zinc rod into a solution containing its own ions. So this whole setup I'll be calling as zinc electrode. So this is your zinc electrode over here, right? Similarly, I would need one more electrode as well. And you already know what that electrode is. That is going to be copper electrode. So again, I have taken one more container. And in this container, what exactly I have done? I have taken copper sulfate, for example. And I'm assuming this copper sulfate has got completely dissociated into its ions. And its ions are copper di positive and SO4 di negative. So I would say this particular solution, right now, again, it contains equal number of cations and anions. So this solution, again, is electrically neutral. It is again electrically neutral. Now, I'm going to introduce a rod. I'm going to introduce a rod. Which rod? I've introduced copper rod into a solution containing its own ions. I've introduced copper rod into a solution containing its own ions. So this setup, again, I'll be calling as what? I'll be calling it as copper electrode, right? So how many electrodes have I taken? How many electrodes have I taken? Quickly. How many electrodes have I taken? I have taken 2 electrodes. One is zinc and one is copper. Correct? Now, dear students, I am going to connect these electrodes with the help of a voltmeter. I've connected them externally with the help of voltmeter, right? These 2 electrodes are connected with the help of voltmeter. And at the same time, internally, I'll be connecting them with the help of inverted U-type tube. This is inverted U-type tube over here. This is inverted U-type tube over here. My dear students, this inverted U-type tube, what does it contain? What does it contain? Let me tell you, this inverted U-type tube, which I have used over here, this inverted U-type tube, it contains an inert electrolyte. The example of the inert electrolyte is, for example, your KCl. For example, it's K2SO4. Let's say it is NH4Cl. These are the examples of the inert electrolytes. And my dear students, this inverted U-type tube, I'm going to fill with inert electrolyte. And that inert electrolyte, it is mixed with, it is mixed with gelatin or agar-agar. This inert electrolyte, it is mixed with gelatin or agar-agar. And let me tell you, when inert electrolyte is mixed with gelatin or agar-agar, it forms a jelly-like paste. It forms a jelly-like paste. And let me tell you, that jelly-like paste is basically introduced in this inverted U-type tube. So this inverted U-type tube, it contains a jelly-like paste, which contains inert electrolyte, which was mixed with gelatin or agar-agar, right? And at the same time, the ends of this inverted U-type tube, it is sealed with cotton balls. So these are the cotton balls which I have used over here, right? Now people, if I ask you, imagine that you have used K2SO4 as the inert electrolyte. If I ask you which types of ions are present in this inverted U-type tube, you will say it's going to be K positive and SO4 di negative. Let's say I've used K2SO4 as the inert electrolyte over here. So this inverted U-type tube, it's going to contain K positive and SO4 di negative. And this inverted U-type tube containing inert electrolyte, this is something which you call a salt bridge. So the first thing which I would want every one of you to remember. What is a salt bridge? What does salt bridge contain? Salt bridge is basically the inverted U-type tube which contains inert electrolyte which is mixed with gelatin or agar-agar. And when we mix inert electrolyte with gelatin or agar-agar, it leads to the formation of the jelly-like paste. And that jelly-like paste is inserted in this inverted U-type tube. and the ends of this inverted U-type tube are sealed with the help of the cotton balls, right? Yeah. What is the function of this salt bridge? You'll get to know in some time. Okay. Tell me one thing. Since I told you already that this zinc electrode in the Daniell cell, it behaves like it is going to behave like the anode. And this copper electrode, it is going to behave like the cathode. Right? This is something which I've mentioned already. I've told you already. Right? Right? And people tell me one thing. At anode, what's going to happen? At anode, oxidation is going to happen. And similarly, at cathode, what's going to happen? At cathode, I must say, a reduction is going to happen. At cathode, reduction is going to take place, right? Okay? Right, people? Someone is saying spelling of jelly is incorrect. Yes, it's incorrect. It's J-E-L-L-Y, right? Is that? Wow. So intelligent people. I'm teaching right now. Yeah? People, is everything clear till here? Yes, so intelligent, right? Literature people. Unpad gawar people. Just kidding. Okay. So I've used two electrodes. One is zinc, one is copper, right? The zinc electrode, it's going to behave like the anode, and copper electrode, it's going to behave like the cathode. Yeah? And my dear students, at anode, we know oxidation takes place, and at cathode, we know reduction takes place. Now, if I ask you whether this particular cell is complete right now or not, what do you think? What do you think? Is this complete? Is the circuit complete or not? Absolutely. The circuit is externally complete as well as it is internally complete. It's a closed loop. It's a closed loop, right? The circuit is complete right now. Okay? And if the circuit is complete, what is going to happen? I told you at anode, oxidation is going to take place. So the first thing, what is going to happen at anode? I told you at anode, oxidation is going to take place. Oxidation means loss of electrons, right? Now, people, tell me one thing. Since you have taken a rod over here, which is a zinc rod, which is absolutely made up of zinc atoms. So this rod is made up of zinc atoms. Now the rod, since it is made up of zinc atoms, those zinc atoms of which rod is made, they'll undergo oxidation. Those zinc atoms of which rod is made, they'll undergo oxidation. Oxidation means loss of electrons. So I would say the zinc atom, for example, zinc solid, it is going to lose some electrons and it's going to get converted into zinc di positive. I would say the zinc atom of which rod is made, it will undergo oxidation, it will get converted into zinc di positive, and with that, you'll be getting 2 electrons. Now the zinc di positive, which we got by the oxidation of zinc atom of the rod, that zinc di positive is going to enter into the solution. The solution initially was electrically neutral. Now I would say an extra zinc di positive is going into the left container, due to which the left container carries the positive charge now. Agreed? What is happening? The zinc rod is made up of zinc atoms. And those zinc atoms of which rod is made, those zinc atoms are undergoing oxidation. And when zinc atom undergoes oxidation, it gets converted into zinc di positive. And with that, it gives 2 electrons. Initially, the solution was electrically neutral. Now, in the solution, an extra zinc di positive is entering, due to which this left container carries a positive charge. Now, these 2 electrons, they are going to get accumulated on the rod. They are going to get accumulated on the rod. Similarly, one more zinc solid, one more zinc atom will undergo oxidation. One more zinc di positive is going to enter into the solution, and 2 more electrons are going to accumulate on the rod. Similarly, I would say the electrons are continuously going to be accumulated on the rod. And if electrons are accumulated on the rod, tell me which charge this rod is going to carry. Since electrons are being accumulated on the rod, I would say the rod is going to carry the negative charge. That's something which I told you already, right? The rod of the zinc electrode, it's going to carry which charge? Negative charge, right? Perfect. Yeah? Right, people? Now, at the same time, this copper electrode, it's going to behave like the cathode. And at cathode, what happens? At cathode, reduction takes place. Reduction means gain of electrons. So at cathode, I must say reduction is going to take place. And you know reduction involves gain of electrons, right? Now try to understand. This particular solution, it contains two types of ions, copper dye positive, SO4 dye negative. And it contains equal number of cations and anions. So this particular solution was electrically neutral in the beginning. Now what's going to happen? My dear students, if I ask you, between copper dye positive and SO4 dye negative, which one is electron deficient? Which one is electron deficient? Is it copper dye positive? Absolutely. So the copper dye positive, which is in the solution, that is going to collide with this particular rod. The copper dye positive, which is in the solution, it's going to collide with the rod. And this copper dye positive, which is going to collide with the rod, it's going to take 2 electrons from the rod. So what's going to happen? The copper dye positive aqueous, which was there in the solution, it is going to take 2 electrons from the rod. And when copper dye positive will take 2 electrons from the rod, it will get converted into copper solid. Right? Now try to understand. Since copper dye positive in the solution is taking electrons from the rod, right? From the rod, electrons are being snatched. So I must say the rod is going to carry the positive charge now. Because electrons are being taken away from what? From this copper dye positive over. Correct? Now we will try to understand one thing. Try to understand one simple thing. At anode, oxidation happened. At cathode, reduction happened. Now, on this rod, electrons are accumulated. On this rod, there is a positive charge. Can I say this particular positive charge is going to attract these electrons towards itself? Since the path is already created. The path is already created. Now, this particular positive charge is going to attract these electrons, right? It's going to pull these electrons towards itself. Perfect. Now, tell me what is happening. Can I say electrons are basically moving from anode to cathode? This positive charged rod, it's attracting the electrons towards itself. Due to which electrons are moving from anode to cathode, from zinc to copper. From zinc to copper. Now, if I ask you one thing, whether it is just the movement of electrons? No, it is not just the movement of electrons. It is movement of electrons in a particular direction. It is movement of charge in a particular direction. And whenever you see the directional movement of electrons, whenever you see the directional movement of charge, whenever you see electrons moving in a particular direction, they say current will be automatically generated here, right? And you must be knowing the direction of current is always opposite to the direction of electrons. So the direction of current is going to be from cathode to anode. This is the first question which can be asked. In case of your galvanic cell, in case of your Daniel cell, what is the direction of the movement of electrons, anode to cathode? What is the direction of current? It's going to be from cathode to anode. Point number 1. Point number 2, my dear students. What is happening at anode? At anode, oxidation is happening. Due to which zinc solid, zinc atoms of which rod was made up of, that's undergoing oxidation, getting converted into zinc dye positive. That zinc dye positive is entering into the solution, right? Similarly, due to the oxidation of one more zinc atom from the rod, one more zinc atom will get oxidized, will get converted into zinc dye positive. That zinc dye positive will enter into the solution. Then one more zinc atom will get oxidized, will get converted into zinc dye positive, will enter into the solution. So what is happening to the thickness of this rod with time? Is the thickness of rod increasing or decreasing? Quickly. If the thickness of this particular rod increasing or decreasing, I would say the thickness of zinc rod, it decreases with time. It decreases with time because the rod is made up of zinc atoms, and those zinc atoms are continuously undergoing oxidation, continuously getting converted into zinc dye positives, and those zinc dye positives are going into the solution, right? So this one more conclusion. The thickness of zinc rod decreases with time. Similarly, if you ask me, what is happening to the thickness of copper rod? What is happening to the thickness of copper rod? See, Cu dye positives which were there in the solution, they collided with the rod. They took 2 electrons from the rod, got converted into copper solid, and that copper solid will get deposited on the rod, my dear students. So, since copper solid is being deposited on the rod, due to which the thickness of the copper rod that increases with time. The thickness of the copper rod, it increases with time, right? Since this particular cell, it is made up of 2 electrodes, anode, cathode, right? At anode, oxidation is taking place. At cathode, reduction is taking place. Now, if I ask you, what is going to be the net reaction? What is the net reaction? What is the net reaction which is happening in the cell? My dear students, whenever you're supposed to write the net reaction taking place in the cell, first you shall be writing reaction taking place at anode. Then you shall be writing reaction taking place at cathode. Right? Reaction at anode, reaction at cathode. Now what you should be doing? You are going to balance these electrons then. Write the reaction at anode first, then write the reaction at cathode. Try to balance these electrons. And in both the reactions, electrons are balanced only. Now you can directly add up. If the electrons were not balanced, you were supposed to balance them. Imagine over here there was 1 electron. Then you were supposed to multiply this reaction by 2 to make the electrons balanced. So first of all, reaction at anode, reaction at cathode, try to balance the electrons. After balancing the electrons, try to what? Try to add these 2 reactions. And when you add these 2 reactions, I'll get something like this. Zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous. And with this, you will be writing copper solid as well. So this is your net reaction which is happening in this Daniell cell over here, right? It is the net reaction which is happening in the Daniell cell. Now, if I ask you, how many electrons got cancelled? You'll say 2 electrons got cancelled. What is meant by that? It means that number of moles of electrons. It means that number of moles of electrons exchanged in the net cell reaction. Exchanged in the net cell reaction, which I'm representing with N. That is equal to 2. So basically, there is a movement of 2 moles of electrons from anode to cathode. Right? Since electrons are moving from anode to cathode. So how many moles of electrons? You got to know 2 moles of electrons are being exchanged from anode to cathode in this particular galvanic cell, in this particular Daniell cell, right? Okay. Is this clear to everyone, people? Is this clear to everyone? Right? So simply just add the reaction. When you add the reactions, the number of electrons which gets cancelled, that gives you the value of N basically. Okay. Now people, you must be thinking, what was the need of this salt bridge? Why did we introduce the salt bridge? There's a logic for that as well. There's a logic for that as well, right? Salt bridge. Why do we use the salt bridge? The first thing, it maintains electrical neutrality. It maintains the electrical neutrality in both the solutions. This is the first point. Now, what that means exactly? What is meant by it maintains electrical neutrality in both the solutions? Try to understand what exactly I'm going to say. My dear students, this particular solution, it was electrically neutral in the beginning. This particular solution, it was also electrically neutral in the beginning, right? Then what happened? When oxidation of zinc happened, what happened? The rod is made up of zinc atoms. Those zinc atoms, they have undergone oxidation. Those zinc atoms got converted into zinc dye positive, right? And those zinc dye positives entered into this solution. The solution was electrically neutral in the beginning. Now, due to the presence of extra zinc dye positive charge got accumulated over here, right? Similarly, my dear students, initially there were equal number of cations and anions in this solution, due to which this particular solution was electrically neutral. Now, one of the Cu dye positive collided with the rod, took 2 electrons from the rod, got converted into Cu solid. And that Cu solid got accumulated on the rod, right? But what happened to the concentration of Cu dye positives? What happened to the number of Cu dye positives in the solution? They decreased. Initially, there were equal number of cations and anions. Now, one of the Cu dye positives is undergoing reduction. It is getting converted into Cu solid. That Cu solid is deposited on the rod. Now, what is happening to the number of Cu dye positives in the solution? Number of Cu dye positives are decreasing. And if the number of Cu dye positives are increasing with time, so what will happen to the charge on the solution? Will the solution get the negative charge? Absolutely, the solution will get negative charge, right? Initially, equal number of cations and anions. Now, one of the cation is lost. It has undergone reduction. So, now one cation is less. So, more anions, less cations. So, net negative charge on the solution, right? So, I would say the left container got the positive charge and right container got the negative charge. Now, this salt bridge, it already contains K positive and SO4 dye negative. Dear students, as soon as this particular solution gets the positive charge, as soon as the solution gets the positive charge, at the same time, the SO4 dye negative is going to come from the salt bridge and it's going to neutralize this charge, right? Similarly, my dear students, Once this particular solution gets the negative charge, at the same time, K positive is going to come from the salt bridge and it's going to neutralize this particular solution. So can I say the ions of the salt bridge, they are going to neutralize, they are going to maintain the neutrality in both the solutions? Yes, they are going to maintain the neutrality in both the solutions. Is this clear? That's what I exactly wrote over here. It maintains the ions of the salt bridge. They are going to maintain the electrical neutrality in both the solutions. Point number one. As soon as the left container gets the positive charge, at the same time SO4 dinegative is going to come from the salt bridge. Similarly, as soon as negative charge is accumulated in the right container, at the same time K positive is going to come. Will make the solutions electrically neutral again, right? Now, there is one more point. The salt bridge, it avoids the liquid junction potential. It avoids the liquid junction potential. Now, what is meant by liquid junction potential and how salt bridge exactly is going to avoid that? Let's try to identify. See guys, see exactly what I am going to do. Just a second. Imagine I'm going to take only one container instead of two containers. Imagine that I'm only taking one container instead of two containers, right? I've just taken one container. And my dear students, this particular container which I've taken, I'm going to divide this container into two parts with the help of semi-permeable membrane. So this is the semi-permeable membrane which I've used in the middle, right? So how many chambers which we got? We got two chambers basically, left chamber, right chamber. The left chamber I'm filling with zinc sulfate. The left chamber I'm filling with zinc sulfate. So imagine this is zinc sulfate present in the left chamber. Similarly, in the right chamber, what do we have? My dear students, imagine that in the right chamber, we have got copper sulfate. So basically, in the left chamber, you have got two types of ions, zinc dye positives and SO4 dye negatives. Similarly, in the right chamber, you again have two types of ions, copper dye positives and SO4 dye negatives. I would say the left chamber contains equal number of cations and anions. The right chamber also contains equal number of cations and anions. So both the solutions right now, they are electrically neutral, right? Now, introduce the zinc rod in the solution. Introduce a copper rod in this particular solution. Now this is the zinc rod and this is the copper rod. So can I say this is the zinc electrode now and this is the copper electrode? So we have got two electrodes now, zinc electrode, copper electrode. Now dear students, what exactly you should be doing? You should be connecting them externally with the help of the voltmeter. Connect them externally with the help of voltmeter. If I ask you whether this cell is completed externally, right? Whether the circuit is completed externally, absolutely you have completed the circuit externally. And internally, I would say they're also connected because the solutions, they are in direct contact with the help of semi-permeable membrane. So internally the cell is connected. Externally also the circuit is complete. Internally also the circuit is complete. So I would say the cell is complete right now. It's complete to work. I have not used salt bridge right now. I have not used salt bridge. By chance, if I do not use salt bridge, what's going to happen? Try to understand. See, this is your anode, right? This is your anode. And in the similar way, this is your cathode. At anode, what's going to happen? Oxidation is going to happen. The zinc rod is made up of zinc atoms. Those zinc atoms will undergo oxidation, will get converted into zinc dye positive. And that extra zinc dye positive is going to enter into this solution, due to which the solution carries what? Positive charge. Similarly, copper dye positive in the right chamber, it's going to collide with the rod. It's going to take electrons from the rod and it will get converted into Cu solid. That Cu solid will get deposited on the rod. But what happened to the number of Cu dye positives in the solution? Since Cu dye positives, they are getting reduced. They are taking electrons from the rod, getting converted into Cu solid. That Cu solid is deposited on the rod. So I would say this right chamber will become Cu dye positive deficient. Already there were equal number of cations and anions. Now cations will be less. If cations are less, I'll say this particular solution, this particular chamber, it gets a negative charge. Now tell me one thing. Left chamber got positive charge. Right chamber got the negative charge. And I say this positive and negative, it's going to attract. This is positive and this negative. They attracted, they got accumulated at the junction. Similarly, one more zinc atom will undergo oxidation. One more zinc positive will come into the solution. And similarly, one more negative charge here, positive negative will attract. Again, this process will keep on happening continuously. The process will happen continuously, positive, negative, right? The process happened continuously. If I talk about this particular junction, on the left of this particular junction, can you see positive charges? On the right of this particular junction, do you see the negative charge? Absolutely. Can I say at this junction, potential difference got created? Can you see at this particular junction, potential difference got created? Because on the left side, you have got a positive charge. On the right side, you have got negative charge. A potential difference, an extra potential difference is getting created at the junction. And dear students, this particular potential difference which gets created at the junction, you call this potential difference as the liquid junction potential. You call this potential difference as the liquid junction potential, right? And people, if you do not use the salt bridge, we'll get this extra potential difference here, which is something you call as the liquid junction potential. And by chance, if you use the salt bridge, what is going to happen? If you use the salt bridge, what's going to happen? As soon as positive charge is accumulated in this container, in the left chamber, at the same time, SO4 di-negative would have come from salt bridge, neutralized it. As soon as negative charge got developed in the right container, at the same time, K positive would have come from the salt bridge and neutralized it. So there was no positive and negative. If there was no positive and negative, I would say there was no potential difference which would have got created at the junction, right? Yeah. So can I say this particular salt bridge, it is avoiding the liquid junction potential? Absolutely, it's avoiding the liquid junction potential, right? Is it clear to everyone? Quickly in the chats. Quickly in the chats with the thumbs ups, people. Everyone. Yeah? Wonderful. Now have a look on a few more things. Since I told you the salt bridge, it contains inert electrolyte. Now people, if I ask you, what inert electrolyte does? You saw its function. So which type of salt we can use as the inert electrolyte? Condition for the salt to be used as the inert electrolyte. Condition for the salt to be used as an inert electrolyte. Number one. The ions of the inert electrolyte. The ions of inert electrolyte should have same ionic mobility. This is point number one. The speed with which K positive enters into the solution with the same speed SO4 di-negative enters into another solution. So the cation and anion of the inert electrolyte, they should move with the same speeds. They should have got same ionic mobility. Number two, the ions of inert electrolyte should not participate. The ions of the inert electrolyte should not participate in the net cell reaction. It should not participate in the net cell reaction. My dear students, if you look at the net cell reaction, In this net cell reaction, do you see K positive or SO4 di-negative? There is no K positive or SO4 di-negative here. So the inert electrolyte which you use in the salt bridge, let me tell you, it should not participate in the net cell reaction, right? So you'll be using that type of inert electrolyte whose cation and anion speed, whose cation and anion mobility will be the same, number one. Number two, what should be there? The ions of the inert electrolyte, they should not participate in the net cell reaction. I hope this is super clear to everyone. Let me know once in the chats if all these things are clear. Let me know quickly in the chats if all these things are clear. These are the conclusions. Any conclusion can be asked in your examination. Any conclusion can be asked in the examination, people. Right? Zinc electrode, anode, oxidation, loss of electrons. Copper electrode, cathode, reduction, gain of electrons. Direction of electrons from anode to cathode. Direction of current, cathode to anode. Zinc electrode keeps on dissolving. Its thickness reduces. Thickness of copper electrode increases with time. Similarly, if I talk about salt bridge, completes the internal circuit. It avoids the liquid junction potential, maintains the electrical neutrality. In the salt bridge, we use inert electrolyte like NH4NO3, KNO3, this mixed with gelatin to get the jelly-like paste, etc., etc. All these things are clear? All these things are clear? Let me know once in the chats. Rupa, which example you're asking? What example? This is the most typical example of the galvanic cell. You will see millions of galvanic cells in some time. Just wait for it. Don't spam the chats. Once you write something in the chats, just once. Don't spam. People, let me know in the chats if all the things are clear till here. Quickly, everyone. Quickly. All the things are clear? Perfect, guys. Now it's time to see exactly how do we represent the galvanic cells, right? How do we represent galvanic cells? Let's get to know about that. See, guys. First of all, let's try to see how do we represent the Daniell cell. Daniell cell, it is one of the common example. It is one of the common example of the galvanic cell. Let's see exactly how this Daniell cell is represented. So when you try to represent a galvanic cell, in the middle, you'll be using two lines. And these two lines, they are going to represent a salt bridge. These two lines are going to represent the salt bridge. Okay. On the left side of the salt bridge, you'll be using anode. On the right side of the salt bridge, you'll be using cathode. And you already know at anode what happens? At anode, oxidation takes place. And you already know at cathode what happens? At cathode, reduction takes place. This is something which you already know. Perfect. The general representation of the galvanic cell. Use the two lines in the middle, salt bridge. On the left side, you'll be writing the anode. On the right side, you'll be writing the cathode. Now, let's exactly see how these galvanic cells are actually represented. Try to understand what exactly I'm going to do. Try to understand what exactly I'm going to do. My dear students, in case of galvanic cells, what do we need exactly? We need two electrodes. In case of galvanic cell, we need two electrodes. Take two electrodes, connect them externally, connect them internally. Connect them externally, connect them internally. Right? You'll be getting a complete cell. Perfect. The most common example was Daniell cell, in which the two electrodes were zinc and copper. Right? In case of other galvanic cells, you can take any electrode, hydrogen electrode, cadmium electrode, any two electrodes connect externally as well as internally, you will be getting a galvanic cell. Now, how do you represent the galvanic cell? With the help of their net cell reaction. Imagine that there is a galvanic cell in which you have used two electrodes, right? This is the net cell reaction taking place in the galvanic cell. With the help of this particular net cell reaction, you should know how to represent the galvanic cell. Try to understand. Try to understand. See, guys. First of all, since this is the net cell reaction, if I ask you what is the charge on zinc? 0. What is the charge on copper? +2. What is the charge on this zinc? +2. What is the charge on this copper? It is 0, right? Okay. Perfect. Now, people, try to understand. Is the oxidation state of zinc increasing or decreasing? It's increasing from 0 to +2. Copper dye positive. +2 to 0, decrease in the oxidation state. Increase in the oxidation state is something which you call as oxidation. So I would say zinc is undergoing oxidation. Copper dye positive is undergoing reduction. Now remember, oxidation takes place at anode. Reduction takes place at, it takes place at cathode. Since you identified which one is going to behave like the anode, which one is going to behave like the cathode, right? Now people, how do you represent it? The two lines, they are going to represent the salt bridge, which we discussed a few minutes back, and someone is still spamming what is salt bridge, what is salt bridge. Nonsense, girl, she is. It's been half an hour, I've been teaching you what is salt bridge, and you are coming and entering into the session and spamming the chat with what is salt bridge, what is salt bridge. Are you out of your mind? You can get the hell out of my class, please. It's been 1 hour and I've been teaching what is salt bridge. I've given you functions of the salt bridge. Suddenly you're entering into the class, you were somewhere else till now. Suddenly you're coming into the class and spamming the chats, that too. I've got the option of blocking as well, by the way. Try to understand now. These two lines, what do they represent? They represent the salt bridge. And on the left of the salt bridge, what do we write? We write anode. At anode, what happens? Oxidation. Oxidation of what is happening? Oxidation of what is happening? Oxidation of zinc is happening. And this zinc is getting converted into zinc dye positive. So on the left side, what is happening? Zinc solid, it is getting converted into zinc dye positive. And this zinc dye positive, it goes into the left container, left chamber, if you remember. Imagine that the concentration of zinc dye positive in the left chamber, imagine that is C1 molar. Imagine that is C1 molar. Similarly, on the right side, what do we write? On the right side, we write the cathode. And at cathode, reduction takes place. Reduction of what is taking place? Copper dye positive. And copper dye positive is getting converted into copper solid. So at cathode, you got to know that copper dye positive, which was there in the right solution, right chamber, that collided with the rod, took 2 electrons from the rod and got converted into Cu solid. I hope you remember that. So this copper dye positive, which was there in the right chamber, let's assume that its concentration is C2 molar, right? And it got converted into copper solid. So this is how you represent your galvanic cell, whose net cell reaction was given to us. I hope this is clear, right? I hope this is clear. I hope this is clear. Similarly, let me take one more example. With that, every single thing will be clear to you. Imagine, my dear students, you have got a galvanic cell. Imagine you have got a galvanic cell in which the net cell reaction is this one. Imagine you have got a galvanic cell in which net cell reaction is this one. From the net cell reaction, can we write the galvanic cell? Can we represent the galvanic cell? Absolutely, we can do that. What is the charge on this iron? It's 0. Charge on this copper, it's +2. Charge on this particular iron, it's +2. Charge on this copper, it's 0. Identify first of all which one is your anode and which one is your cathode. Identify. Iron is changing its oxidation state from 0 to +2. 0 to +2 means increase in the oxidation state. Increase in the oxidation state means oxidation. So this particular iron is undergoing oxidation, and oxidation takes place at anode, right? Similarly, the oxidation state of copper is changing from +2 to 0. +2 to 0 means decrease in the oxidation state. Decrease in the oxidation state is something which we call as reduction. Reduction always takes place at cathode. So first of all, you identified which one is your anode and which one is your cathode. Now, what I'll be doing? I'll be using 2 lines. These 2 lines represent the salt bridge. On the left side of the salt bridge, I'll be writing anode. And at anode, oxidation takes place. And oxidation of what is taking place? Oxidation of iron is taking place. Iron is getting converted into Fe dye positive, right? Perfect. So what is happening? At anode, Fe solid is getting converted into Fe dye positive. And I must say this Fe dye positive will go into the left container in which the concentration of Fe dye positive, imagine that, assume that is C1 molar. On the right side, you will have to write cathode. At cathode, reduction takes place. Reduction of what? Cu dye positive. Cu dye positive will get converted. Cu dye positive, which was there in the right container, whose concentration, imagine, was C2 molar, it got converted into Cu solid, right? So this is how you represented this particular cell over here. Yeah? Is this clear? Quickly. Is this clear? Quickly. Shaurya, you can check the name of the channel. It is Unacademy NEET English. Okay? Perfect. Let's take one more example. Imagine that you have got a galvanic cell. Imagine that you have got a galvanic cell in which this is the net cell reaction. By looking at the net cell reaction, you should be able to write. You should be able to represent the cell. Again, what I'll be doing? So first of all, the charge on zinc is 0. The charge on zinc here is +2. 0 to +2 means increase in the oxidation state. Increase in the oxidation state is oxidation. And oxidation takes place at anode. If this is anode, that means this has to be your cathode. Right? At cathode, reduction takes place. So you identified the anode and cathode. Perfect. Now people, use the 2 lines as the salt bridge. On the left side, you'll be writing the anode. At anode, zinc is getting converted into zinc dye positive. So zinc solid at anode is getting converted into zinc dye positive. And this zinc dye positive enters into the left chamber in which the concentration of zinc dye positive is, for example, C1 molar. Right? Similarly, on the right side, at the right side, what's going to happen? At the right side, you'll be writing the cathode. And at cathode, reduction takes place. Reduction of what? H positive. And H positive is getting converted into H2. So basically, H positive, whose concentration in the right chamber is, for example, C2 molar, it is getting converted into H2 gas. Few minutes back only I told you, how do you make the hydrogen electrode? With the help of platinum solid. With the help of platinum solid, you make the hydrogen electrode. So I'll be writing platinum solid as well here, right? I hope this is clear. I hope this is clear to everyone. Okay. Let me take one more example, and with that, we'll be moving on to the new concept. See, guys, let's assume you have got a galvanic cell in which this is the net cell reaction. By looking at the net cell reaction, try to identify it. Try to represent the galvanic cell. How? The charge on hydrogen is 0. The charge on copper is +2. The charge on hydrogen is +1. The charge on copper is 0. Check it out now. 0 to +1. Increase in the oxidation state. Increase in the oxidation state means oxidation. Oxidation takes place at anode. So you got to know what your anode is. Copper, +2 to 0. +2 to 0. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. And you know, reduction takes place at cathode. So you identified your anode and cathode. So what you'll be doing? Again, draw the two lines. These two lines represent the solid bridge. On the left, you'll be writing the anode. And at anode, H2 is getting converted into H positive. At anode, H2 gas is getting converted into H positive. And this H positive, it enters into the left container in which the concentration of H positive, imagine that is C1 molar. Now this is the hydrogen electrode. Hydrogen electrode is made with the help of what? It is made with the help of platinum solid. So I've written platinum solid with it as well, right? I've mentioned platinum solid here as well. Now on the right side, what do you have to write? You will have to write cathode. And at cathode, reduction takes place. A reduction of what? Copper dye positive. And this copper dye positive, it's undergoing reduction. This copper dye positive is present in the right chamber, right? In which the concentration of Cu dye positive, imagine that it is C2 molar. And my dear students, this copper dye positive, it is getting converted into copper solid. So this is how you represent the cell. This is how you represent the cell. Okay? This is how you represent the cell. Perfect? This is how you represent the cell. Can you represent this one? I think I've already showed this. Leave this aside now. Okay, the other one. Can you represent this particular cell? Can you represent this particular cell? Try to identify what exactly should be done. The oxidation state of chromium right here is +6. Right here it's +2. Oxidation state of chromium here is +3. And here it's +3 as well. Perfect. You got the oxidation states. Now tell me one thing. Is the oxidation state of chromium increasing or decreasing? +6 to +3. Decrease. Decrease in the oxidation state is something which you call as reduction. And reduction takes place at cathode. So this is your cathode. If this is cathode, that means this has to be your anode. So you identified your cathode and anode. So draw the two lines. These two lines will be representing solid bridge. On the left side, write the anode. And at anode, you can see Fe dye positive is getting converted into Fe tri positive. So I'll be writing like this. Fe dye positive is basically getting converted into what? Fe tri positive. Similarly, on the right side, you'll be writing cathode. And at cathode, Cr2O7 dye negative is getting converted into Cr tri positive. So Cr2O7 dye negative is getting converted into Cr tri positive. So this is your cathode. Now, first of all, try to understand. Try to understand one simple thing. Just a second, guys. Just a second, people. Okay. So try to understand one more thing. This is iron, right? This is basically iron electrode. Till now, if you remember your zinc electrode, we used to have a zinc rod. Zinc rod was dipped into zinc dye positive. Here there is no rod. I mean, what kind of rod here is? I was taking zinc rod, which was made up of zinc atoms, right? And those zinc atoms were dipped in zinc dye positive ions. Similarly, copper electrode. Take the copper rod, introduce that in copper dye positive. Yeah? And here you have got iron. Here you have got iron electrode. So again, in order to make this electrode, you will take the help of platinum solid. Again, over here you have got iron as well as iron. So this particular electrode is also made with the help of platinum solid. Perfect. I hope this is clear. I hope this is clear. So this is how you represent it. For example, there is one more cell reaction of some galvanic cell which is given to me. How do I represent it? How do I represent it? Again, the simple procedure you'll be following. Calculate the oxidation state of manganese here, it's +7. Calculate the oxidation state of carbon over here, it's +3. Oxidation state of manganese here, it's +2. Oxidation state of carbon over here, it's +4. Agreed? Now tell me one thing. What is happening to the oxidation state of manganese? +7 to +2, decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. Reduction takes place at cathode. So this is going to be your cathode, right? +3 to +4. +3 to +4. Increase in the oxidation state means oxidation. Oxidation takes place at anode. So you identified your anode and cathode. You identified your anode and cathode. Now use the two lines as the salt bridge. On the left side, try to write anode. And at anode, the oxalate ion, it is getting converted into carbon dioxide. The oxalate ion, C2O4 di negative, it is getting converted into carbon dioxide. Similarly, on the right, you'll be writing the cathode, and at cathode, reduction takes place, MnO4 negative gets converted into Mn di positive. So I would say MnO4 negative is getting converted into Mn di positive here, right? Again, have a look. This is gas, this is ion. So this is a new type of electrode. So what kind of electrodes we have discussed till now? We have discussed metal ion electrode. Metal, for example, zinc rod introduced in zinc di positive. So metal ion electrode. Copper rod introduced in Cu di positive. So metal ion electrode. This is not metal ion electrode. This is not your metal ion electrode, right? This is ion, this is ion. So whenever you do not have the metal ion electrode, you'll be using platinum with it, right? So in order to make this particular electrode, you'll take the help of platinum. Here also you'll take the help of platinum. So this is how you're going to represent this particular cell as well. Yeah? Perfect. I hope these type of things are clear to you. Now we will try to understand few more things. Till now I was teaching you how to represent a cell, right? How was represent a cell. Now comes the most important part. If the cell is given to you, after looking at the cell, how do you write the cell reaction? After looking at the cell, how do you write the cell reactions? That is important, right? So mark the heading as how to write the cell reactions. This is most important part over here, because afterwards I'm going to teach you the Nernst equation. Nernst equation you can only do if you understand this particular topic, right? How to write the net cell reaction. Okay, tell me one thing, guys. Do you remember how to write the equilibrium constant? Do you remember how do we write the equilibrium constant of some reaction? Do you remember that? Quickly. Do you remember that? Yeah, yes or no? I hope you do, right? Okay. Now, for example, let's say you have got a cell like this. Zinc solid getting converted into zinc di positive, salt bridge, copper di positive getting converted into copper solid. Imagine this is the cell which is given to us. After looking at the cell, what all parameters we should conclude from the cell? What all parameters we should get from the cell? See, guys. Point number one. This is the salt bridge. On the left side of the salt bridge, you know it's going to be anode always. On the right side of the salt bridge, it's going to be cathode always, right? And at anode, what happens? At anode, oxidation takes place. Your zinc is getting converted into zinc di positive. See, 0 to +2. 0 to +2, increase in the oxidation state. Oxidation means loss of electrons. So basically at anode, oxidation takes place, and oxidation means loss of electrons. So I would say zinc has to go into zinc di positive. So the reaction has to be zinc solid. It will be getting converted into zinc di positive aqueous. And with this, you will be writing 2 electrons. Because the reaction is taking place at anode. And at anode, oxidation takes place. Oxidation means loss of electrons. So zinc is getting converted into zinc di positive. 0 to +2. Increase in the oxidation state means oxidation, means loss of electrons. So when zinc will be getting converted into zinc di positive, it will be giving 2 electrons, right? Perfect. Similarly, what is happening at cathode? You know, at cathode, reduction takes place. Look at the cathode. +2 to 0. +2 to 0 means decrease in the oxidation state. +2 to 0 means decrease in the oxidation state. Decrease in the oxidation state means reduction. Reduction means gain of electrons. So I would say copper di positive will be gaining some electrons, and then only it will be getting converted into copper solid. So if I ask you how many electrons this copper di positive will be gaining, it's simple. I would say copper di positive will be gaining 2 electrons, and it will be getting converted into copper solid. This is the reaction taking place at cathode. Now you got the reaction at anode, you got the reaction at cathode. What is the next step? You will have to write the net reaction. My dear students, before writing the net reaction, what you need to do? You need to balance the electrons. Are the electrons already balanced? Yes, the electrons are balanced. Now you can directly add them. And when you add them, what exactly you'll be writing? You should be writing zinc solid plus copper dye positive aqueous. What does it give us? It gives us zinc dye positive aqueous. And with zinc dye positive aqueous, you'll be writing copper solid as well. So this is the net cell reaction which is taking place in the galvanic cell, which is given to us, right? This is the net cell reaction. If I ask you, since you got to know the net cell reaction, if I ask you how many moles of electrons got exchanged in the net cell reaction, you will directly say 2 moles of electrons got exchanged in the net cell reaction. If I ask you, how do you write the reaction quotient, QC? Reaction quotient. My dear students, if you remember, reaction quotient expression is written in the similar way as you write the equilibrium constant expression, right? You'll be starting with the product. You'll be starting with the products, right? In order to write the QC, you'll be starting with the product. And that reactant or product which will be present in aqueous state, you'll be using the term concentration for that. That reactant or product which will be present in gaseous state, you'll be using partial pressure term for that. That reactant or product which is in solid state or liquid state, right? You're not going to consider that. Its active mass is taken as unity. Leave that part aside. Tell me one thing. In order to write the expression for QC, you'll be starting with the product. This particular product is in aqueous state. So you'll write concentration of zinc dye positive. Raised to the power, its stoichiometric coefficient, that's 1, right? This one is in solid state. Its active mass is unity, nothing to do with it. Divided by. This is also in solid state. Its active mass is unity, nothing to do with it. This copper dye positive, it is in aqueous state. So you'll be using the term concentration. So concentration of Cu dye positive raised power 1. So this is how you write the expression of QC for this particular cell that's given to us. These are 3 important points which you have to learn at any cost. Then only you can master the electrochemistry. First, write the net cell reaction, get the value of N, and write the QC expression. Let me take a few more examples. Wait. Let me take a few more examples. For example, the second example which I'm taking, it is like this. Understand, guys. Let's say you've got the cell like this. Ag solid, Ag positive, salt bridge, H positive, H2 gas, and here this is platinum solid. Let's assume this is a cell that's given to me, right? So after looking at this cell, I should know all the parameters. First thing, what is the first thing? On the left side of the salt bridge, what do I write? I'll be writing the anode. On the right side, I'll be writing the cathode. Correct? One is anode, one is cathode. Perfect. Now people, at anode what happens? Oxidation takes place. So the reaction taking place at anode will be the oxidation reaction. Oxidation means loss of electrons. See, this is 0, this is +1. 0 to +1, increase in the oxidation state means oxidation, right? So Ag has to get converted into Ag positive, then only I can say that oxidation is taking place. So Ag solid, it has to get converted into Ag positive, right? Then only I'll say oxidation will take place. Now, when it's oxidation, loss of electrons takes place. Loss of electrons. Now, how many electrons are lost? I would say when Ag is getting converted into Ag positive, this Ag will be losing some electrons. How many? How do you check that? Final oxidation state minus initial oxidation state. Final minus initial will give you 1. So it is losing 1 electron here basically, in short, right? Similarly, at cathode. At cathode, what is happening? At cathode, I must say, reduction is taking place. Your H positive is getting converted into H2. So +1 to 0. +1 to 0 means decrease in the oxidation state. +1 to 0 means decrease in the oxidation state. Decrease in the oxidation state means reduction. Reduction means gain of electrons. So H positive has to get converted into H2. Then only reduction will take place. So what has to be the reaction? What has to be the reaction? So what should we form? We have to form H2 gas. So to form H2 gas, how many H positives do we need? We need 2 H positives. We need 2 H positives. So H positive should be gaining electrons, then only it will be getting converted into H2. Correct? How many electrons? Check it out. How many electrons? How many electrons H positive should? How many electrons will be participating in this reaction? Can you let me know that? How many electrons will be participating in this reaction? Say, for example, if you have 1 H positive, one H positive will gain one electron, will get converted into H. But do I have to make H or H2? I have to make H2. To make H2, you should take two H positives. Two H positives will gain 2 electrons, right? Perfect. So plus 2 electrons. Now tell me one thing. In order to write the net cell reaction, do I have to add the reactions directly? No, I'm not supposed to add the reactions directly. So what do I need to do? I'll be balancing the electrons first. In the first reaction, you've got 1 electron. In the second reaction, you've got 2 electrons. So I'll be multiplying this reaction by 2. When you multiply this particular reaction by 2, this becomes 2 times, this becomes 2 times, even this becomes 2 times. Now add them up. It is going to be 2 times Ag solid plus 2 times H positive aqueous. It gives what? It gives 2 times Ag positive aqueous plus H2 gas. This is your net cell reaction. This is your net cell reaction. And my dear students, in this particular net cell reaction, if I ask you how many moles of electrons got exchanged, you'll say 2 moles of electrons got exchanged in the net cell reaction. If I ask you, how do we write the QC expression? QC is going to be, start with the product. This product is in aqueous state, so use the term concentration. Concentration of Ag positive raised par stoichiometric coefficient, that's 2. This H2 is in gaseous state, use the term partial pressure. Partial pressure of H2 raised par stoichiometric coefficient, that's 1. Divided by, this is in solid state, so its active mass is unity, nothing to do with this. H positive, use its concentration, raised par what? Raised par 2. So this is how you write QC expression as well. I hope this is super clear to everyone, right? Okay? Clear? Clear, people? Perfect. For example, this is the cell that's given to me. Try to write all the parameters. Try to write all the parameters related to this particular cell. Whatever I have taught you till now, utilize all the concepts and try it out. See guys, these two lines, they are representing the solid bridge. On the left side, you always write anode. On the right side, you always write cathode, right? And you know, at anode, oxidation takes place, loss of electrons, right? You can check it out also. H2 is 0, here it's plus 1. 0 to plus 1 is increase in the oxidation state. It means oxidation, loss of electrons, right? Now, tell me the reaction taking place at anode. I would say at anode, H2 has to get converted into H positive. At anode, I must say, H2 gas, it has to get converted into H positive. But should I write H positive or 2 times H positive? Absolutely, I should write 2 times H positive, right? Because this H2. Perfect. Now, you know, when H2 is getting converted into H positive, 0 to plus 1, increase means oxidation, loss of electrons. So H2 has to lose some electrons, then only it will get converted into H positive. Now, how many electrons will it lose? Check it out. Final minus initial. Final minus initial, the value is 1. But 1 is the change in the oxidation state for 1 atom of hydrogen. But I have 2, right? So how many electrons it will be losing? It will be losing 2 electrons. It's simple. It's simple, guys. See, when one hydrogen has got 1 electron, right? When it loses 1 electron, it gets converted into H positive, right? But do I have 1 hydrogen? No, we have got 2 hydrogens. So 2 hydrogens will be giving 2 H positives. And with that, you'll be getting 2 electrons as well. Perfect. So you got the reaction at anode. Now it's time to write the reaction at cathode. Time to write the reaction at cathode. At cathode, what happens? Reduction. Plus 4 to plus 2. Plus 4 to plus 2. Decrease. Decrease means reduction, gain of electrons. Right? So I would say Sn plus 4 aqueous. Sn plus 4 aqueous. At cathode should get converted into what? It has to get converted into Sn plus 2 aqueous. Now, at cathode, reduction takes place, gain of electrons. So I must say Sn plus 4 has to gain electrons. Then only it will get converted into Sn plus 2. Right? Now, how many electrons this Sn plus 4 will be gaining? Final oxidation state minus initial. I would say 2 electrons it will be gaining. Tell me one thing. Whether electrons are balanced in both the reactions or not. Yes, the electrons are balanced. Electrons are balanced in both the reactions, right? Yeah? Electrons are balanced in both the reactions. So directly you are going to add them up. When you add them up, what do we get? We get H2 gas plus Sn plus 4 aqueous. It gives 2 times H positive aqueous plus Sn di positive aqueous. Perfect. Now people, if I ask you how many moles of electrons got exchanged, you will directly say 2 moles of electrons got exchanged, right? 2 moles of electrons got exchanged. So I would say N value is equal to 2 moles of electrons got exchanged in the net cell reaction. Now, if you ask me what is the QC value, start with the product. Start with the product. This H positive is an aqueous state, so use the term concentration. Concentration of H positive raised by stoichiometric coefficient, that's 2. Sn di positive is again aqueous state. So concentration of Sn di positive raised by stoichiometric coefficient divided by H2 is in gaseous state. So use the term pressure. Pressure of H2 raised by stoichiometric coefficient. Sn plus 4 is in again aqueous state. So use the term concentration raised by stoichiometric coefficient. This is how you write the expression for QC. Is this clear? Is this clear, people? Is this clear? Quickly. For example, this is the question. You have to write the net cell reaction, you have to write the QC, you have to get the N value. Guys, these are the most important things which I'm teaching you right now. Because if all these things are not clear, definitely electrochemistry can never be clear. Honestly, I'm telling you. Okay? Try to understand. Try to understand. See guys, these two lines, they'll be representing what? Solid bridge. On the left side, we'll be writing anode. On the right side, we'll be writing cathode. So you have got anode and cathode, right? Nowadays, students, at anode, what happens? Oxidation takes place. At anode, oxidation takes place. Oxidation means loss of electrons. See, oxidation state here is 0. It's plus 4. 0 to plus 4 means increase. Increase means oxidation. Oxidation means loss of electrons. So I would say N has to get converted into Sn plus 4. I would say Sn solid should get converted into Sn plus 4, right? Then only oxidation will happen. Now it's evident when Sn gets converted into Sn plus 4, increase in the oxidation state means oxidation means loss of electrons. So Sn has to lose certain electrons. Then only it will get converted into Sn plus 4. Now how many electrons? Final minus initial. The value is 4. So I would say it will be losing 4 electrons. Yeah. Similarly, what is going to happen at cathode? I would say at cathode, reduction takes place. Reduction takes place. Reduction means gain of electrons. See, the oxidation state here is 0. Here it's minus 1. 0 to minus 1 means decrease in the oxidation state. Decrease is the reduction. So, at cathode, Cl2 has to get converted into Cl negative. At cathode, Cl2 has to get converted into Cl negative. So, I must say, Cl2 gas, it has to get converted into Cl negative. Right? And you know, at cathode, reduction takes place, gain of electrons. So I would say Cl2 will be gaining some electrons. Then only it will be getting converted into Cl negative. Now this is Cl2, make it 2 times Cl negative. Tell me one thing. 0 to minus 1. What is the change? 1. 1 is the change for one atom. How many we have? 2. So basically, it will be gaining 2 electrons. Are the electrons balanced in both? No. You'll be balancing the electrons. So multiply this particular reaction by number 2. This becomes 2 times. This becomes 4 times. This becomes 4 times. Now add these two reactions. I would say 4 and 4 got cancelled. So the net reaction is going to be 10 solid. 10 solid plus 2 times Cl2 gas. Plus 2 times Cl2 gas. Just a second. Yeah. 2 times Cl2 gas. It gives what? It gives Sn plus 4 aqueous. And with that, you'll be writing 4 times Cl negative aqueous as well. So this is your net cell reaction. If you ask me, how many moles of electrons got exchanged? How many moles of electrons got exchanged? I'll directly say 4 moles of electrons got exchanged. What is the value of QC? What is the value of QC? Start with the product. This is an aqueous state. So it has to be concentration of Sn plus 4 raised by 1. Right? It has to be concentration of Cl negative raised by 4 divided by. This is in solid state. Its active mass is unity. This Cl2 is in gaseous state. So use the term pressure. So pressure of Cl2 raised by 2. So this is how you're going to write QC for the net reaction as well. Right? Is this clear to everyone? Is this clear to everyone quickly? Okay. One example in which you might do a mistake. One example in which you might do a mistake. For example, I'm writing like this. I'm representing a cell like this. Platinum solid. This is Fe di positive. Getting converted into Fe tri positive. This is salt bridge, for example. And this is MnO4 negative getting converted into Mn di positive. This is one more platinum solid. Let's assume this is a cell which is given to me. Imagine that it is a cell which is given to me. Now you have to do every single procedure. Anode reaction, cathode reaction, net reaction, N value and QC. Here you can do a mistake. Try to understand what that mistake is. First of all, I'll be writing the reaction which should take place at anode. At anode, oxidation takes place. Your Fe di positive is getting converted into Fe tri positive, right? plus 2 to plus 3. Increase in the oxidation state, loss of electrons. So basically, Fe di positive aqueous will be losing certain electrons and then only getting converted into Fe tri positive aqueous. Now, how many electrons? Final minus initial. I'll say 1 electron. This is the reaction at anode, right? Now, if I ask you what is going to be the reaction at cathode, you know, at cathode reduction takes place. At cathode reduction takes place, gain of electrons. Now, my dear students, the oxidation state of manganese here is plus 7. Plus 7 to plus 2. Decrease in the oxidation state. Plus 7 to plus 2. Decrease. Decrease means reduction. So basically, at cathode, MnO4 negative will be finally getting converted into Mn di positive, right? Since it's a reduction reaction, plus 7 to plus 2 means decrease. Decrease means reduction, gain of electrons. How many electrons will be gained? MnO4 negative will be gaining certain electrons. How many? Final oxidation state minus initial. So it will be gaining 5 electrons. Then only it will be getting converted to Mn di positive. Correct? Now, people, are the electrons balanced? The electrons are not balanced in the reaction. So I'll be balancing the electrons. Multiply this reaction by number 5. So this has to be 5 times. Even this has to be 5 times. Even this automatically becomes 5 times. Right? Now you are going to add these two reactions. Just add them up. Just add them up. This is going to be 5 times Fe di positive aqueous plus what? Plus MnO4 negative aqueous. And it's going to give me 5 times Fe tri positive aqueous plus Mn di positive aqueous. This is your net reaction. Perfect. This is your net reaction. Now tell me one thing. How many electrons are being exchanged in the net cell reaction? I would say 5 moles of electrons are exchanged in the net cell reaction. Right? Now one thing is there. Is the reaction balanced or not? This is not the net cell reaction yet. The reaction is not completely balanced. You are supposed to balance the reaction completely. You have to write the reaction in the complete balanced format. It is not present in the complete balanced format, right? So what you shall be doing? Understand. Understand, people. How many oxygen atoms do you have on the left side? 4 oxygen atoms, right? How many oxygen atoms are on the right side? No oxygen atoms. So which side is oxygen deficient? LHS or RHS? RHS is oxygen deficient. How many oxygen deficiency are there on the right side? 4 oxygen deficiency. Number of oxygen deficiency is equal to number of water molecules added on the oxygen deficient side. So on this side, I'll be adding 4 water molecules. I'll be adding 4 water molecules. Now tell me one thing. How many hydrogens on this side? 8. How many hydrogens on this side? No. So which side is hydrogen deficient? LHS side. Hydrogen deficiency is eradicated through H positives. So on this side, we have got 8 hydrogen deficiency. The number of hydrogen deficiency is equal to the number of H positives added on that side, which is hydrogen deficient. So basically, oxygen is balanced with the help of water and hydrogen is balanced with the help of H positives. Something which I've taught you in redox reactions as well, right? Yes? Perfect, people. A Prasant work everywhere has got the sign minus. We always start with minus sign. Minus integral V1 to V2, P gas multiplied by dV. That's for reversible. And for irreversible, it is minus P external delta V, V2 minus V1. This negative is in chemistry basically. In physics, you do not start with negative sign. In physics, your work expression is simple, P delta V. Here it is minus P delta V. And minus here indicates that internal energy decreases during expansion. Internal energy of the system I'm talking about. Right? Okay. So this is the net reaction now. N value is calculated. Now it is the time to get QC expression. In order to get the QC, we have to start with the products. We have to start with the products, right? See, this is aqueous. So use the term concentration. Concentration of Fe tri positive. Raise bar 5. This is aqueous. It is concentration of Mn di positive. Raise bar stoichiometric coefficient, that's 1. This water is in liquid state, nothing to do with this. Divided by. This H positive is in aqueous state, so concentration of H positive raised by 8. Fe di positive is in aqueous state, so concentration of Fe di positive raised by 5. MnO4 aqueous state, so it is concentration of MnO4 negative raised by 1. So this is how you write the expression for QC as well. Perfect. In these questions, see guys, you know why? These are not the actual questions. The actual question will come in the Nernst equation. But Nernst equation, while solving the question based on Nernst equation, you should know all these parameters basically. That's why I'm clearing all the parameters right here. That's why I'm clearing all the parameters right here, so that when I teach you Nernst equation, there'll be no issues at all in doing the equations. Yeah? Clear, people? Clear, clear, clear? Okay. Let me give one last example. Look at this particular example, guys. Look at this particular example. This is the last example of the today's session. Okay? After this, we'll end the session. The next session will be, or should I give you this as the homework? What do you think? What do you suggest? Are you going to solve this? Or let me solve this. The other one I'll be giving you the homework. Okay? And let me tell you, the next session will be on Tuesday, 6 p.m. Lecture number 2 of electrochemistry. Let me solve this. The other question I'll be giving you as the homework. Okay? Let's try to solve this. First of all, these two lines, they represent the salt bridge. On the left side, you'll be writing the anode, right? So this is the anodic part. This is the cathodic part. You know, at anode oxidation takes place. At anode oxidation takes place. So Fe di positive is getting converted into Fe tri positive, right? So Fe di positive aqueous is getting converted into Fe tri positive aqueous. Since it is the oxidation reaction, so loss of electrons has to happen, right? So plus 2 to plus 3. Final minus initial. Value is 1. So the value comes out to be 1 here, right? So 1 electron is lost in the oxidation reaction. Similarly, the reaction which will be taking place at cathode. You know, at cathode what happens? Reduction. At cathode what happens? Reduction. Try to understand. Oxidation state here is plus 6. Here it is plus 3. So plus 6 to plus 3. Decrease in the oxidation state. Reduction. Gain of electrons. So I would say when Cr2O7 dinegative, when Cr2O7 dinegative will be getting converted into Cr tri-positive, definitely this Cr2O7 dinegative will be gaining some electron. Now how many? Plus 6 to plus 3. Change is 3. 3 is the change in the oxidation state for 1 atom of chromium. But I have 2 atoms, so 3 2s are 6. So it will be gaining some 6 electrons, and at the end it will be getting converted into 2 times Cr tri-positive, because you have got 2 chromium, right? Now tell me one thing. Are the electrons balanced? The electrons are not balanced yet. Okay? 6 and this is 1. So multiply this particular reaction by 6. So this has to be 6 times. This has to be 6 times. This has to be 6 times. Now the electrons are balanced. After balancing the electrons, what you need to do? Just add the reactions. When you add the reactions, 6 and 6 got cancelled. The net reaction has to be 6 times Fe di positive aqueous plus what? Plus Cr2O7 di-negative aqueous. It gives 6 times Fe tri-positive aqueous. And with this, I'll be writing 2 times Cr tri-positive aqueous. Tell me one thing, how many moles of electrons got exchanged? I would say 6 moles of electrons got exchanged in the net cell reaction. Can we write the expression for QC? Before writing the expression for QC, check it out. Is the reaction balanced or not? The reaction is not balanced yet. It is time to balance the reaction first, right? It is time to balance the reaction first. On the left side, how many oxygen we have? 7. On the right side, there is no oxygen. So right side is oxygen deficient. So add 7 water molecules on right side, right? How many hydrogen? 14. So on this side, you'll be adding 14 H positives. Perfect. Now the reaction is balanced. Now it's time to write the expression for QC. How do we write the expression for QC? Start with the product. It's an aqueous form, so use the term concentration. So concentration of Fe tri-positive raised power 6. Similarly, it's going to be concentration of Cr tri-positive raised power stoichiometric coefficient, that's 2. It's in liquid form, nothing to do with this. Divide by. Again, use the concentration of Fe di-positive raised power 6. Concentration of Cr2O7 di-negative raised power stoichiometric coefficient, that's 1. And here, it's going to be concentration of H positive raised power 14. So this is how you are going to write the expression for QC as well, right? Is this clear? Quickly, people, one question I'll be giving you as the homework. You are going to let me know the number of moles of electrons exchanged in the net cell reaction. Okay? In the comments once the session ends. Okay? And let me tell you one more thing. On Tuesday, 6 p.m., day after tomorrow, there is one more session of the chapter Electrochemistry. You have to be there on time, right? On this channel itself. The ones who have not subscribed to the channel yet, do subscribe to the channel as well. Okay? Perfect. For example, the cell is like this. Platinum solid, This is Sn di positive, Sn plus 4, salt bridge, Cr2O7 di negative, Cr tri positive. This is platinum solid. This is the cell which I'm giving you. Try to write every single thing related to this particular cell. Write the net cell reaction, N value, as well as QC. Okay? And do let me know the answers in the comment section of this particular video. So dear students, every single parameter, is it clear or not? Is it clear or not? Do let me know in the comment section at the end. Did you get every single thing? Okay? Do let me know in the comment section at the end, not in the chats, the chat box, right? I'm telling you, do write in the comment section at the end, whether you got all the concepts which I taught or not. Perfect? Perfecto, people? Perfecto? Yeah? So the first session is done and it's okay, Narmada, it's okay. It's okay. Don't spam from now onwards because I get frustrated when somebody spams, right? Either he lives or I live. Yeah? Perfect, people? Sir, I need your WhatsApp number. You're not supposed to ask the WhatsApp numbers publicly, right? Welcome back, people. Welcome back. So, my dear students, as you all must be knowing, we are done with the first session of electrochemistry in the last session, if you remember. And today, it's going to be basically the second session. Well, I would say this is the most important session of the chapter electrochemistry, right? Because in this particular session, you're going to learn something really very important, right? Something which students mostly find tough, basically, right? But again, we'll be starting exactly from the basics as we keep on doing in every session, okay? So we'll start with electrode potential, then we'll see the EMF, we'll see how to calculate standard EMF, we'll talk about spontaneity, right? We'll talk about the Nernst equation. So all the most important things of this particular chapter will be done in the today's session. Perfect. But before starting the session, just let me know once in the chats if all of you have watched the first session of electrochemistry. Can you let me know quickly in the chats? I just want to know. Are you guys done with the first session of electrochemistry, which I took like 3-4 days back? Yeah? Quickly, people, quickly. Say yes or no in the chats, quickly. Okay, that's great, that's great. That's great then. Perfect. All right then, so let's get going. Let's get started with the topic that is electrode potential, right? Electrode potential. Just give me a second. Electrode potential. My dear students, how do we define the term electrode potential? This is the first topic. Let me quickly write its definition, then I'll make you understand what it exactly means. Okay? Dear students, electrode potential, it is basically defined as the potential difference that gets created between the rod and the electrolytic solution. The potential difference that gets created between the rod and the electrolytic solution. What does it mean? Let's try to understand this in detail. Okay? Let's try to understand this in detail. My dear students, imagine that you're taking a container. Let's say this is the container which you are taking, right? For example, in this particular container, what exactly I'm going to take I'm taking zinc sulfate into the container. Let's say I'm taking zinc sulfate into the container. Okay. Now, dear students, let's assume that the zinc sulfate, it got completely dissociated into its ions. And its ions are zinc dye positive plus SO4 dye negative. I'm assuming this particular electrolyte, the zinc sulfate which you have taken in the container, I'm assuming this zinc sulfate has got completely dissociated into its ions. So in this particular container right now, can I say there will be equal number of cations and anions? Absolutely. In this particular container right now, there will be equal number of cations and anions. Now what exactly I'm going to do? Since there are equal number of cations and anions in the solution, so I must say this particular solution right now is electrically neutral. There is no net charge present in the solution. Okay. Now, dear students, just do one thing. Just place a zinc rod. Just place a zinc rod in this particular solution. What would you call this particular setup as? You have taken the zinc rod and you have introduced the zinc rod into the solution containing its own ions, right? So what you should be calling this setup as? This particular setup will be called as electrode, right? As simple as that. So I just took a zinc rod. I just introduced the zinc rod into the solution containing its own ions. So I'll be calling this whole setup as the electrode. Point number one. This is the zinc electrode basically. Now, my dear students, this particular zinc electrode, it can behave like the anode. It can behave like cathode as well, right? Let's exactly see what are the possibilities. What exactly will happen if this particular electrode behaves like the anode, if the same electrode behaves like the cathode. Let's see what exactly is going to happen. Try to understand. I'm assuming that the zinc electrode, for example, which you took, let's say it is behaving like the anode. You already know at anode oxidation takes place. If this electrode behaves like the anode, so oxidation will be taking place here, right? And what will happen due to oxidation? I must say, the zinc atoms of which this rod is made up of, those zinc atoms will undergo oxidation, right? Those zinc atoms will undergo oxidation. So I would say the zinc atoms of which rod is made up of, right? Those zinc atoms will undergo oxidation. Oxidation means loss of electrons. So this zinc solid, it will lose 2 electrons and will get converted into zinc dye positive. The zinc solid, right? The zinc atoms of which rod is made up of, they'll undergo oxidation, they'll lose 2 electrons, get converted into Zn dye positive. My dear students, what exactly happened? Try to understand. The zinc atoms of which this rod is made up of, this zinc rod is undergoing oxidation. It is losing 2 electrons and getting converted into zinc dye positive. Tell me one thing. Initially, in the container, there were equal number of cations and anions. Initially, there were equal number of cations and anions. And the solution initially was electrically neutral. Now, what happened? The zinc atoms of which rod is made up of, those zinc atoms are undergoing oxidation. And those zinc atoms are getting converted into zinc dye positives. I would say those zinc dye positives will enter into the solution, right? The extra zinc dye positives, which are produced by the oxidation of zinc atoms of the rod, those extra zinc dye positives will enter into the solution, correct? Initially, the solution was electrically neutral. Now, an extra zinc dye positive is entering into the solution, due to which this particular solution gets a positive charge, right? So, the electrolytic solution, which you took here, this electrolytic solution is getting the positive charge. The 2 electrons which are generated due to the oxidation of the zinc atom, right? These 2 electrons are accumulated on the rod. Perfect. Since electrons are being accumulated on the rod, so I must say, due to the accumulation of electrons, the rod will carry the negative charge. Perfect. So I took one electrode. I assumed that this electrode is behaving like the anode. If the electrode behaves like the anode, oxidation will take place. Oxidation of what will take place? Oxidation of the rod. Oxidation of the zinc atoms of which rod is made up of. And those zinc atoms of which rod is made up of, they got oxidized, got converted into zinc dye positive, gave certain electrons. The extra zinc dye positives, they entered into the solution, due to which solution got positive charge. And these electrons, they got accumulated on the rod, due to which rod got negative charge. Now tell me one thing. What kind of charge do you see in the solution? Positive. What kind of charge do you see on the rod? Negative. Can I say, since solution is getting the positive charge, rod is getting the negative charge, can I say polarity got developed over here? Can I say potential difference got created between the rod and the solution? My dear students, this particular potential difference which got created between the rod and the solution, this potential difference is something which you call as electrode potential. That is a definition which I mentioned over here, right? The potential difference which gets created between what? Between the rod and the electrolytic solution. The potential difference is something which you call as electrode potential. I hope this is clear to everyone, right? Now imagine, my dear students, the same electrode was behaving like the cathode. Imagine that the same electrode was behaving like the cathode, right? What would have happened then? What would have happened? Imagine the same electrode which I took over here, right? Imagine the same electrode is behaving like what? Imagine the same electrode is behaving like the cathode. If the same electrode behaves like the cathode, what will happen? I would say reduction will happen. Reduction involves gain of electrons. So what is exactly going to happen? I would say the zinc dye positives which are there in the solution. These zinc dye positives will collide with the rod, will take 2 electrons from the rod and will get converted into zinc solid. If by chance reduction happens here, reduction of what will happen? Since in the solution there are equal number of zinc dye positives and SO4 dye negatives, I would say the zinc dye positives which are there in the solution, they are going to collide with the rod, they are going to take 2 electrons from the rod. So what will happen? The zinc dye positives which are there in the solution, they are going to take 2 electrons from the rod, will get converted into zinc solid. Now tell me one thing. Initially in the solution, there were equal number of cations and anions. Equal number of cations and anions. Now, cation is undergoing reduction. This zinc dye positive, it's gaining electrons from the rod. It's taking electrons from the rod. It is getting converted into zinc solid. Now tell me one thing. Electrons are being taken out from the rod. If electrons are snatched from the rod, I would say right now, the rod is going to get the positive charge because electrons are snatched from the rod. At the same time, initially, equal number of cations and anions were there in the container. Now, cation collided with the rod, took 2 electrons from the rod, right? Got converted into zinc solid. That zinc solid gets deposited on the rod, right? Due to which, tell me what happened to the number of cations in the solution? Are the number of cations in the solution increasing or decreasing? Quickly. Are the number of cations in the solution increasing or decreasing? Initially, there were equal number of cations and anions, due to which there was no charge, no net charge in the solution. Now, cations are decreasing. If cations are decreasing, can I say the solution overall will get the negative charge? Can I say again polarity got developed between the rod and the solution? Right? Rod is right now getting the positive charge. Solution is getting the negative charge. Can I say again a potential difference is getting created between the rod and the solution? Absolutely. And this particular potential difference between the rod and the solution, this is something which you call as electrode potential, my dear students. Right? Perfect. So I hope you got to know exactly what is actually the concept of electrode potential. So electrode potential is just the potential difference which gets created between the rod and the solution, right? Perfect. Let me know once in the chats if it is clear to everyone. Let me know once in the chats if all these things are super clear to everyone. Because I'm going to teach you some important stuff now. Quickly, people, everyone in the chats. Quickly. Yes? Wonderful. Now guys, try to understand a few more things. This electrode potential which I'm talking about right now, this electrode potential, it is represented by what? It is represented by E. Okay? Electrode potential, it is represented by capital E. Okay? And this electrode potential, we further divide it into 2 categories. One is called as oxidation potential. One is called as reduction potential. One is called as oxidation potential, one is called as reduction potential. The electrode potential, which is represented by E, it's further classified into two types. One is called as oxidation potential, one is called as reduction potential, right? My dear students, this oxidation potential and reduction potential, it gives us the idea of how easily oxidation and reduction takes place at the electrodes, which I'll let you know in some time. But before that, is there any other way to represent the oxidation potential? Yes, there are many ways. My dear students, you can represent oxidation potential like this as well. E of M changes into Mn positive. M changing into Mn positive. This is one more way of representing the oxidation potential. And how you exactly got to know that this term represents oxidation potential? Since if you look at the oxidation state of M over here, it's 0. The oxidation state of M over here is plus N. 0 to plus N means increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation, right? So this represents your oxidation potential. What about reduction potential? My dear students, reduction potential is represented like this. E of Mn positive change to M. E of Mn positive change to M. This is how you represent the reduction potential. Now check it out. The oxidation state of M over here is plus N. The oxidation state of M over here is 0. Plus N to 0. Decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. So this particular term, it represents the reduction potential. So my dear students, electrode potential is exactly of two types. One is oxidation potential, one is reduction potential, right? I hope this particular thing is clear to everyone. And these are the ways by means of which you can represent either oxidation potential or reduction potential, which are the types of what? Which are the types of electrode potential. Okay? Perfect. What is electrode potential? Electrode potential is the potential difference which gets generated between the rod and the solution. If the rod gets negative charge, solution gets positive charge. That means I'm making sure the electrode behaves like the anode. That means that potential difference which we calculated between the rod and the solution, when the rod got negative, solution got positive, that potential difference is what you'll be calling as oxidation potential, right? Similarly, when the rod gets positive, solution gets negative. That means I made sure the electrode behaves like the cathode. At that point of time, the potential difference which got created between the rod, between the positively charged rod and negatively charged solution, that potential difference I'll be calling as a reduction potential. I hope you got the difference between the two, right? One is oxidation potential, one is reduction potential. Perfect. Oxidation potential is the potential difference between negatively charged rod and positively charged solution. Reduction potential, in short, that is the potential difference between positively charged rod and negatively charged solution. Correct? I hope this is clear. Now guys, understand one more thing. Let me tell you electrode potential. Electrode potential when measured under standard conditions. Electrode potential when measured under standard conditions. Is termed as standard electrode potential. Whenever this electrode potential, which is basically the potential difference between the rod and the solution, when it's measured under standard conditions, you call it as standard electrode potential. Now you must be thinking, what these standard conditions are? What these standard conditions are? My dear students, if I talk about standard conditions, what are basically your standard conditions? Under standard conditions, pressure is to be taken as 1 bar or 1 atm, you can say, right? Temperature is taken as constant. Generally, it is taken as 25 degrees centigrade. Concentration of electrolyte in the solution is taken as 1 molar. My dear students, these conditions, when pressure is kept as 1 bar, temperature is taken as constant, generally 25 degrees centigrade. And at the same time, concentration of electrolyte in the container is taken as 1 molar. Or you can say concentration of ion in the solution is 1 molar. At that point of time, I'll be calling these particular conditions as standard condition. Now, Imagine that you have got the electrode and the electrode is kept at pressure 1 bar. Temperature is kept constant. The concentration of ions in the container is kept as 1 molar. That means I have taken electrode under standard conditions. And under standard conditions, whatever will be the potential difference between the rod and the solution, that potential difference I'll be calling as standard electrode potential. Is this clear to everyone? Is this clear to everyone? So in short, electrode potential when measured under standard conditions, it's going to give you what? It is going to give you the standard electrode potential. I hope this is clear to everyone. Okay, so electrode potential when measured under standard conditions, that's called as standard electrode potential. And this standard electrode potential, my dear students, it is represented by E naught. Standard electrode potential, it is represented by E naught. And dear students, this standard electrode potential, it is further of two types. One is called as standard oxidation potential. One is called as standard reduction potential. Standard oxidation potential you can call as SOP. Standard reduction potential you can call as SRP, right? Or there is one more way of representing. The standard oxidation potential you can represent like this: E naught of M changing into Mn positive, right? And standard reduction potential you can represent like this: E naught of Mn positive changed to M. These are the ways of representing the standard oxidation and standard reduction potentials, right? Perfect. I hope this is super clear to everyone. My dear students, there is one more thing. There is one more point. There is one more point. When we talk about the standard electrode potential in general, when we talk about the standard electrode potential of an electrode in general, be it SOP or SRP, let me tell you, SOP or SRP of an element whose electrode you have made, is calculated with the help of a reference electrode. And that reference electrode is something which you call as standard hydrogen electrode. That reference electrode is something which you call as standard hydrogen electrode. So my dear students, let me tell you, the electrode, whatever electrode you have made, for example, zinc electrode, copper electrode, whatever electrode you have, perfect. Every element has got a particular value of its standard electrode potential, be it SOP or SRP. Every element has got a particular value of standard electrode potential, be it SOP or SRP. And that SOP or SRP of an element is measured with the help of one more electrode. And that one more electrode is the reference electrode, with the help of which we calculate the standard electrode potentials of different elements. And that reference electrode is something which you call as standard hydrogen electrode. I'll let you know in some time what this standard hydrogen electrode is all about, right? So why am I introducing the standard hydrogen electrode here? Because every element has got a particular value of SOP, SRP, right? SOP as well as SRP. And those SOP and SRP values are measured with the help of a reference electrode, and that reference electrode is taken as standard hydrogen electrode. So standard hydrogen electrode is the one with the help of which we calculate the SOPs and SRPs of different elements. Okay? Perfect. Let me know once in the chats if all the things are clear till here. Quickly. Let me know quickly in the chats, people. Let me know quickly in the chats, everyone. Okay? All right. Now there are a few more things which I would want to share with you. And what are those things? Those are again very important things. Try to understand. Let me tell you, for an element, whatever element you have, its SOP is always equal to minus times its SRP. This is important. For a particular element, the SOP value is always equal to minus times its SRP. For example, if I say that the SOP of zinc is 1.1 volt, for example, right? Let's say I'm saying the SOP of zinc is 1.1 volt. So what will be the SRP of same zinc? The SRP of same electrode is going to be, just reverse the sign. It's going to be minus times. Okay? Just remember this particular thing. Perfect. Now you must be thinking what kind of idea this SOP and SRP gives us. Before understanding what kind of information this SOP SRP gives us, before understanding that, it is high time to understand the standard electrode potential first. Sorry, standard hydrogen electrode first. Let's get to know how the standard hydrogen electrode is made, right? Which is the reference electrode, which is the standard electrode, right? With the help of which we calculate the standard electrode potentials of different elements. Let's get to know how this particular setup is made exactly. Try to understand, people. This is important. For example, I'm taking a container over here. Imagine this is the container. And in this particular container, what exactly I'm doing? In this particular container, I'm, for example, keeping HCl. So I've got HCl in this particular container. Now imagine that this particular HCl, I'm taking its concentration as 1 molar. And this HCl, for example, it has got completely dissociated into its ions, which are H positive, Cl negative, right? So at time t is equal to 0, the concentration of HCl was 1 molar. This will be 0, this will be 0. Now this HCl, it has got 100% dissociated into its ions. So this is 0. This has to be 1 molar. This has to be 1 molar too. Now people, try to understand. Try to understand. I took HCl in the container. And I'm telling you, the concentration of H positive as well as Cl negative in the container is 1 molar, right? The concentration of H positive, Cl negative, I'm taking as 1 molar. The temperature of the system I have kept as 25 degrees centigrade. I'm keeping the temperature of the system as 25 degrees centigrade. Now after this, dear students, I'm going to take an inverted tube like this. I'm taking an inverted tube like this. And in this particular inverted tube, what exactly am I going to do? In this particular inverted tube, I'm going to keep a platinum wire. Imagine this is the platinum wire. Imagine this is the platinum wire which is coated with platinum black. So it is basically a platinum wire which is coated with platinum black. Now dear students, from this side, I'm introducing H2 gas. I'm introducing H2 gas at 1 bar pressure. I'm introducing H2 gas at 1 bar pressure. What is going to happen? What is going to happen exactly? My dear students, since you are introducing H2 gas through this particular hole, what will happen? The H2 gas will start to adsorb on this platinum surface. H2 gas will start to adsorb. It will get sticked. It will get sticked with the surface of platinum. Perfect. Now imagine you're introducing H2 gas. You're introducing H2 gas until the whole surface of platinum gets covered with hydrogen. Now imagine once whole surface of platinum got covered with hydrogen. Imagine this was the platinum wire. Now the whole surface of this platinum is covered with hydrogen, right? Now how it looks to me? Is it looking like a platinum wire now? No, it looks like a hydrogen rod to me now. It's not a platinum wire now. It looks like a hydrogen wire to me. Now you have got the hydrogen wire which is introduced in a solution containing its own ions. You have got the hydrogen wire which is introduced into a solution containing its own ions. You'll be calling this particular setup as the hydrogen electrode. And which conditions I have kept here? I have kept standard conditions. So this hydrogen electrode I'll be calling as the standard hydrogen electrode, my dear students, right? So this is the standard hydrogen electrode which I've taken. Perfect. Now this standard hydrogen electrode, it's not necessary that every time you'll make it like this. No, you can represent it like this as well. You will simply say I've taken a container in which we have got H positive ions and you have introduced one H2 rod. And it's understood how this H2 rod was was made basically. It's understood. So H2 rod into H positives. This is the hydrogen electrode, right? So you can represent it like this as well, no issues. Now people, this particular hydrogen electrode, it can behave like the anode, it can behave like the cathode as well. And let me tell you, when this hydrogen electrode behaves like the anode, at anode oxidation takes place. When this hydrogen electrode behaves like the anode, oxidation will happen, right? Oxidation means loss of electrons. On the surface of this rod, you have got H2, right? So I would say H2 gas, which is there on the surface of the rod, it will get converted into 2 times H positives, and with that you will be getting 2 electrons, right? If this particular electrode behaves like the anode, oxidation will happen. Oxidation means loss of electrons. Now what is happening basically? The surface contains H2 molecules. Now these H2 molecules will undergo oxidation. They lose electrons. They lose 2 electrons and will get converted into twice H positives. It's simple, guys. See, when you have got the hydrogen atom, if one hydrogen atom loses 1 electron, it gets converted into H positive. Now you have got 2 hydrogen atoms here. So if 2 hydrogen atoms loses electrons, they lose 2 electrons and will get converted into 2 times H positive. Nothing to think a lot about it, right? Okay. So this is the reaction which will happen when the hydrogen electrode behaves like the. This is the reaction which is going to happen when your hydrogen electrode behaves like the anode. Okay. If the same electrode behaves like the cathode, if the same electrode behaves like the cathode, what's going to happen then? Reverse the reaction. Simple. Reverse the reaction. It becomes 2 times H positives. So H positives which are there in the solution, they'll collide with the rod. They'll take 2 electrons from the rod, will get converted into H2 gas. So this is the reaction which will happen when the same electrode will behave like the cathode. Because at cathode, reduction takes place. Now, my dear students, if this hydrogen electrode behaves like the anode, or if the hydrogen electrode behaves like the cathode, in both the categories, SOP as well as SRP of the hydrogen electrode, SOP as well as SRP of the hydrogen electrode is taken as 0 as per convention, right? As per reference, the value of SOP as well as SRP of the hydrogen electrode, it is taken as 0, right? It is taken as 0 as per reference. Okay. If I ask you, how do you represent SOP of hydrogen electrode? How do we represent it? I'll write E. Okay, if I write not, that means standard, right? Now, for example, if I write something like this, H2 gives H positive. H2 gives H positive. H2 gives H positive. 0 to plus 1. 0 to plus 1. Increase, oxidation. So this is SOP. This is SOP of hydrogen electrode. Similarly, what about SRP of hydrogen electrode? Just reverse it. It becomes H2 and this, sorry, H positive gives H2. Plus 1 to 0. Decrease. Decrease means reduction. So this SRP. SOP as well as SRP of hydrogen electrode, it's taken as 0 as per convention, as per reference. I hope this is clear. I hope this is clear to everyone. Yeah? Clear, people, quickly? Is every single thing clear till here? I want you to let me know in the chats. Are all the things clear? If all the things are clear, then only I can tell you some important things about this electrode potential, which are going to have a lot of significance. Okay, perfect. Wonderful. Now try to understand the significance of electrode potential. What kind of information this electrode potential gives us? What kind of information it gives us? My dear students, do remember, more the standard oxidation potential of an element. More the standard oxidation potential of an element. More is the tendency of an element to undergo oxidation. More the standard oxidation potential of an element, more is the tendency of an element to undergo oxidation. If more is the tendency of an element to undergo oxidation, better will be the reducing agent. Better, I'll be calling it as a reducing agent. I'll be calling it as a better reducing agent. And do remember, the one which will be the better reducing agent will have more reducing power. This is the first statement which I would want every one of you to know. you'll be given a lot of questions in which you will have to compare different elements on the basis of their reducing agent capabilities, on the basis of their reducing power, right? Just do remember one thing. More the SOP, more the standard oxidation potential of an element, more is its tendency to undergo oxidation, better the reducing agent, more the reducing power. As simple as that. Okay? As simple as that. Now, we will one more statement. Its application you'll get in some time. Second statement. More the SRP of an element, more the standard reduction potential, more is the tendency of an element to undergo reduction, more the tendency of an element to undergo reduction, better the oxidizing agent, better the oxidizing agent, more the oxidizing power, more the oxidizing power. Do remember this particular statement as well. Do remember this particular statement as well, right? More the SRP, more the standard reduction potential, more the tendency to undergo reduction, better oxidizing agent, more oxidizing power, right? Right, people? Is it clear? Is it clear, people? Quickly in the chats. Perfectly done. Perfectly well. Let's try to understand where these two statements are utilized. Okay, let's try to understand that. Okay, one simple and basic question. Simple and basic question. If I ask you people, see, you are given with certain values, or leave the values aside. Let me give you one more question. Just a second. Let me give you one simple question so that you can understand it properly. So that just to make you understand, okay? For example, I'm writing certain elements, X, Y, and Z. These are few elements which I have. And over here, I'm writing certain values. E naught of M gives Mn positive. Tell me in the chats whether it is SOP or SRP. Tell me in the chats quickly. E naught of M gives Mn positive, whether it's SOP or SRP. Quickly. SOP or SRP. 0 to plus N, increase in the oxidation state means oxidation. That means this is SOP. Let's say this value is 1.1 volt, this is 2.1 volt, this is 3.1 volt. So you are given with SOP values, right? Now, which one has got more SOP? This is the maximum SOP. More the SOP, more the tendency to undergo oxidation, better the reducing agent. So this is the better reducing agent. The one which is the better reducing agent will have more reducing power. Done and dusted, right? Okay. For example, I'm writing something like this. E naught of M gives Mn positive. Let's say it is minus 1.1 volt, it is minus 2.1 volt, it is minus 3.1 volt, right? Now again, you're given with SOPs only. Which one is maximum SOP among all? This is maximum SOP. More the SOP, more the tendency to undergo oxidation, better the reducing agent. So this is the better reducing agent. It has more reducing power now. Okay. Now, for example, I'm writing something like this. E naught of Mn positive gives M. So plus N to 0. Plus N to 0. Decrease. Decrease means reduction. Reduction means SRP. This is SRP now. Let's say this is 1.1 volt. This is 2.1 volt. This is 3.1 volt. So which one has got more SRP now? This is the more SRP value. More SRP. More SRP means more tendency to undergo reduction. More SRP, more tendency to undergo reduction. Better oxidizing agent. So better oxidizing agent, more oxidizing power. Okay. Similarly, for example, I'm writing something like this. E naught of Mn positive gives M. This is minus 1.1 volt. This is minus 2.1 volt. This is minus 3.1 volt. Now check it out. Check it out. Which value? First of all, this is SRP again. And this is the maximum SRP here. Maximum SRP means maximum tendency to undergo reduction. Better oxidizing agent. More oxidizing power. Is this clear to everyone? Is this clear to everyone, people? Quickly. Quickly, let me know in the chats. Try to solve this question. I'm giving you 1 minute of time. Give it a try. Give it a try, people. Give it a try. Everyone. What do you think is the correct answer of this question? हाँ समीर, मुझे पानी की एक बॉटल चाहिए. हेलो. हाँ जी. ओके ओके ब्रो. ओके. People are saying option D. Is it? People are going with option D. Let's get to know. What do we have to check? Strongest reducing agent. Strongest reducing agent. So we have to check the strongest reducing agent. Reducing agent is the one which undergo oxidation. Reducing agent is the one which undergo oxidization. We have to check strongest reducing agent. So strongest reducing agent will be the one which will undergo oxidation easily. Now, which will undergo oxidation easily? The one which will be having maximum SOP. The one which will be having maximum SOP will undergo oxidation easily. That will be the better reducing agent. That will be the strongest reducing agent. Now check which one of the following has got maximum SOP. Guys, I want you to understand one thing over here. In all these reactions, electrons are gained. Let's say in the first reaction, electron is gained by Mg dye positive. Mg dye positive is gaining electrons. So Mg dye positive here is undergoing reduction. So this is the standard reduction potential value which is given to us, right? It's not mentioned whether it's SOP or SRP. Look at the reaction carefully. In the reaction, gain of electrons is happening. Gain of electron involves means reduction. So this is standard reduction potential of Mg dye positive when getting converted into Mg. Similarly, standard reduction potential of zinc dye positive when getting converted into zinc, minus 0.76, right? Similarly, these are the SRP values basically. These are the SRP values of Mg dye positive, zinc dye positive, nickel dye positive, and Fe tri positive respectively, right? These are the SRP values, okay? Now, do I have to check on the basis of SRP or SOP? I will have to check on the basis of SOP values. My dear students, if I reverse the reaction, if I reverse the first reaction, for example, if I reverse the first reaction, it becomes like this. Mg gives Mg dye positive plus 2 electrons. Now its E0 value, its sign would have got changed. Now it is 2.37 volts. What should I be calling this value now as? Is this reaction reduction or oxidation? This is the oxidation reaction. Which is undergoing oxidation? Magnesium is undergoing oxidation here. Magnesium is losing electrons, right? So this is the SOP of magnesium. SOP of magnesium. This value was SRP of Mg dye positive. This value was SRP because Mg dye positive was undergoing reduction. So this value was SRP of Mg dye positive. But this value is going to be the SOP of Mg because Mg is undergoing oxidation. Mg dye positive is undergoing reduction, but Mg is undergoing oxidation. So this is the SRP of Mg dye positive, which is undergoing reduction, but this is SOP of Mg, right? Now check. If you reverse the sign everywhere, where do you see the maximum SOP value? Maximum SOP value on reversing the sign will be the first one. And that is the maximum SOP of what? That is the SOP of what? That is the SOP of magnesium, right? So more the SOP, more the tendency to undergo oxidation, better reducing agent. So the answer is going to be magnesium. Is this clear to everyone? Is this clear to everyone? Quickly, people, quickly. What do you think about this one? What do you think about this one? This particular question, quickly. It's again one simple question, people. See, in every reaction, as you see all the reactions, in every reactions, electrons are gained. And you know, gain of electrons is called as a reduction. Gain of electrons is called as a reduction. Guys, just give me a second. Just give me a second. Thank you. Okay. In the first one, gain of electrons is happening. Gain of electron is what we call as a reduction. So CO tri positive is gaining electron. So CO tri positive is undergoing reduction. So this is SRP of CO tri positive. This is SRP of Ce plus 4. This is SRP of Pb plus 4. This is SRP of Bi tri positive. So we have SRP values, right? Now, if you reverse the first reaction, for example, if you reverse the, okay, Don't reverse the reaction. Tell me one thing. What do we have to check? The oxidizing power of order. The oxidizing power order. Tell me people one thing. I told you a few minutes back only. The one which is the better oxidizing agent. The one which is the better oxidizing agent will always have more oxidizing power. And the oxidizing agent always undergoes reduction. Right? So the one which undergoes reduction easily, will be the better oxidizing agent, will have more oxidizing power. Now, which one will undergo a reduction easily? The one which will be having more SRP. More the SRP, more the tendency of an element to undergo reduction, better oxidizing agent, more oxidizing power. Now, what do you think should be the answer of this question? These are all the SRPs of the substances which are undergoing reduction. In the first reaction, cobalt tripositive is undergoing reduction. So this is SRP of cobalt tripositive getting converted into cobalt dipositive, right? Now, where do you see, since we got to know these are SRP values, right? So where do you see SRP value maximum? Which one is the maximum SRP? 1.81. This is the SRP of what? This is the SRP of cobalt tripositive, right? After that, 1.67. This is the SRP of PV plus 4, right? After 1.67, 1.61. This is the SRP of Ce plus 4. And then at the end, it's going to be Bi tripositive, right? So this is the order of SRP values. These are the SRPs basically, right? More the SRP, more the tendency to undergo reduction, better oxidizing agent, more oxidizing power. So what should be the answer? CO tripositive will have maximum. CO tripositive will have maximum, followed by PB plus 4, followed by, so it has to be option B, right? I hope you can solve these sort of questions from now onwards. Clear, people? Is it clear to everyone? What do you think about this one? The reducing power. Reducing power. Reducing power. The one which will be having more reducing power will be always a better reducing agent. And the reducing agent is the one which undergoes oxidation. So the one which undergoes oxidation easily will be better reducing agent, more reducing power. Now, which one has got more tendency to undergo oxidation? The one whose SOP will be more. The one whose SOP will be more will be undergoing oxidation easily. Better reducing agent, more reducing power. Now, which one among the following will undergo oxidation easily? First of all, check one simple thing. In all the reactions, electrons are gained. Gain of electrons is reduction. So these are basically the SRPs. This is the standard reduction potential of what? Of the substance which is undergoing reduction. Zinc dipositive is gaining electrons. So zinc dipositive is undergoing reduction. So this is E naught of zinc dipositive gives zinc. This is E naught of calcium dipositive gives calcium. This is E naught of Mg dipositive gives Mg. This is E naught of Ni dipositive gives Ni. Right? Now tell me one thing. Since these are the standard reduction potentials, but I have to solve the question in terms of SOP. So reverse the sign. This will be plus, this will be plus, this will be plus, this will be plus. Now this plus 0.76, plus 0.76, is it going to be SOP or SRP? Initially it was SRP, now it is going to be SOP. SOP of what? Of the substance which undergoes oxidation. It is going to be SOP of zinc. This is going to be SOP of calcium. This is going to be SOP of this. This is going to be SOP of nickel. Simple. Right? Okay. Initially, we were given SRP of the ions. Now we got the SOP of these metals, right? Initially, we were given SRP of ions. Now we got SOP of the metals. Now check which one has got more SOP. It is calcium, I believe, right? Calcium has got maximum SOP, followed by magnesium, followed by zinc, followed by nickel, right? This is the SOP order. More the SOP, more the tendency to undergo oxidation, better reducing agent, more reducing power. So which answer should be the correct one? So calcium has got maximum, followed by magnesium, followed by zinc, followed by nickel. So it has to be option B again. I hope all these things are clear. If all these things are clear, let me know once in the chats quickly. Yeah? Perfectly done, guys. I hope you can solve all the questions based on electrode potential. Yeah? I believe that. Perfect, people. Now, let's get into one more topic, that's EMF. Have you studied this topic before? I'm just asking you. Let me know in the chats quickly. Have you studied this topic before? EMF. Quickly, guys. Yeah? All right. So let's get going then. Let's get started with the topic EMF. What EMF exactly is all about? How do you define the term EMF? It's a simple topic again, right? See, guys. First of all, if you talk about EMF, it is basically, EMF is the maximum potential difference between the electrodes. Between the electrodes means between anode and cathode, right? I hope you remember your galvanic cell, in which we used to have two electrodes, right? Two electrodes, connect them externally and internally. We used to get a complete cell, right? Now, let me tell you the maximum potential difference between anode and cathode. When no current is drawn from the cell. Or you'll directly say when the cell is not in use. When the cell is not in use, you call that maximum potential difference between the electrodes as EMF. So imagine that. I hope you remember your galvanic cell. In case of your, I hope you remember your Daniel cell. In case of your Daniel cell, you used to have zinc electrode on one side. You used to have copper electrode on one more side, right? And here, you used to connect an emitter, and here a salt bridge, right? What this Daniel cell used to do? Daniel cell, it is a typical example of the galvanic cell. It converts chemical energy into electrical energy, right? Basically, this Daniel cell, it produces current. Now, since this Daniel cell produces current, you already know current direction in the Daniel cell, it is from cathode to anode. This is the direction of current. And since the Daniel cell is producing current, right? Current is produced due to potential difference. Can I say this cell will only produce current if there will be potential difference between these two electrodes? Right? This cell will only produce current if there will be potential difference between these two electrodes. Correct? The maximum potential difference between these electrodes, between cathode and anode, when the cell is not in use, when no current is drawn from the cell, right? That's something which you call as EMF. Now you must be thinking how it's calculated, how it's done, right? Let me tell you, EMF is calculated with the help of potentiometer. It is calculated with the help of potentiometer. Now guys, what I'm going to teach you now, that's important. Try to understand what exactly I'm going to say. Okay? Try to understand. For example, imagine this is zinc sulfate in this container. And here you have got copper sulfate. This is something important, guys. Try to understand this properly. Right? Copper sulfate. And here you are keeping a zinc rod. And here you are keeping a copper rod. One is zinc rod and one is copper rod. Okay? This is your zinc rod and this is your copper rod. You're connecting them with the help of emitter, for example, right? And what this emitter will do, it will show deflection maybe, right? And when it shows deflection, that means the cell produces current. If it is not showing any deflection, that means the cell is not producing any current. And when the cell produces current, when the emitter shows deflection, that means the cell is producing current. Current is produced due to potential difference between the electrodes. That means at that time there will be potential difference between the electrodes. Now, over here, I'm using a salt bridge as well. The circuit is complete. Now, my dear students, try to understand what exactly I'm going to say. Try to understand what exactly I'm going to say. I told you EMF is measured with the help of potentiometer. How exactly? From here, you'll get the exact feel of what EMF is all about. Before that, let me tell you one thing. EMF, when measured under standard conditions, and you know what standard conditions are. When EMF is measured under standard conditions, you do not call it as the EMF of the cell. You call it as the standard EMF of the cell. So there's a difference between E cell and E naught cell. What is E cell? E cell is simply the maximum potential difference between anode and cathode. What is E naught cell? It is the maximum potential difference under standard conditions between the anode and cathode. Now try to understand. Try to understand, people. I'm assuming this particular cell is kept under standard conditions. Right? It is kept under standard conditions. Okay? Now guys, understand what exactly I'm going to say. This particular zinc rod, as you know, this zinc rod, it gets the negative charge, something discussed already, and this cathode, it gets the positive charge, right? Now people, what we are planning to do, we are planning to use an external battery. This is the external battery which I'm going to take. Positive terminal of the external battery, negative terminal of the external battery. This is the external battery which I've taken over here. This is the external battery which I've taken over here. Okay. And this external battery, my dear students, I'm going to connect this external battery with this Daniel cell over here. Okay. See, the positive terminal of the external battery is connected to the negatively charged rod. It is connected with the negatively charged rod, and the positively charged rod is connected to the negatively charged terminal. Okay, I hope you're understanding what exactly I'm doing. I connected the external battery in reverse polarity over here. Positively charged with the negatively charged rod. Negatively charged with the positively charged rod. That's what I'm doing, right? My dear students, this external battery which you are using, it will be definitely having some voltage, right? It will have some voltage. Perfect. Even there will be potential difference between these two electrodes as well. These two electrodes, there will be potential difference. Correct? Now tell me one thing. Tell me, imagine and understand. If by chance the external battery, right? If by chance the voltage of external battery is 0 volts. If the voltage of external battery is 0 volts, will anything happen to the potential difference between the electrodes? I'll say the potential difference between the electrodes I'm representing with E cell, for example. If external voltage is 0, it is not going to affect this particular Daniel cell, right? The Daniel cell will be normally working in which oxidation takes place at anode, reduction takes place at cathode, electrons will move from anode to cathode, current will move from cathode to anode, right? Now try to understand. If by chance external voltage is equal to what? Is equal to EMF of the cell. If external voltage is equal to the EMF of the cell. So first of all, try to understand what I'm going to say. Since between these two electrodes, there will be potential difference, right? Now, initially, the external voltage given was 0. Now, imagine slowly you are increasing the external voltage. Slowly you are increasing the external voltage. Imagine that. External voltage, slowly you are increasing. Let me tell you, E naught cell. That means the potential difference between these two rods, that is experimentally observed, it is 1.1 volt. Experimentally, it's observed that maximum potential difference between these two electrodes under standard conditions, that is 1.1 volt. So initially, the external voltage was 0. Now slowly you are increasing the external voltage. Slowly you are increasing the external voltage. Slowly you are increasing the external voltage. Can I say there will be a time? There will be a time when external voltage will become equal to E naught cell. And my dear students, since this particular battery, it is connected with reverse polarity. It is connected with reverse polarity. Now imagine if external voltage becomes equal to E naught cell. At that point of time, will this particular cell produce any current? Say yes or no. Will it produce any current at that time? Will it produce any current at that time? Understand it properly. Since external battery, you are connected with reverse polarity, positive with negative, negative with positive. Initially, there was no external voltage. There was no external voltage. The cell was working like a normal galvanic cell. Now, slowly you started increasing this external voltage. And slowly you started increasing the external voltage. Initially, in absence of external voltage, this emitter was showing maximum deflection. This emitter initially was showing maximum deflection when there was zero external voltage. Now, slowly when you start increasing external voltage, the deflection in the emitter will decrease. The deflection in the emitter will keep on decreasing. As the external voltage will keep on increasing, the deflection in the emitter will keep on decreasing. And there will be a point. There will be an external voltage at which there will be no deflection in emitter. There will be an external voltage at which there will be no deflection in emitter. And that external voltage at which there is no deflection in emitter, that is 1.1 volt in case of Daniell cell. Right? Now, since external voltage and E cell have become equalized and both are reversely polarized, right? Polarity is reverse. So at this particular point of time, there'll be no current in the cell. At that point of time, there is no current in the cell. Perfect. Right, people? So if you ask me how this 1.1 volt was calculated, 1.1 volt was basically the voltage which was used here. So initially you did not know what was E0 cell. What you kept on doing, you kept on increasing the voltage of external battery. And there was one voltage, which was 1.1 volt, at which cell stopped working. Right? And that external voltage has to be equal to the E0 cell basically. Yeah? I hope this particular point is clear. So what is E0? What is E cell basically? It is the maximum potential difference between the electrodes when the cell is not in use, when no current is drawn from the cell. I hope this particular point is clear. Okay. Now, the actual stuff which we have to understand here, which we have to remember. The actual stuff which we have to remember. Let's try to understand that. Let's try to understand that. How do you exactly calculate this? How do you exactly calculate this E0 cell? That's important. My dear students, there is one simple way of calculating this E0 cell. How? E0 cell is calculated as E0 of cathode minus E0 of anode. This is one way of calculating the E0 cell. E0 of cathode minus E0 of anode. What is E0 of cathode and what is E0 of anode? E0 of cathode is basically standard reduction potential of cathode, and this is your standard reduction potential of anode. Right? This is the generalized result which I would want all of you to remember. E0 cathode will be equal to E0 cell will be equal to E0 of cathode minus E0 of anode. What is E0 of cathode? This is SRP of cathode. This is SRP of anode. Well, you can convert them into SOP values as well, right? You just need to write one thing. Instead of SRP of cathode, you have to write minus times SOP of cathode, right? Instead of SRP of anode, you have to write minus times SOP of anode. You'll get one more formula. No need to remember a lot of formulas, just remember this particular one. So this is one general result of calculating E0 cell, which is E0 of cathode minus E0 of anode. Now, people, where do I use this equation? That's important. Try to understand one simple thing. Imagine I've got two electrodes, A and B. Imagine I've got two electrodes, A and B. Okay, imagine. I'm writing the value E0 of A positive gives A is equal to 1.1 volt. E0 of B positive gives B. It is equal to 2.1 volt. Imagine I'm writing something like this. How many electrodes I have? Two. One is your A, one is B. Now tell me one thing, since I've got two electrodes, my dear students, understand. If I connect them externally as well as internally, if I connect two electrodes externally as well as internally, can I say I will be getting one galvanic cell? I'll be getting an electrochemical cell, right? Yeah? Just give me a second, guys. Guys, just a second now. Okay. Try to understand what exactly I'm going to say. I took two electrodes A and B. I am connecting these electrodes externally and internally. You know, externally we connect them with the help of ammeter, internally we connect them with the help of salt bridge. Now, my dear students, we got a cell. We got a complete cell, which is made up of two electrodes. Now, I'm asking you, what will be the standard EMF of that particular cell? I'm asking you, what will be the standard EMF of that particular cell? First of all, try to understand which value this is. It is SOP or SRP. What do you think? Is it SOP or SRP? Plus 1 to 0, decrease, reduction, this SRP. This plus 1 to 0, decrease, this reduction, SRP. So both are SRP values. Now, which SRP's value is more? This SRP is more. More the SRP, more the tendency to undergo reduction. And reduction takes place at cathode. So this electrode will be behaving like the cathode, and this electrode will be behaving like the anode. So first of all, you'll try to identify which is your anode and which is your cathode. You identified the cathode and anode. Now, after identifying the cathode and anode, it's the time to calculate E naught cell, which is E naught of cathode minus E naught of anode. SRP of cathode minus SRP of anode. What is SRP of cathode? SRP of cathode is 2.1 volt. SRP of anode is 1.1 volt. The value will be exactly 1 volt. Done and dusted, right? So what this 1 volt is? This 1 volt is basically going to be your E naught cell. That's it. Right? Perfect. If this is clear, let me take a few more examples. Let's say, people, I'm writing something like this, and you need to answer me this, okay? For example, you have got the electrode like this. I'm writing E naught of A positive gives A. This is 3.1 volt. I'm writing E naught of B gives B positive. It is equal to 5.1 volt. So I've got two electrodes basically. I've got two electrodes. I'm connecting them externally as well as internally. And you know, when we connect these electrodes externally as well as internally, do we get one complete cell? Absolutely, we get one complete cell, which is made up of two electrodes. Nowadays, students, how do we calculate E naught cell of the cell which is made by connecting these two? How do we calculate E naught cell? First of all, which potential this is? SRP, plus 1 to 0. Which potential this is? 0 to plus 1. SOP. One is SRP, one is SOP. So if this is SOP, so what has to be SRP then? SRP will be minus 5.1 volt. Right? Now compare these SRP values. Compare these SRP values. Which SRP is more? 3.1 or minus 5.1? 3.1. The one which will be having more SRP will undergo reduction, and reduction takes place at cathode. So this has to be cathode and this has to be anode. So you got to know which one among the two is going to behave like the anode and which one among the two is going to behave like the cathode. So my dear students, it is the time to calculate E naught cell, which is E naught of cathode, SRP of cathode minus SRP of anode. This is the E naught cell value. I hope this is clear. I hope this is clear. There is something wrong with my throat. I don't know. What about this particular question, guys? Give it a try, quickly. Quickly give it a try. Standard oxidation potential of the half cells. So you are given with SOP value. This is SOP value of zinc. Zinc is undergoing oxidation here. Zinc is losing electrons. Here iron is losing electrons. So zinc and iron both are undergoing oxidation. So these are the SOP values of zinc and iron. EMF of this particular cell. EMF of this particular cell. The cell which is given to us is like this. Zinc plus iron dye positive gives zinc dye positive plus iron. Tell me one thing. Here it is 0. Here it is plus 2. Here it is plus 2. And here it is 0. Now tell me, 0 to plus 2, increase or decrease? Increase. Plus 2 to 0, increase or decrease? Decrease. Increase in the oxidation state is something which you call as oxidation. right? So zinc is undergoing oxidation. Oxidation takes place at anode, right? Iron dye positive is undergoing reduction. Reduction takes place at cathode. Perfect. Reduction takes place at cathode. So you understood, you got to know that in this net reaction, your zinc electrode will be behaving like the anode and iron electrode will be behaving like the cathode. So since you identified, calculate E naught cell. E naught cell is going to be E naught of cathode minus E naught of anode, right? Right, people? Yeah? Perfect. So E naught of cathode, which is SRP of cathode. SRP of cathode. Cathode is iron. Is it SRP of SOP? This SOP. What we have to write SRP. So minus 0.41. Minus SRP of anode. This is SOP of anode. But we need SRP. So minus 0.76. Solve it. Get the E naught cell value. Is this clear? Is this clear to everyone, people? Is this clear to everyone? Quickly. Clear? I believe everything is clear to everyone, right? Okay. Now, guys, now comes one more important thing. That is spontaneity and E naught cell. This is again one important topic. Spontaneity and E naught cell. My dear students, imagine and understand. This is something important, okay? Understand it properly. Imagine that you have got one electrode. This one electrode. Imagine you have got one more electrode. This is one more electrode. Simply you are taking two electrodes. You are connecting them with the help of ammeter, with the help of salt bridge. It's a complete cell. What is a complete cell? What is a complete cell? Complete cell is made up of two half cells, two electrodes. Half cell is also called as electrode. A complete cell is made up of two half cells. So imagine you have got two half cells here, right? Which are connected externally as well as internally. So I would say this is a complete cell which is made up of two half cells. No doubt you made a complete cell. You made a complete cell. Now the point is whether this complete cell will be working or not. Whether this complete cell will be generating current or not. Right? That is one more debate. So till now, you can make many complete cells. You can make many galvanic cells, right? You can make many complete cells. Just take two electrodes, connect them externally, connect them internally. You'll be getting a complete cell. Now, whether the complete cell will be working or not, on what parameters that will depend? On what parameters that will depend upon? Whether the complete cell will be working or not, on what factor it will depend upon? Let's try to check that factor on which the complete cell depends upon. Understand, guys. I hope you got the context of what exactly we are going to discuss. We are going to set the parameters. We are going to set the criteria which a cell must follow. Then only we can say the cell is working like a normal galvanic cell. Okay? Right? We are going to set the parameters. We are going to set the parameters which a cell has to follow. Then only I'll say the cell is working like a normal galvanic cell in which electrons will move from anode to cathode, current will flow from cathode to anode. Right? Now try to understand. My dear students, let's say I'm taking a Daniel cell here. Imagine this is the Daniel cell which I'm taking. Try to understand what I'm going to talk. Imagine this is the Daniel cell. Okay, this is one Daniel cell. Over here, there's the zinc electrode, there's the copper electrode. So 2 electrodes connected externally and internally. It's a cell. It's a complete cell. Now, whether this cell will be working or not, we have to discuss that condition only. Tell me one simple thing. If you remember, we have studied in thermodynamics. System always possesses 2 types of energies. This cell is my system right now. It is under observation. It is under investigation. This cell is under investigation right now. It is my system. So this particular system, it will be having 2 types of energies. One is called as available. One is called as unavailable energy. There will be 2 types of energies present in the system. One is available, one is unavailable. My dear students, if you remember, this unavailable energy, it increases the randomness or disorderness of the particles present in the system. This unavailable energy, it increases the disorderness present in the system, right? So whatever is the disorderness of the particles, whatever is the randomness of the particles present in the system, that is on the cost of unavailable energy. So unavailable energy, it tries to increase the randomness, the disorderness present in the system. And that disorderness or randomness, that is measured by the factor called as entropy. I hope you remember. That disorderness is measured by the factor called as entropy. So what is entropy? Entropy is the factor which gives you the measure of unavailable energy present in the system, right? More the unavailable energy, more the randomness, more the disorderness in the system, more the entropy of the system. You know that, right? Now, this available energy is used for what? My dear students, let me tell you, this available energy is converted into useful work. The name of the useful work is also non-PV work. Non-PV work. The example of non-PV work is electrical work. Tell me one thing. Do you see any electrical work happening here? I would say yes. Yeah? Do you see any electrical work happening here? You know, my dear students, in case of this particular cell, your electrons, they move from zinc to copper, right? You know that. You know, electrons move from zinc to copper. That means in case of your Daniel cell, if you remember, this part of the cell, in this part, what is happening basically? Electrons are shifted from anode to cathode in case of your Daniel cell, right? In case of your Daniel cell, the electrons are shifted from anode to cathode. You know that, right? So I would say, is this just the movement of electrons, or it is the movement of electrons in a particular direction? It is the movement of electrons in a particular direction, due to which the cell produces current. You know that. Now, my dear students, tell me one simple thing. So, you know, electrical work is happening here. Since electrons are moving from anode to cathode, you know, electrical work is happening here. Electrical work, that is the example of non-PV work, which is also called as useful work, right? And what is useful work? It is that work which happens on the cost of what? On the cost of available energy. What does that mean? That simply you can understand like this. See, I can say the electron has to go from zinc to copper. Okay. Now, electron on its own won't go from zinc to copper. I'll say system will utilize some of its energy. System will consume some of its energy to send electron from anode to cathode, to send electron from zinc to copper, right? This particular system, this particular cell, it is going to convert, it is going to consume some of its energy. It is going to utilize some of its energy. Then only it will send electron from anode to cathode. For example, I'm walking on the cost of my energy. I'm consuming my energy, then I'm walking. Similarly, the electron is going from anode to cathode. So the system, the cell will be consuming its energy. The cell will be consuming its energy, right? And that energy consumed by the cell will be utilized to send electrons from anode to cathode. Now, which type of energy the cell utilizes in order to do the electrical work, in order to do the useful work? It is the available energy which the cell consumes. It is the available energy which the cell consumes to do what? To do the useful work, to do the non-PV work, to do the electrical work, to send the electron from anode to cathode, right? So imagine in the beginning there was 80 joules of available energy in the system. Imagine there were 80 joules of available energy present in the system initially. After some time, you observed that only 60 joules of available energy is left in the system. So what has happened? Has the available energy increased or decreased? The available energy of the system has decreased by how much unit? By 20 units. The available energy has decreased by 20 joules. My dear students, the available energy of the system, the available energy of the cell is decreasing by 20 units. What does that mean? Can I say those 20 joules of energy has been utilized in order to perform the electrical work? Right? Those 20 joules have been utilized to perform what? To perform electrical work. So can I write a simple statement? Decrease in the available energy, decrease in the available energy is equal to the what? Useful work. And which kind of useful work is happening here? It is the electrical work. It is the electrical work which is happening. Okay? Right, people? I hope this particular statement is clear to everyone. If this is clear to everyone, let's try to understand one simple thing. My dear students, I'm writing minus delta G as such is equal to electrical work. How do you calculate electrical work? It is charge multiplied by potential difference. Charge multiplied by potential difference. Right? Now, I can write something like this. Minus delta G is equal to. See, the charge on one electron is how much? Minus 1.6. The magnitude of charge on electron is 1.6 into 10 raised by minus 19 coulomb. Right? My dear students, the charge present on 1 mole of electrons is equal to 96500 coulombs. And this 96500 coulombs is something which you call as farad. So 1 farad is basically equal to 96500 coulombs. Imagine that if 1 mole of electron is moving from anode to cathode. Imagine if 1 mole of electron moves from anode to cathode, how much charge is transferred from anode to cathode? Imagine. When 1 mole of electron moves from anode to cathode, that means 1 farad charge is transferred from anode to cathode. Now imagine, n moles of electrons are moving from anode to cathode. That means n farad charge is moving from anode to cathode. So if I'm assuming n moles of electrons moving from anode to cathode, that means n farad charge is going from anode to cathode. Multiplied by what? Multiplied by E cell. So my dear students, delta G we got to know as minus NF E cell. This is one very, very, very important result which every one of you are supposed to remember. Yeah? Is it clear? Delta G is equal to minus NF E cell. Why did we derive this result? What was the importance of it? Why do we need this? There's a logic for that as well. My dear students, just remember thermodynamics. For the process to be spontaneous, for any process to be spontaneous, delta G for the system at constant pressure and temperature, that has to be negative. Then only we say the process is spontaneous, right? Okay. Right, people? For any process to be spontaneous, delta G for the system at constant pressure and temperature, that has to be negative. You know that. Now imagine you have got 2 electrodes. You are connecting them externally as well as internally. You got one complete cell. Now for the cell to be working, for the cell to produce current, what should happen? Once you complete the circuit, once you introduce a salt bridge, automatically at anode oxidation should start. At cathode, reduction should start. And once oxidation reduction takes place spontaneously, then you will directly say electrons will move from anode to cathode. Current will move from cathode to anode, right? So for a complete cell to be working, like a normal galvanic cell, I'm writing it over here. For a cell to be working like a normal galvanic cell, in which current will be from cathode to anode, right? For the cell to be working like a normal galvanic cell, once you make the cell, once you complete the cell, once you take two electrodes, connect them externally, internally, if automatically at anode oxidation takes place, at cathode reduction takes place, electrons will automatically move from anode to cathode. Current will move from cathode to anode, right? So for the cell to be working like a normal galvanic cell, the cell reactions in the cell should be spontaneous. And the cell reactions in the cell will be only spontaneous if delta G reaction will be negative. Delta G has to be negative. Delta G for the reactions have to be negative. Delta G negative means minus NFE cell. It has to be negative. Delta G negative means minus NFE cell has to be negative. So what does that mean? When is this whole term negative? This whole term is only negative if E cell is positive. If E cell is positive. So I would say for the cell to be working like a normal galvanic cell, delta G for the reactions have to be negative. Or you can say E cell has to be positive. This is the condition, my dear students, this is the condition which a cell should follow. Then only you can say the cell is working like a normal galvanic cell in which electrons are moving from anode to cathode and current is moving from cathode to anode, right? Yes? I believe it's clear. I believe it's clear. Point number one. Point number two. If by chance delta G for the reactions is equal to 0, what does it indicate? It indicates E cell is equal to 0. E cell is equal to 0. And this particular condition is called as equilibrium state, equilibrium condition in the cell. What is equilibrium condition? This is something which I have not discussed yet. I'll be discussing this in the next session, not now. Not now, okay? And my dear students, one more thing. If by chance delta G for the cell comes out to be positive, or you'll say E cell is negative, the cell reactions will be non-spontaneous. The cell reactions will be non-spontaneous. And if the cell reactions are non-spontaneous, cell won't work like a normal galvanic cell. Cell won't work like a normal galvanic cell, right? Perfect. These are the three conditions which you guys need to remember. So for any cell to be working like a normal galvanic cell, its cell reactions should happen on its own. They should be spontaneous. So for that purpose, delta G for the reaction should be negative, or E cell should be positive. Right? Perfect. My dear students, one more thing. If I write the same equation under standard conditions, it becomes delta G naught is equal to minus NF E naught cell. Right? This is one more equation which is valid under standard conditions. Sometimes they ask you calculate the standard Gibbs free energy of the cell, delta G naught. Delta G naught is equal to minus NF E naught cell. That's it. That's the difference. Okay? So, let me quickly summarize all these things. What did I say? I said one simple thing. For example, you are getting two electrodes. You are connecting them externally, you are connecting them internally. You are getting a complete cell. Now, whether this complete cell will be working or not, whether this complete cell will generate current or not, whether this complete cell will behave like a normal galvanic cell or not, once you make this cell, if reactions at anode and cathode are happening on its own, that means the cell will work, right? And if the reactions at anode and cathode are not happening on its own, the cell will not work like a normal galvanic cell. I hope this is clear to everyone. Okay? I hope this is clear to everyone. Okay? And for the cell reactions to happen on its own, its delta G for the reaction has to be negative. Delta G negative means E cell has to be positive. Then only delta G will be negative. Okay? My dear students, on this particular concept, there is one more thing. There is one more thing. If you would have studied thermodynamics, I would have told you Gibbs free energy, it is an extensive property, and EMF is an intensive property. Gibbs free energy is an extensive property and EMF is an intensive property. And I have told you, if you remember, I have told you in thermodynamics, we cannot add or subtract intensive properties directly. Extensive properties can be added or subtracted directly, but intensive properties cannot be added or subtracted directly. Right? Okay, intensive, we cannot add or subtract the intensive properties like E cell. Like E cell. E cell is the intensive property. You cannot add these intensive properties directly. Right? Whereas you can add or subtract extensive properties. For example, there is one question which is frequently asked from this. Let's say you have got something like this. Understand. Fe tri positive plus 3 electrons. It gives Fe solid. Fe di positive plus 2 electrons gives Fe solid. Fe tri positive plus 1 electron gives Fe di positive. E1 value is 1 volt. E2 value is 2 volts. You are supposed to calculate E3 value. How do you solve these sort of questions? You would have seen these sort of questions, right? I believe you would have seen these sort of questions. I believe you would have seen these sort of questions. My dear students, how do we solve these sort of questions? Understand. First of all, let me tell you, let me call this as reaction number 1. Let me call this as 2. Let me call this as 3. Right? I'm supposed to calculate E value for this particular reaction. I'm supposed to calculate E value for this particular reaction. Just remember one thing. The reaction whose E is to be calculated, you are supposed to make that reaction out of the given reactions. The reaction whose E value is to be calculated, you are supposed to make that reaction out of the E values, out of the given reactions. Now, how do you make this particular reaction? My dear students, third reaction is made when you subtract second from first. Third reaction is made when you subtract second from first. If you subtract second from first, so this will be 3 electrons minus 2 electrons, gives 1 electron. Fe solid, 0, nothing. So Fe tri positive minus Fe di positive, that minus Fe di positive comes to the right side. So this becomes the reaction. So third reaction we got when these two are subtracted. Now, if you are thinking that on subtracting these two, you are getting third. If you are thinking you'll do the same algorithm with their E values, if you are thinking you'll write something like this, E3 is equal to E1 minus E2, it is absolutely wrong. There will be option. There will be option like this as well. But this is wrong. Why? Because I told you your EMF, your electrode potentials, they are intensive properties. They cannot be added or subtracted directly. So my dear students, if your electrode potential EMF, if they are intensive properties, if they are not added or subtracted directly, that means you'll be solving this particular question with the help of delta G value. Instead of 3, you'll write delta G3 is equal to, instead of 1, you'll write delta G1, minus instead of 2, you'll write delta G2. Okay. Now you already know delta G3, what that is. Delta G3, it is minus N3 FE3 is equal delta G1 minus N1 FE1 minus delta G2, it is minus N2 FE2. Correct? F everywhere cancelled. If you multiply throughout by minus sign, at the end you'll be getting something like this. E3 is equal to N1 E1. E3 is equal to N1 E1 minus N2 E2 divided by what? Divided by N3. Now, E1, E2 are given to us as per the question, right? E1, E2 are given to us as per the question. Now, tell me, what is N1, N2, N3? How many electrons are exchanged in the first reaction? 3. So, N1 value is 3. In the second reaction, 2 electrons are exchanged. N2 value is 2. In the third reaction, 1 electron is exchanged. So, N3 value is 1. So, E1, E2, N1, N2, N3, everything is given. Put it here and get the E value, right? So, my dear students, one thing you need to remember. which you are going to remember directly from now onwards. The reaction whose E value is to be calculated, you are supposed to make that reaction out of the given reactions. Point number one. Point number two. Your electrode potential EMF, they are intensive properties. They cannot be added or subtracted directly. Whereas your delta G, that's extensive property. You can add or subtract that directly. That's why this particular sort of question is solved in terms of delta G, not in terms of E. Yeah? Is it clear to everyone? Quickly in the chats. Is it clear to everyone, people? Quickly. Let me know quickly in the chats if it is super clear to everyone. Can you give it a try? Can you give it a try? 3 reactions I've already given. The E values I've given. The 4th reaction, its E value has to be calculated. I told you one simple thing. The one whose E is to be calculated, you're supposed to make that reaction. Now you must be thinking how to make this reaction. For that purpose, you should complete these reactions. Tell me one thing. Oxidation state of manganese here is +7. +7 to +6. The change is 1. +7 to +6. Decrease in the oxidation state. Reduction. So MnO4 negative will be gaining 1 electron. Then only it will be getting converted into MnO4 dinegative. Tell me the oxidation state of manganese here. It is +6. Here it is +4. So +6 to +4. Decrease in the oxidation state. A reduction. Gain of electrons. How many? 2 electrons. Right? This is +4 to +2. Decrease in the oxidation state. Reduction. Gain of electrons. How many? 2 electrons. This is +7 to +2. Decrease. Decrease means reduction. Gain of 5 electrons. Now I believe you can. I have completed the reactions. After completing the reactions, the reaction whose E value is to be calculated, you are supposed to make that reaction. Now, how can you make the 4th reaction? I would say 4th reaction can be made when 1st, 2nd, and 3rd will be added. Because this term will get cancelled out. This term will get cancelled out. 2 + 2 + 1 makes it 5 electrons. So MnO4 negative plus 5 electrons gives Mn di positive. MnO4 negative plus 5 electrons gives Mn di positive. So 4th reaction you are making when you are adding first 3 reactions. Right? Now, are you going to do the same algorithm with their E values? Are you going to write E4 is equal to E1 plus E2 plus E3? No way. You are going to solve this question in terms of delta G. So my dear students, delta G for the 4th is equal delta G for the first reaction is equal delta G1 plus delta G2 plus delta G3. Now you know delta G4 is equal to minus NF E4 is equal to minus N1 F E1 minus N2 F E2 minus N2 F E3. Right? Multiply throughout with minus sign. And F everywhere gets cancelled out. So from here you can calculate E4, which has to be equal to N1 E1 plus N2 E2 plus N3 E3 divided by what? Divided by N4. E1, E2, E3 are given as per question. Now N1 is 1, N2 is 2, N3 is 3. Sorry, N3 is 2 and N4 is 5. N1, N2, N3, N4, everything is given. So easily, my dear students, you can calculate E4 value from here. Right? I gave you the random values. I did not give you the exact values. This 1, 2, 3, 4, I'm giving you on my own. Right? These are not the exact values. Perfectly done? Perfectly done, guys? Yes? Is it perfectly done? Now, people, till now, I told you how to calculate E naught cell. how to calculate standard EMF of the cell, how to calculate maximum potential difference between the electrodes when the cell is not in use under standard conditions, right? Under standard conditions. That's something which I told you. How do we calculate standard EMF of the cell? But by chance, imagine you have got a cell which is made up of 2 electrodes. But imagine the conditions are not standard. The conditions are something different. Imagine the concentration of electrolyte is different. Imagine temperature is changed. Imagine pressure is changed, right? That means conditions are different. If conditions are different at that point of time, if I ask you, calculate the maximum potential difference between the electrodes, that means I'm not asking you to calculate the standard EMF. I'm asking you to calculate the normal EMF. So these are 2 things. One is standard, one is normal. Standard is E0, normal is E0. Sorry, normal is E. Normal is E, standard is E0. Right? Difference? One is measured under standard conditions. One is simple, the maximum potential difference under normal conditions. Okay? Now, understand properly what I'm going to say. I'm going to give you one equation here. The most important topic of the chapter. The most, I would say. Nernst equation. Right? Nernst equation. People, this Nernst equation, it has got many uses. But right now, I'm not going to tell you about the uses. Let's first of all derive this equation. Let's see from where the equation comes exactly. There is one equation which I would say everyone would have studied in thermodynamics. Delta G is equal to delta G naught plus RT ln of QC. Have you studied this? You should have, I believe. Now, what is this delta G? It is equal to minus NF E cell. What is delta G naught? Minus NF E naught cell. Right? Plus RT, it is a ln of QC. If I multiply throughout by minus and divide with NF, what do I get? I'll get E cell is equal to E naught cell minus RT divided by NF. It is a ln of QC. Correct? I can write this equation in this format as well. E cell is equal to E naught cell minus. This is ln converted into log. It is 2.303 RT divided by NF and its log of QC. This is something which is what you call as Nernst equation. Why did we write this particular equation? My dear students, be careful with these terminologies. E cell is what you call as EMF of the cell under non-standard conditions. Under non-standard conditions. This is standard EMF of the cell. Standard EMF of the cell, which is equal to E0 cathode minus E0 anode. This N, what is N? Number of moles of electrons exchanged in the net cell reaction. Number of moles of electrons exchanged in the net cell reaction. What is F? F is Faraday's constant, whose value is 96500 coulomb. R value is 8.314 joules per Kelvin per mole, right? And T stands for temperature and QC stands for reaction quotient. QC stands for reaction quotient. This equation is what we call as Nernst equation. Now, dear students, this particular equation you won't be using in the questions. In the questions, I'll be giving you one simplified version of this. Imagine you are putting the value of R as 8.314 joules per Kelvin per mole. Imagine you are keeping the Faraday's constant as 96500 coulombs. Imagine temperature is taken as 298 Kelvin. Let's say all these 3 parameters you put into this equation. After putting in this equation, what do we get? E cell is equal to E naught cell minus 0.0591 divided by N, and then it's going to be log of QC. This is the equation which I will be using in majority of the questions, guys. This is the equation which I'll be using in majority of the questions, right? And this equation is basically valid when temperature of the cell is kept as 25 degrees centigrade, 298 Kelvin. Okay? So this particular equation, it has got many uses basically, right? We use this particular equation to calculate a lot of things, to calculate EMF of the cell, to calculate oxidation potential of the electrode, reduction potential of the electrode, pH of the cell, etc., etc. A lot of things are, I mean, A lot of things are calculated with the help of this particular equation or this particular equation. And how do we calculate them, right? What are its applications, to be more precise? That's something which I'll be teaching you in the next session, because my throat has stopped talking. The application of Nernst equation, where the Nernst equation is used, how it's used, that's something which I'll be discussing in the next session, okay? All the things, whatever I've taught you today, is every single thing clear, guys? Is every single thing clear? I'll let you know the schedule, when the next session will be. I'll let you know on the Telegram, okay? On my Telegram. All the things are clear? Perfect then. Do let me know in the comment section if every single thing is absolutely clear to everyone. Okay? And stay tuned to the next session, because next session is going to be very important, in which we shall be discussing the application of Nernst equation. That portion from which majority of the times question is asked. Okay? Well, I thought of completing this chapter in 3 sessions, but I believe it will take 4 sessions now, since I have taken session for only 2 hours today. So it will take 4 sessions. It's okay. No issues. We have already completed some 10 chapters, right? So there was basically a technical glitch. There was a technical glitch. I was live on JE channel, but I was supposed to be live on this particular channel, right? So can you all hear me now? Am I like perfectly audible, visible to you? Like all the things are absolutely clear, right? Just give me some green signal from the chats. Give me some green signal from the chats, people. Quickly, everyone in the chats. Everyone. So basically, today it's going to be the 3rd session of the electrochemistry chapter. And my dear students, today we are going to discuss the most important topic of the chapter. I'll say the most important topic of the chapter. And the name of the topic is going to be Nernst equation. You must have heard about it, right? Guys, it is, again, I'm telling you, it is the most important topic of the chapter, because majority of the times, whenever question is asked from the chapter electrochemistry, majority of the times the question is asked from the Nernst equation itself. And in this particular session, we are going to start the Nernst equation and we are going to complete the Nernst equation at the same time. We'll first of all see what this Nernst equation is, and after that, we'll see all its applications. Okay? So are you all ready for it? Are you all ready for it? Quickly in the chats. Quickly in the chats. Are you all ready for it? Let me know quickly in the chats. Everyone. Yes, exactly. We are meeting after long, right? We are actually meeting after 10 days, I believe. Right? You know, I was basically busy with a lot of stuff. I kept you updated about everything in the Telegram group. Okay? So from now onwards, we are going to have the regular sessions on this particular channel as well. Okay? Perfect, guys. So let's get going then. Let's get started. One thing which I would want to share with you, whatever I'll be mentioning on the screen, whatever I'll be writing on the screen, I would want you guys to take a note of every single thing, because every single thing is going to be really, really very important when it comes to the Nernst equation. Okay? Perfect. So let's get going then. Let's get started. My dear students, if you remember in electrochemistry, what all topics we have discussed till now. First of all, we started with something called as galvanic cell, if you remember, right? We discussed how galvanic cell exactly works, how Daniell cell exactly works. Then I told you how do we represent a galvanic cell. That was the second topic. The third topic was how to write the net cell reactions from a given cell. That was the third topic. Fourth topic was your electrode potential and its significance, right? Fifth topic was how do you calculate the standard EMF of the cell, E0 cell, which used to be E0 of cathode minus E0 of anode. I hope all those things I hope all those things you exactly remember, which we already discussed in the chapter Electrochemistry, right? Okay. Now we will try to understand what exactly I'm going to say. Now we are going to discuss something called as Nernst equation. So let's exactly get to know what this Nernst equation is all about. Okay, let's have a look, people. Let's have a look. Tell me in the chats whether the video clarity is proper. Is the video clarity proper? Say yes or no in the chats. Say yes or no in the chats quickly. Quickly, everyone. Is the video clarity all okay? Let me know quickly, because somebody wrote video clarity should be increased. I think you should increase your video clarity in the settings. Yeah, because on my side, I believe everything is okay. Yes, Sumanthi, you can enroll still. You can still enroll into the batch. No issues. The link is there in the description. Okay. So let's try to get this Nernst equation. My dear students, what this Nernst equation is, I'll be first of all deriving it. If you remember, there was one equation which you all must be knowing from the chapter Thermodynamics. And the equation was delta G is equal to delta G naught plus RT ln of QC. I hope you remember this particular equation, which we have discussed in thermodynamics. If you do not remember it, do remember it from now onwards. Delta G, it is always equal to delta G naught plus RT ln of Q, where Q is the reaction quotient. You know it. Now, my dear students, if I particularly talk about the galvanic cell, for a galvanic cell, in case of the galvanic cell, can you let me know what delta G exactly is all about? We have discussed this in the last session. Delta G for the galvanic cell is equal to minus NFE cell, right? And delta G naught is equal to minus NFE naught cell. These were the things which we have already discussed, right? Now, people, understand. If I put these two parameters into the main equation, what do I get? Instead of delta G, I'll be writing minus NFE cell is equal to, instead of delta G naught, I'll be writing minus NFE naught cell. Minus NFE naught cell. It's going to be plus, this is RT, this is ln of QC. Okay. Now, first of all, if I divide this equation throughout by what? If I divide this equation throughout by NF, I'm dividing this particular term by NF. I'm dividing this particular term by NF. And at the same time, I'll be dividing this particular term with NF as well, right? So NF and NF cancelled. So I'll be getting, okay, you can do one more thing. You can multiply throughout with the minus sign. When you multiply throughout with the minus sign, NF and NF cancelled, minus minus becomes plus. So you are getting one equation here, which is E cell is equal to E naught cell minus E naught cell minus, this is RT divided by NF, and it's going to be ln of QC. This particular equation which is made over here. My dear students, this particular equation which is formed over here, which is made over here, this particular equation is something which you call as Nernst equation. This is something which you call as Nernst equation. Okay. So E cell is equal to E naught cell minus RT divided by NF ln of QC. Now, let me further simplify it a bit. Have a look. So you can write something like this. E cell you are going to write as such. Is equal to E naught cell you are going to write as such minus. This is ln of QC. So convert it into log. So it has to be 2.303 RT divided by NF, and now it's going to be log of QC, right? This is one more form of the Nernst equation, which is something I call as the logarithmic form. This is something which I call as the logarithmic form of the Nernst equation. Now, my dear students, try to understand the parameters which are there in the equation. Once you get to know the parameters, then I can show you its application form. Where do we exactly need this particular equation? Before that, what is this E cell over here? E cell is something which you call as EMF of the cell. E cell is something which you call as EMF of the cell, but under which conditions? Under non-standard conditions. Under non-standard conditions. I hope you all remember what are standard conditions and what are non-standard conditions. In case of standard conditions, concentration is taken as 1 molar, pressure is taken as 1 bar, right? And temperature is generally kept constant, right? Temperature is kept constant, generally 25 degrees centigrade. Perfect. So E cell is something which you call as the EMF of the cell under non-standard conditions. I hope you remember what EMF is. What is the EMF? EMF is the maximum potential difference between the electrodes in the galvanic cell when the cell is not in use. Discuss that in detail, right? Already we have discussed that in detail. EMF is basically the maximum potential difference between the electrodes when the cell is not in use, when no current is drawn from the cell, right? And EMF is measured with the help of potentiometer. I hope you remember that. Now, people, what is E naught cell? What is E naught cell? E naught cell is something which you call as standard EMF of the cell. This is something which you call as standard EMF of the cell. And I hope you guys remember, how do we calculate E naught cell? It is calculated like this. E naught cathode minus E naught anode. What is E naught cathode? This is something which you call as standard reduction potential of cathode. And this particular term is your standard reduction potential of anode. This is how you calculate E naught cell as well. Okay. I hope you remember what this N exactly is. If I ask you what is this N over here, N represents number of moles of electrons exchanged in the net cell reaction. Number of moles of electrons exchanged in the net cell reaction. And I have taught you in detail how do we get the N value, right? What is this F over here? F is the Faraday's constant. F is the Faraday's constant, whose value is 96500 coulombs, right? And what is this QC over here? QC is something which you call as reaction quotient. QC is something which you call as reaction quotient. And if you remember, already I have taught you how to get the reaction quotient of a particular reaction. What is this T over here? T is the temperature at which the cell is working. And R, it's a constant whose value you already know, that's 8.314 joules per Kelvin per mole. Correct? Now, my dear students, try to understand what exactly I'm going to say. Something important I'm going to discuss with you. See, we got the equation. The equation is something like this. E cell is equal to E naught cell minus 2.303 RT divided by NF, and then we are going to write log of QC. This is something which you call as the Nernst equation. Now, my dear students, in the questions, I'm not going to use this equation always. In the questions, I'm going to simplify this equation a bit, right? And after simplifying, we'll be getting one comparatively simple equation, and that simple equation we'll be using in the questions. And how do we get that equation? See, guys, if I keep the temperature as 25 degrees centigrade, which means 298 Kelvin, right? If I take the Faraday's constant as 96500 coulombs, right? If I take the value of R as 8.314 joules per Kelvin per mole, if I put all these parameters into the equation, what do I get finally? I'll be getting something like this. E cell is equal. It is going to be E naught cell minus 0.0591 divided by N, and then it's going to be log of QC. This is the equation which I'll be using in majority of the questions in case of the Nernst, right? Okay. E cell is equal to E naught cell minus 0.0591 divided by N, then it's going to be log of QC. My dear students, do you remember how do we calculate E naught cell? I have discussed this with you. E naught cell is equal to E naught cathode minus E naught anode. Do you remember how do we get the N value? Number of moles of electrons exchanged in the net cell reaction. For that purpose, we write reaction at anode, then we write reaction at cathode, then we try to balance the electrons, then we try to add the reactions, and once we add the reactions, there will be the electrons which gets cancelled out, right? That gives you the N value. I hope you remember. And I hope you remember how to get the QC value as well. This is something which we have discussed too, right? So basically, whatever parameters we need in the Nernst equation, all those parameters we have already discussed. Now, what we need to do is, we need to put those parameters, we need to put the value of those parameters into this equation and get the value of E cell. Okay? So number one, this equation is what you call as Nernst equation. Now the point is, where all do we use this equation? What about its application? My dear students, let me exactly tell you where all do we use this particular Nernst equation. Okay? So first of all, Nernst equation is used in half cells. Half cells means electrode, right? You know, a complete cell, a complete galvanic cell, that's made up of 2 electrodes, right? Or you can say a complete galvanic cell, it's made up of 2 half cells. Half cell is equal to electrode, right? Half cell is equal to electrode. You can use this particular equation for the half cells. Why? My dear students, in order to calculate the oxidation potential of any electrode under non-standard conditions, or in order to calculate the reduction potential of any electrode under non-standard conditions, I'll be using this particular equation. In order to calculate the oxidation potential of the half cell, the oxidation potential of the electrode, or the reduction potential of the electrode under non-standard conditions, at that point of time, I'll be using this particular equation. And how exactly I'm going to write this? Imagine that I need to calculate reduction potential of some electrode under non-standard conditions. How do I write this equation? You'll be writing this equation in a different format. You'll write ERED, which represents the reduction potential of the half cell, is equal to E naught RED. E naught RED means standard reduction potential of the same electrode, right? Minus 0.0591 divided by N. And then it's going to be log of what? Log of QC. So this particular equation is used to calculate the reduction potential of the half cell under non-standard conditions. Okay? My dear students, in the similar way, whenever you need to calculate the oxidation potential of the half cell under non-standard conditions, again, you'll be using this particular equation. And how do you write this equation at that time? You'll write EOX. Instead of E cell, you'll be writing EOX, which represents oxidation potential of the half cell under non-standard conditions, is equal to E naught OX. E naught OX represents standard oxidation potential of the half cell, minus 0.0591 divided by N. Then it's going to be log of QC. Where do we use this particular equation? My dear students, whenever you'll be given with the electrode, whenever you'll be given with a half cell, and you will be supposed to calculate the oxidation potential or reduction potential of that half cell under non-standard conditions, you'll be using this Nernst equation in these 2 forms, right? If you are supposed to calculate the reduction potential of the half cell, use this equation. If you are supposed to calculate oxidation potential of the half cell, use this particular equation. That's all, right? Okay. Is this point clear to everyone? Now, one by one, in detail, we are going to discuss how this Nernst equation exactly is used. Okay. So first of all, I'll show you how Nernst equation is used in case of electrodes, or electrode is something which you call as half cell. Okay. Try to understand what exactly I'm going to say. Imagine that I've taken a container. Let's say this is the container. And my dear students, in this particular container, imagine that there is an electrolyte. Is it fine now? Is it fine now? Quickly, let me know in the chats. It should be okay now, I believe. Yeah? Guys, just refresh once. Just refresh once. Okay, now it's fine. All right, perfect. All right, guys, try to understand what exactly I'm going to say. Imagine that this is a container, and in this container, you have kept the ions. Which ions? Mn positive ions, right? And in this particular container, you have dropped a rod. There is a rod which is made up of element M. There is a rod which is made up of element M. And this particular rod is introduced into a solution containing its own ions, right? I've taken a rod, right? And this rod is introduced into a solution which contains its own ions. Perfect. So I'll be calling this whole setup as electrode. This whole setup should be called as electrode. Now, my dear students, this particular electrode, which I've taken over here, It can work like cathode, it can work like anode as well. You know it already. Imagine that this particular electrode is working like cathode. Imagine that the electrode is behaving like the cathode. Okay. Now tell me one thing. When this particular electrode behaves like the cathode, what is going to happen? Oxidation or reduction? Reduction will happen. Because at cathode, always reduction takes place. A reduction means gain of electrons. So what exactly is going to happen? My dear students, these Mn positive ions, which are there in the solution, they are going to collide with the rod. They are going to take N electrons from the rod. So the reaction has to be something like this. Mn positives, which were there in the solution, they are going to collide with the rod. They are going to take N electrons out from the rod, and it will get converted into M solid. This has to be the reaction when this particular electrode behaves like the cathode, right? Now tell me one thing. In this particular reaction, if I ask you how many moles of electrons are exchanged, in this particular reaction, I must say N moles of electrons are exchanged. Now, dear students, if I ask you to write the reaction quotient for this particular reaction, you'll start with the product, which is in solid form. It's active masses unity divided by. It's going to be concentration of Mn positive raised by its stoichiometric coefficient. That's 1. Okay, perfect. Now, my dear students, I want you guys to calculate the reduction potential of this particular electrode. Imagine for example, the concentration of Mn positive is anything, 3 molar, 4 molar, 5 molar, right? Imagine the concentration of Mn positive in the container is anything, 3 molar, 5 molar, 6 molar, anything, right? So basically, is this electrode present under standard conditions or non-standard conditions? I'm not keeping the concentration of electrolyte here as 1 molar. I'm keeping it different. So this particular electrode is present under non-standard conditions. Now, under non-standard conditions, I want you to calculate the reduction potential of this half cell, the reduction potential of this electrode. And reduction potential of the electrode under non-standard conditions is calculated with the help of Nernst equation. It is calculated with the help of Nernst equation, right? My dear students, basically what am I asking you to calculate? Try to understand one thing. If you remember, we have discussed this in detail. See, basically initially in the container, there were equal number of cations and anions. Initially in the container, there were equal number of cations and anions. Now, the cation in the container is colliding with the rod. It is taking electrons from the rod. Getting converted into what? Getting converted into M solid. And that M solid will be deposited on the rod. Tell me, is the amount of cations in the container increasing or decreasing? Is the amount of cations in the container increasing or decreasing? I'll say amount of cations in the container is decreasing because Mn positives, they are undergoing reduction, getting converted into M solid, and that M solid is deposited on the rod basically, right? So the amount of cations in the container are decreasing. If the cations are decreasing, anions in the container are remaining the same, but cations are decreasing. So this solution will effectively get which charge? This solution will get effectively negative charge. And my dear students, these Mn positive ions, they have collided with the rod. They have taken electrons from the rod. If electrons are taken from the rod, then the rod gets which charge? Positive charge, right? So tell me one thing. The rod got positive charge. Solution got negative charge. Can I say between the rod and the solution, a potential difference is getting created? A potential difference is getting created between the rod and the solution. And that potential difference is what you call as electrode potential basically, right? That's what you call as electrode potential. Imagine the conditions are not standard. So I'll be calling this electrode potential under non-standard conditions, right? Perfect. So what I simply did, leave all this aside. We have discussed this in detail. I just need one thing here. I told you that I've got an electrode and I want to calculate its reduction potential under non-standard conditions. Okay. So till here, I'm done. Now, in order to calculate reduction potential under non-standard conditions, I'll be using the Nernst equation. Nernst equation says that ERED, reduction potential of the same electrode under non-standard conditions, is equal to E naught RED, which is standard reduction potential of the same electrode, minus 0.0591 divided by N, and it's going to be log of QC. What is QC? QC is 1 divided by concentration of Mn positive. right? This is how you guys are going to calculate. This is how you guys are going to calculate the reduction potential of the half cell under non-standard conditions. This particular term represents what? It represents the reduction potential of the half cell. Under which conditions? Under non-standard conditions. Under non-standard conditions. This particular term represents standard reduction potential of this electrode, standard reduction potential of the half cell, right? And N already you know, it represents moles of electrons exchanged. Now tell me one thing. Tell me one thing, guys. One thing I want you guys to learn from here. Say, imagine that I'm increasing the concentration of electrolyte in the container. Imagine that I'm increasing the concentration of electrolyte in the container. If I increase the concentration of electrolyte in the container, tell me what will happen to the concentration of Mn positives. These Mn positives, how they are coming into the container when the electrolyte is undergoing dissociation. If I'm increasing the amount of electrolyte in the container, can I say the concentration of Mn positives in the container will increase? Absolutely. The concentration of Mn positives in the container will increase. Now use simple mathematics here. You are increasing the concentration of Mn positives in the container by adding more electrolyte. You are increasing the electrolyte in the container. So you are increasing the concentration of Mn positive. That means you are increasing the denominator here. If you increase the denominator, what will happen to this particular value? This value will decrease. You are increasing the denominator. So this whole value is decreasing. If this value is decreasing, I would say this whole value will be decreasing. If this whole value is decreasing, what will happen to the difference of these two terms? If this value is decreasing, I must say the difference between these two terms, it will increase. If the difference between these two terms increases, that actually means your reduction potential is increasing. That actually means reduction potential of the half cell that is increasing. So from here, we can generalize one very, very, very important statement. And what is the statement all about? Statement is very simple. On increasing the concentration of electrolyte in the container, the reduction potential of the half cell that increases. Okay, what is meant by this? Let's try to understand this a bit more in detail. See guys, imagine that this is the zinc electrode. This is the zinc rod, and you have introduced the zinc rod into zinc sulfate, right? You have got one more zinc electrode here. This is your zinc rod, which is introduced into zinc sulfate, right? Electrodes are same. Both are zinc electrodes, right? Now tell me one thing. Imagine the concentration of zinc sulfate here is 2 molar. And the concentration of zinc sulfate here I have kept as 5 molar. Will the reduction potential of both the electrodes be same or different? Since the concentration of electrolyte is kept different, that electrode in which the concentration of electrolyte is more, will have more reduction potential. Is it simple? So I would say this particular electrode will have more reduction potential than this particular electrode. Yes? Agreed? So do remember, this is one very important thing. With the increase in the concentration of electrolyte, the reduction potential of the electrode, it automatically increases. Okay? Now people, so this is how you calculate the reduction potential of the half cell. Okay? Now people, now the point is, how do we calculate oxidation potential of the half cell? How do we calculate the oxidation potential of the half cell? Tell me one thing. Imagine I'm taking the same electrode which I took few minutes back. Let's say this is your container, and in this container what do we have? We have got Mn positive ions, and here you have introduced a metal rod. So this is an electrode. Now my dear students, I want to calculate the oxidation potential of this half cell under non-standard conditions. In order to calculate oxidation potential, I'll make sure this electrode behaves like the anode. Why? Because at anode only oxidation takes place. So I'll make sure that this electrode behaves like the anode. When this electrode behaves like the anode, what will happen? Oxidation, right? So this rod is basically made up of metal atoms, and those metal atoms will undergo oxidation. They'll lose electrons, and those metal atoms, they'll get converted into Mn positives, and Mn positives will enter into the solution, and you'll be getting some N electrons here. Perfect. This is the reaction which will happen when this particular electrode behaves like the anode. behaves like the anode, right? Now try to understand. This represents number of moles of electrons exchanged, right? Now, I'm asking you to get the QC value. Start with the product. It's going to be concentration of Mn positive, raised power stoichiometric coefficient, that's 1. This is in solid state, its active mass is unity. Now, my dear students, what exactly am I going to do? I made sure that electrode behaves like the anode. At anode, oxidation takes place. So basically, I'm asking you to calculate the oxidation potential of this particular half cell. Oxidation potential of this electrode. As per Nernst equation, it has to be equal to E naught OX, standard oxidation potential of the same electrode, minus 0.0591 divided by N, and then it's going to be log of QC. And QC value is nothing, that's concentration of Mn positive. Clear? So with the help of this particular equation, I will be calculating the oxidation potential of this particular electrode under non-standard condition. So this is oxidation potential of what? Of the half cell under what? Under non-standard conditions. Under non-standard conditions. What is this E naught OX? This is your standard oxidation potential of the same half cell. Okay. Now try to understand one thing here. My dear students, if I increase the concentration of electrolyte in the container, what will happen due to that? Due to that, I would say the concentration of Mn positives will increase. Now, if the concentration of Mn positive is increasing, if this term is increasing, that means this term is increasing. If this term is increasing, that means this term is increasing. If this particular term is increasing, that means the difference between the two will decrease. If the difference between the two is decreasing, what does that mean? That means indirectly oxidation potential is decreasing. So indirectly oxidation potential is decreasing. So do remember this particular scenario as well. Upon increasing the concentration of electrolyte in the container, the oxidation potential of the half cell, the oxidation potential of the electrode, it decreases. Is this point clear to everyone? Say yes or no in the chats quickly with the thumbs ups. Is this point clear to everyone? So with the increase in the concentration of electrolyte, reduction potential of the electrode increases. And it's evident, if reduction potential of the electrode increases, automatically oxidation potential of the same electrode, that will decrease, right? Let me know once in the chats quickly, everyone. Everyone. Yeah, it's clear? Wonderful. All right. So I hope you got to know how do we calculate the oxidation potential and reduction potential of the half cells of the electrodes under non-standard conditions, right? And my dear students, after some time, I'll be giving a lot of questions on the same equations so that you'll understand it in a better way, right? But right now, this much is enough. Okay, after some time, I'll give you the questions. Before solving the equations, there are a few more things which I want to share with you. What are those things? Nernst equation for hydrogen electrode. How do you exactly write the Nernst equation for hydrogen electrode? Try to understand. I hope you guys remember how we exactly make the hydrogen electrode. I hope you remember. This is the container. In this particular container, what are we keeping? In this particular container, we are keeping H positives, right? This concentration of H positive can be anything. I'm keeping H positives in the container. And my dear students, over here, this is the inverted U-type tube, which I'm keeping over here, right? And if you remember, there's a platinum wire, which is coated with platinum black. I hope you remember this as well. This is the platinum wire, which is coated with platinum black, right? And over here on this side, I'm introducing H2 gas. What is going to happen? This H2 gas will adsorb on the surface of platinum. And I'll make sure this H2 gas, which I'm introducing, it gets adsorbed on the whole surface of platinum, right? I'll introduce H2 gas, still the whole surface of platinum is covered by H2 gas. Can I say, after continuously the introduction of H2 gas, can I say there'll be a scenario when this platinum wire is completely covered with H2 gas, right? So it looks like a hydrogen rod to me. It does not look like a platinum rod now. It looks like a hydrogen rod because its entire surface is covered with hydrogen gas. Now put this hydrogen rod and introduce in H positives, right? So hydrogen rod introduced into its own ions. So this whole setup I'll be calling as electrode. Now which electrode this is? This is the hydrogen electrode. This is the hydrogen electrode, right? This is the hydrogen electrode. Now tell me one thing. Imagine the pressure at which I'm introducing H2 gas. Imagine that is, for example, 1 bar. The pressure at which I'm introducing hydrogen gas. Imagine that's 1 bar, right? Now guys, this particular hydrogen electrode which we have, this hydrogen electrode, it can behave like anode or it can behave like cathode, right? Imagine that this particular hydrogen electrode is behaving like the anode. When the hydrogen electrode behaves like the anode, what's going to happen? Oxidation is going to happen. Oxidation is going to happen. The surface is covered with H2 gas, right? So H2 gas on the surface, it will undergo oxidation. And if you remember, when H2 undergoes oxidation, it gets converted into 2 times H positive aqueous, and with that you'll be getting 2 electrons. This is something which is also discussed when I taught you the hydrogen electrode formation long back. So when this particular hydrogen electrode, when it behaves like the anode, this is the reaction which is going to happen, which I call as the oxidation reaction. Now, my dear students, in this particular reaction, if I ask you, how many moles of electrons are exchanged? I would say 2 moles of electrons are exchanged. 2 moles of electrons are exchanged in this reaction. Okay. Tell me what is the value of QC? QC value. Start with the product. It is concentration of H positive raised power 2 divided by, this is partial pressure of H2, and partial pressure of H2 I have kept as 1 bar. So leave that aside. Okay. So this is your QC value. Now, my dear students, since this electrode, this hydrogen electrode is behaving like the anode, and at anode oxidation takes place, right? Imagine I want to calculate the oxidation potential of this hydrogen electrode under non-standard conditions. So I'll be using the Nernst equation. I'll say EOX, oxidation potential of this hydrogen electrode, is equal to E naught OX, standard oxidation potential of the same hydrogen electrode, minus 0.0591 divided by N. Then it's going to be log of QC. This is how you are going to write Nernst equation. To calculate what? To calculate oxidation potential of this particular hydrogen electrode under non-standard conditions. Now, my dear students, you guys are going to tell me one thing. What is E naught OX? That is standard oxidation potential. If you remember, SOP, SRP of hydrogen electrode as per convention is taken as 0. Do you remember that? Right? SOP as well. This is SOP of hydrogen electrode. And you know SOP as well as SRP of hydrogen electrode, that's taken as 0. So this particular term is already 0. Now minus 0.0591 divided by what? Divided by N. Log of QC. So it's going to be log of QC is nothing. That's concentration of H positive ka square. Correct? Now guys, tell me one thing. Log of M raised power N. Log of M raised power N is N log M. So I can write it like this. EOX is equal to minus 0.0591 divided by N value is 2. So this is 2 log of H positive. Log of H positive concentration. As simple as that. Right? As simple as that. Now after this, what am I going to do? Try to understand. After this, what exactly am I going to do? Try to understand. I'll write EOX is equal to. EOX is equal to. This 2 and 2 gets cancelled out. I'll just write 0.0591. And this minus I'll take inside. So it's minus log of H positive. Minus log of H positive is something which you call as minus log of H positive, something which you call as pH. So my dear students, this is one general result which I got. Calculate the oxidation potential of the hydrogen electrode in which the partial pressure of H2 is 1 bar. Right? In which the partial pressure of H2 is 1 bar. If the partial pressure of H2 is changed, if it's not 1 bar, then you cannot use this relation. You cannot use this relation. This relation is only valid when the partial pressure of H2 is 1 bar. Now guys, tell me one thing. Can I say oxidation potential of the hydrogen electrode depends on the pH of this solution? It depends on the pH of this particular solution, right? Okay. So can I say on increasing the pH of the solution, the oxidation potential of the hydrogen electrode, does it increase or decrease? It will absolutely increase, right? Oxidation potential is directly proportional to pH. If you increase the pH of the solution, I would say its oxidation potential will automatically increase. Right, people? Is it clear to everyone? Quickly in the chats. Quickly in the chats. Let me know quickly in the chats if all the things are absolutely clear. right? Okay. So what I was telling you, this is just a general equation by means of which you can calculate the oxidation potential of the hydrogen electrode under non-standard conditions. Now guys, tell me one thing. Can't the same hydrogen electrode behave like the cathode? What do you think? Can't the same hydrogen electrode behave like the cathode? Absolutely, the same hydrogen electrode, it can behave like the cathode as well. Yeah? The same hydrogen electrode, it can behave like cathode as well. And tell me just one thing. When the same hydrogen electrode behaves like the cathode, what will happen? Reduction will happen. Just reverse this reaction. So the reaction now is going to be 2 times H positive aqueous plus 2 electrons. It gives what? It gives H2 gas. So this is the reaction when the hydrogen electrode behaves like the cathode. Now guys, how many moles of electrons are exchanged? 2 moles of electrons are exchanged in this particular reaction. Write the expression for QC. QC is going to be, start with the product. It is in gaseous form. So partial pressure of H2, I'm going to take as 1 bar divided by concentration of what? Concentration of H positive raised power 2. And it has to be concentration of H positive raised power minus 2. Simple. Now, I made sure that hydrogen electrode behaves like the cathode. At cathode, reduction takes place. So indirectly, what am I trying to calculate? I'm trying to calculate the reduction potential of the same hydrogen electrode under non-standard conditions. And I'll be using the Nernst equation. Reduction potential of the hydrogen electrode is equal to standard reduction potential of the hydrogen electrode minus 0.0591 divided by N. And it's going to be log of QC. Right? Now, my dear students, in case of hydrogen electrode, this particular term is going to be 0. This is SRP of hydrogen, 0. So it's going to be ERED is equal to minus 0.0591 divided by N value is just 2 and log of QC. QC is concentration of H positive raised power minus 2. Perfect. Now, log of M raised power N. Log of M raised power N, which has to be N log M, right? So I would say ERED is equal to minus 0.0591 divided by 2. Log of M raised power N is N log M. So minus 2 comes to the front. Then it's going to be log of H positive here. Perfect. Simple maths I'm using, nothing else. So 2 and 2 got cancelled out. When 2 and 2 gets cancelled out, what I'll be left with? See guys, try to understand. I'll be writing the reduction potential of the hydrogen electrode is equal to minus 0.0591. Oh, this is minus log of H positive, and minus log of H positive is something which you call as pH. Minus log of H positive is something which you call as pH. So I got one more important result over here. The reduction potential of hydrogen electrode, does it depend on pH? Yes, it does depend upon the pH. And you got to know, on increasing the pH of the solution, reduction potential of the hydrogen electrode, it will decrease because the sign here is minus. Right? Perfect. And just try to understand one thing. Look at this equation. ERED is equal to minus 0.0591 multiplied by pH. And look at this equation. AOX is plus 0.0591 into pH. It is evident only. This is something which we already knew. This is something which I've already told you. EOX of an electrode is equal to minus times its ERED. Right? That's something which was already discussed, which was already understood. I hope all these things are clear. To you. Is that people? Right? So this is one more important result. You need to remember this. So when you increase the pH, of this particular solution, oxidation potential of hydrogen electrode will increase and reduction potential of the same electrode, it will decrease. Right? Perfect. Perfect, guys. So I hope you got to know how exactly we are going to use Nernst equation for half cell. Okay? So now, my dear students, let's try to solve few basic questions so that you can understand all these things properly. Look at the first question. From this particular question, you'll exactly get the idea of how we use Nernst equation for the half cells. All the types of questions which can be asked from Nernst equation, I'll be solving all those types of questions here only. right? Afnan, that was a nice one, yeah? Okay, look at this particular question, guys. Try to understand. The question is, we are given with an electrode. Look at the electrode carefully. You have taken an iron rod, and this particular iron rod is introduced in a solution containing FeSO4, right? Simple. So basically, you have taken an iron rod. Let me just make it clear to you. Imagine this is the container, and in this particular container, what have we kept? We have kept FeSO4. Now, this FeSO4 would have got dissociated as Fe di positive plus SO4 di negative. Now, in the same container, you have introduced an iron rod. This is the iron rod which is introduced into a solution containing its own ions. I'll be calling this whole setup. As electrode. So this is an iron electrode, right? And my dear students, what exactly I'm going to do? Look at the question. The question is asking, calculate the oxidation potential of this half cell when the concentration of FeSO4 is kept 0.1 molar. The question says, when the concentration of electrolyte in the container is 0.1 molar, at that point of time, what will be the oxidation potential of this half cell? Yeah? Now have a look. Have a look, people. First of all, initially, as per the question, the concentration of FeSO4 I have kept 0.1 molar. So this has to be 0. This has to be 0. Now imagine that this FeSO4, it gets 100% dissociated into its ions. And when this FeSO4 gets 100% dissociated into its ions, I'll be left with nothing. Now people, 1 mole gives 1 mole, 0.1 molar gives 0.1 molar. This has to be also 0.1 molar. If I ask you, what is the concentration of Fe di positive in the solution? You will say the concentration of Fe di positive in the solution is 0.1 molar. Now you must be thinking, why did I calculate the concentration of Fe di positive? My dear students, I need that concentration of Fe di positive to write QC. Have a look. See, as per the question, what do I need to calculate? I need to calculate oxidation potential of this half cell when the concentration of FeSO4 is 0.1 molar. To calculate the oxidation potential, I'll make sure that the electrode behaves like the anode, because at anode only oxidation takes place, right? At anode only oxidation takes place. Now have a look. What has to be the reaction? At anode, oxidation. Oxidation means loss of electrons. See, this is iron with oxidation state 0. This is iron with oxidation state +2. So iron is changing its oxidation state from 0 to +2. Increase in the oxidation state. Oxidation, loss of electrons. So basically the reaction has to be Fe solid is getting converted into what? Fe solid has to get converted into Fe di positive aqueous. And with this, you'll be writing 2 electrons. So this is the reaction which will take place when this particular electrode will behave like the anode. Now if I ask you, how many moles of electrons are exchanged in this reaction? I'll say 2 moles of electrons are exchanged. Okay? 2 moles of electrons are exchanged. Tell me, what about QC value? What about QC value? Start with the product. Its concentration of Fe di positive raised power 1 divided by, this is solid, its active mass is unity. Now, do you understand why did I calculate the concentration of Fe di positive? Because I needed it here. So the concentration of Fe di positive in the solution is nothing, that is 0.1. Perfect. So QC value is 0.1, right? N value is 2. Now, what do I need to calculate? I need to calculate the oxidation potential. So use the Nernst equation. Oxidation potential of the half cell is equal to E naught OX, standard oxidation potential of the half cell, minus 0.0591 divided by N. Then it's going to be log of QC. Perfect. So this is something which I need to calculate. EOX is equal to E naught OX. Look at this particular value. Is this SOP or SRP? See, this is +2 to 0. +2 to 0 means decrease in the oxidation state. Decrease in the oxidation state means the reduction. So this is SRP. But do I need SRP or SOP? We need SOP. So this particular term is SOP, right? This is SRP. So just reverse its sign. So it's plus 0.44. Plus 0.044 minus 0.0591 divided by N value. N value as per the question is 2. Then it's going to be log of QC. QC value, we have already calculated that 0.1, which means 10 raised power minus 1. Now it's a matter of calculation only. This is 0.0591 divided by 2, and it's log of m raised power n log m. So minus 1 comes to the front, log 10 is 1. So just solve this value and get the answer in volts. That's going to be the oxidation potential of this particular half cell, right? Okay. Whatever you get from here, that's going to give you the oxidation potential of the half cell, which you were supposed to calculate. Imagine that you were supposed to calculate the reduction potential of the same half cell. Since you calculated the oxidation potential, just reverse its sign. You'll be getting the reduction potential of the same half cell as well, when the concentration of FeSO4 is taken as 0.1 molar. Is this clear? Let me know once in the chats, people, quickly. Quickly. Priya is saying it's 0.046, right? Okay. It is 0.0, I think 47, right? This is the oxidation potential of this particular half cell. So its reduction potential will be minus times this. Okay. This sort of a question, I believe you can solve easily from now onwards. Look at the next question. Look at this particular question. Calculate the oxidation potential of this particular half cell. Your half cell is H2 gas. This side you have got HCl. So HCl in the container would have dissociated as H positive plus Cl negative. So I'm making it in the simpler format like this. Imagine that in this container you have kept HCl, and this HCl would have got dissociated as H positive plus Cl negative. The concentration of HCl which you have taken, that is 0.1 molar. So initially this will be 0, this will be 0. Now finally this is 0, this will be 0.1 molar, and this is 0.1 molar as well, because the stoichiometry is 1:1:1, right? Simple. 1 mole gives 1 mole, so 0.1 is going to give 0.1. Yeah? Now people try to understand. Imagine this is the hydrogen rod. This is the H2 rod here. And you already know how this H2 rod is made with the help of platinum, right? And the pressure at which H2 was introduced on platinum, that is 10 atm. That is 10 atm, right? Okay. Now guys, try to understand. As per the question, what am I supposed to calculate? Oxidation potential of this hydrogen electrode. This is the hydrogen electrode basically. I need to calculate its oxidation potential. To calculate the oxidation potential, I'll make sure the electrode behaves like the anode. I'll make sure the electrode behaves like the anode. And at anode, oxidation takes place. Tell me, when hydrogen electrode behaves like the anode, oxidation takes place. What has to be the reaction? Few minutes back I told you, H2 gas, it gets converted into what? 2 times H positive aqueous, and with that you'll be writing 2 electrons. This is the reaction which will happen when the hydrogen electrode behaves like the anode, right? Now my dear students, if I ask you how many moles of electrons are exchanged here, you will say 2 moles of electrons are exchanged. Okay? Try to calculate the QC value. QC value has to be its concentration of H positive raised to the power 2 divided by what? Divided by partial pressure of H2 raised power 1. Now what is the concentration of H positive in the container? The concentration of H positive in the container is nothing, that's 0.1 molar. 0.1 means 10 raised power minus 1. So it's 10 raised power minus 1 raised power 2 divided by. What is the partial pressure of H2? That's 10. So this is 10 raised power minus 2 divided by 10. The value comes out to be 10 raised power minus 3. So you got the QC value. You got the QC value. Now what are we supposed to calculate? Oxidation potential. Use the Nernst equation. Oxidation potential of the half cell is equal to standard oxidation potential. SOP of hydrogen, that's 0. SOP of hydrogen is 0 minus 0.0591 divided by n value is 2, and its log of QC. QC is just 10 raised power minus 3. Again, the matter of calculation only. Minus 0.0591 divided by 2. Log of m raised power n is n log m. So minus 3 comes to the front. Log 10 is 1. Just solve it and get the answer in volts. This will be the oxidation potential of this particular half cell when the concentration of HCl in the container is 0.1 molar. Is this clear? Is this clear? Yes, I'll teach everything. Conductance, Kohlrausch law, everything I'll teach. But that will be in the next session. In this session, I'll be completing complete EMF. EMF part will be completed today. In the next session, Faraday's laws, conductance, Kohlrausch law, that will be done. All the things clear? Perfect. Let's have a look on one more question. Let's have a look on one more question, yeah? Okay. Look at this particular question. Similar type of question, guys. Similar type of question. You are given with a half cell, right? You are supposed to calculate its oxidation potential. You're supposed to calculate its oxidation potential. Now, oxidation potential you have to calculate. In order to calculate the oxidation potential, you'll make sure that this electrode behaves like the anode. At anode, oxidation takes place. At anode, oxidation takes place. Oxidation means increase in the oxidation state. Oxidation state here is 0. Here the oxidation state is -1. So what should be the reaction? Should I write the reaction as Cl2 gives Cl negative or Cl negative gives Cl2? You tell me that. What should I write? Should I write Cl2 gives Cl negative or Cl negative gives Cl2? Quickly. What should I exactly write? What do you think? What do you think? Since I'm making sure that the electrode behaves like the anode, right? At anode, oxidation takes place. Oxidation means increase in the oxidation state. So through the reaction, I have to show that oxidation state is increasing. So for that purpose, I have to write Cl negative, it gives what? It gives Cl2 gas, right? So now it becomes -1 to 0. -1 to 0 means -1 to 0 increase in the oxidation state, means oxidation, loss of electrons. Loss of electrons. Now this is Cl2, so this has to be 2 times Cl negative. Tell me one thing. 1 Cl negative, when it loses 1 electron, it gets converted into Cl. Now as per the question, this is Cl2, this is 2, so this has to be 2 as well, right? So you'll be writing 2 electrons with it. You'll be writing 2 electrons with it. I hope this is clear. Okay, so this is the reaction. Now since N value you got, N value is 2, now write the QC. QC is going to be, it's going to be partial pressure of Cl2 divided by concentration of Cl negative raised power 2. What is the partial pressure of Cl2? 10 atm divided by, what is the concentration of Cl negative in the solution? In the solution. Since in the solution you have taken HCl, this HCl would have got dissociated as H positive plus Cl negative. Stoichiometry is 1:1:1, right? So 1 mole of HCl gives 1 mole of Cl negative. 0.1 molar HCl will give 0.1 molar Cl negative, right? So you got the concentration of Cl negative as well. That is simply 10 raised power -1. But this is raised power 2. So it's going to be 10 divided by 10 raised power -2. The value will come out to be 10 raised power 3. So this is QC. Now what do I need to calculate? I need to calculate the oxidation potential of the half cell. So I'll write oxidation potential of the half cell is equal to standard oxidation potential E0x minus 0.0591 divided by, this is going to be N, and now it's going to be log of what? Log of QC. I believe all the terminologies you already have now. So EOX is equal to E0x. What is E0x? Standard oxidation potential. Look at this. -1 to 0, -1 to 0, -1 to 0, increase. Increase means oxidation. So this SOP, and that SOP I need here. So it's -1.36, minus 0.0591, divided by N value is 2. Log of 10 raised power 3. Log of 10 raised power 3 means P log 10. Log 10 is 1. Just solve this part, get the answer of the question, get the oxidation potential of the half cell, which you were supposed to calculate. Right? Electrons will add. Why electrons will add? At anode, oxidation takes place. Oxidation means loss of electrons. Right? That's why electrons are on right side. Okay? And this is Cl negative. Cl negative. Right? It's not Cl or something. I hope it's clear. Okay, guys? All right, let's try to solve one more question. Let's try to solve one more question. Look at this particular question. See what the question says. A solution containing 4 into 10 raised power -4 molar Cr2O7 dinegative and 2 into 10 raised power -2 molar Cr tripositive ions shows a pH of 1. Calculate the reduction potential of this half cell. So as per the question, we are given with the half cell, and half cell is like this. Half cell is like this. Platinum solid, Cr2O7 dinegative, right? Cr tripositive. This is your half cell, correct? Now, my dear students, what you need to calculate? You need to calculate the reduction potential of this half cell. You need to calculate the reduction potential of this half cell. In order to calculate its reduction potential, I'll make sure this half cell behaves like the cathode. I'll make sure this half cell behaves like the cathode, because at cathode only reduction takes place, right? Now, try to understand. What is the oxidation state of chromium here? It is +6. Oxidation state of chromium here, it's +3. So +6 to +3. +6 to +3. +6 to +3. Decrease in the oxidation state. Decrease means reduction. And I have to write the reduction reaction only. So basically, Cr2O7 dinegative, aqueous. It has to get converted. It has to get converted into Cr tripositive aqueous. Then only I can represent reduction. Because reduction means decrease in the oxidation state. +6 to +3. Decrease. Decrease means gain of electrons. Now, when Cr2O7 dinegative gets converted into Cr tripositive, how many electrons are gained? +6 to +3. Change is 3. 3 is the change for one atom. But I have 2 atoms of chromium. So 3 2s are 6. I'll say 6 electrons are being gained here. Right? And then it gets converted into Cr tripositive. Make sure this is 2 Cr. So it has to be 2 times Cr this side as well. Okay. Now people, if I ask you whether this particular reaction is balanced or not, look at it carefully. Is it balanced? Look at it carefully. Is it balanced? The reaction is not balanced because you have got oxygen here. No oxygen on this side. There is one hint that is given. As per the question, pH of the solution is given to us as 1. If pH is 1, that means solution is acidic. So you're going to balance this particular reaction in acidic medium. You're going to balance this reaction in acidic medium. And how do you balance the reaction in acidic medium? 7 oxygen on this side. No oxygen on right side. So right side is oxygen deficient. So add 7 water molecules on this side. Now after this, balance hydrogen. 14 hydrogen on this side. So it has to be 14 H positives on this side as well. So now the reaction is balanced. Reaction is balanced. At the same time, if I ask you how many moles of electrons are exchanged, 6 moles of electrons are exchanged in the net cell reaction. Okay. Tell me the value of QC. Start with this particular thing. It is concentration of chromium tripositive raised by stoichiometric coefficient, that's 2. This is in liquid form. Its active mass is unity. Nothing to do with that. Divided by. It's going to be concentration of Cr2O7 dinegative raised by stoichiometric coefficient 1. And this is going to be concentration of H positive raised by stoichiometric coefficient, that's 14. This is how you write the QC expression. Correct? Now tell me one thing. Concentration of Cr tripositive is given, this is given, but concentration of H positive is not given. But pH of the solution is given to me as 1. And you already know, if pH is equal to 1, what does that mean? That means concentration of H positive is 10 raised power minus 1 molar. Right? If pH is X, so concentration of H positive becomes 10 raised power minus X. Right? So, put the values here. Cr tripositive concentration is given to me, I believe, 2 into 10 raised power minus 2. So 2 into 10 raised power minus 2 raised power 2 divided by concentration of Cr2O7 dinegative given to me as per the equation, 4 into 10 raised power minus 4. Concentration of H positive, 10 raised power minus 1 raised power 14, right? I'll say this particular term gets cancelled out. So the final value is 10 raised power 14. So this is QC. This is QC, right? What was I supposed to calculate? As per the equation, I was supposed to calculate the reduction potential. Now we use the Nernst equation. ERED is equal to E naught RED, standard reduction potential. This is the standard reduction potential which is given. See, nothing is mentioned. Nothing is mentioned. Whenever nothing is mentioned, you'll be assuming it as standard reduction potential. When nothing is mentioned here, right? So assume it as SRP always. So SRP is 1.5 minus 0.0591 divided by n values 6 log of QC. QC value is 10 raised power 14, right? So m raised power n is n log m. So it is going to be 1.5 minus 0.0591 divided by 6 log of m raised power n is n log m. So 14 log 10. Log 10 is 1. So this particular term you have to solve. The answer is going to be in volts. So this is the reduction potential of the half cell which you were supposed to calculate. I hope this is clear to everyone. Let me know once in the chats quickly. Is this clear? Is this clear? Let me know once in the chats quickly, people. Everyone. Everyone. Perfect. Okay. Let's try to solve one more question. Look at this particular question. Read the question carefully first. I want you guys to read the question and let me know in the chats whether you can solve this question or not. Read it. A zinc rod is dipped in 0.1 molar solution of its salt at 25 degrees centigrade. Assume the electrolyte is 20% dissociated. Calculate the electrode potential. They're asking you to calculate electrode potential. They are not mentioning clearly whether to calculate oxidation potential or reduction potential. Whenever this kind of the scenario arises, you're supposed to calculate electrode potential. That means they are asking you to calculate the reduction potential. Okay? They're asking you to calculate the reduction potential. So can't you do it? What do you think? What do you think about this question? Can it be done? Quickly in the chats, can it be done? See guys, look at the questions clearly. Imagine this is the container. And in this particular container, what do we have? We have got salt of a zinc. Let's assume that we have got zinc sulfate. Imagine we have got zinc sulfate. Now tell me how zinc sulfate undergoes dissociation. Zinc di positive plus SO4 di negative, like this. Okay. Now we have introduced a zinc rod here. This is the zinc rod which you have introduced. So zinc rod you have introduced into a solution containing its own ions. So you'll be calling this whole setup as, this whole setup is your zinc electrode, right? Now, as per the question, you have to calculate the reduction potential of the zinc electrode. When? You have to calculate the reduction potential of the zinc electrode when 20% electrolyte is dissociated into its ions. When 20% electrolyte is dissociated into its ions, at that point of time, what will be the reduction potential of this electrode? Now guys, have a look. See, this is time t is equal to 0. At time t is equal to 0, what is the concentration of zinc sulfate that's given to me? The concentration of zinc sulfate is 0.1 molar. So C value is 0.1 molar, right? So this will be 0, this will be 0. Now, if you remember, we have discussed in equilibrium. After some time, this will be C minus C alpha. And this is going to be C alpha and this is going to be C alpha, right? Do you remember? If this is C minus C alpha, this has to be C alpha, this has to be C alpha. Stoichiometry is 1:1:1. Okay. Now, how much percentage of zinc sulfate should get dissociated? 20%. If 20% is getting dissociated, that means alpha value is 0.2. Alpha value is 0.2. Correct? So tell me, what will be the concentration of zinc di-positives in the container when 20% electrolyte is dissociated? When 20% electrolyte is dissociated, what is the concentration of zinc di-positive in the container? The concentration of zinc di-positive is C alpha. C value is given to us, 0.1. Alpha value will be how much? 0.2. So 0.1 into 0.2 makes it 0.02. Or you can write it as 2 into 10 raised power minus 2 molar. So this is the concentration of zinc di-positive in the container when 20% electrolyte has got dissociated into its ions. I hope this is clear. Now tell me one thing. What are we supposed to calculate? We are supposed to calculate the reduction potential. For the reduction potential to be calculated, we'll make sure that electrode behaves like the cathode, because at cathode only reduction takes place, right? Now what should be the reduction reaction? Reduction means gain of electrons. So I would say the zinc di-positives which are there in the container, they'll collide with the rod, right? The zinc di-positives which are there in the container, they will be colliding with the rod, will be taking 2 electrons from the rod and getting converted into zinc solid. So this has to be the reaction. Now if I ask you how many moles of electrons are exchanged, how many moles of electrons are exchanged? So basically I'm asking you the N value. N value is 2, right? Okay, what about QC value? QC is equal to, start with the product. It's zinc solid. Its active mass is unity. So 1 divided by, it's going to be concentration of zinc di-positive, raised power stoichiometric coefficient. So it is 1 divided by, what is the concentration of zinc di-positive? What do we need to calculate? We need to calculate the reduction potential of the half cell when 20% electrolyte is dissociated. Now tell me one thing. What is the concentration of zinc di-positive when 20% electrolyte is dissociated? That is 0.02, right? That is 0.02. This value comes out to be 50. Right? This value comes out to be 50. So QC value I got. QC value I got. Right? Now if I got the QC value, I'll be simply writing the Nernst equation. Nernst equation says that ERED is equal to reduction potential of the half cell is equal to E naught RED, standard reduction potential. Check this particular value. Is this SRP or SOP? Plus 2 to 0. Plus 2 to 0 means decrease in the oxidation state, reduction. So this is SRP, right? And I need SRP only. So minus 0. So it is minus 0.76. So this is E naught RED minus 0.0591 divided by N value is 2, and it's going to be log of QC. QC value is how much? QC value is 50. 50 can be written as 5 into 10. Okay. So now it's just a matter of calculation. I'm just breaking it a bit. Then calculation part you will do on your own. So this 0.0591 divided by 2. Log of M into N. Log of M into N is log of M plus log of N. Log of 5 is 0.69 plus log of 10 is 1. Right? Just do this calculation and get the value of reduction potential of this particular half cell in volts. Right? Is this clear? Is this particular question clear to you? Will you be able to solve this sort of a question as well? Someone is saying, sir, what you are doing is not live. I know you're looking at the time. This time is wrong, right? I know it is 7:17 at this point of time, but over here it's mentioning as 6:47. Since long it's like this. Perfect. Okay, let's have a look on one more type of the question. See, if the question is asked in the NEET from the electrode potential, this can be the toughest question which can be asked in the NEET examination, right? Okay, this can be your tough question which can be asked in the NEET examination, because in this question you'll be using the concepts of equilibrium as well. And have a look how exactly this particular question is to be solved. Understand properly. The question is, calculate the reduction potential. Calculate the reduction potential at pH equal to 14. Calculate the reduction potential at pH equal to 14 for this half cell. For this half cell at 25 degrees centigrade. KSP is given. E naught of something is also given. So basically, as per the question, we are given with the copper electrode. We are given with the copper electrode, and we need to calculate its reduction potential. Now, in order to calculate the reduction potential, should I make sure this copper electrode behaves like the cathode or anode? I'll make sure it behaves like the cathode, because at cathode only reduction takes place, and I'm supposed to calculate reduction potential only, right? So let's assume that this copper electrode is behaving like the cathode. When it behaves like the cathode, what's going to happen? Reduction, right? Reduction means gain of electrons. So I'll say copper dye positives in the solution, they'll be gaining 2 electrons, and they will be getting converted into copper solid. This is the reaction which is going to happen. This is the reaction which is going to happen. This is your reduction reaction. This will only happen when the copper electrode behaves like the cathode, right? So I'm making sure that copper electrode behaves like the cathode. Now tell me one thing. What is the N value? N value you already got. What about QC value? QC value is going to be 1 divided by concentration of Cu dye positive. But my dear students, as per the question, do you see anywhere the concentration of Cu dye positive given to us? Do you see concentration of Cu dye positive anywhere given? No, right? So we have to calculate concentration of Cu dye positive with the parameters, from the parameters which are given to us. Whatever parameters are given to us, just use them and get the concentration of Cu dye positive, because we have to write QC. Okay. Now what all things I'll be doing? Have a look. As per the question, pH is given to us as 14, right? Now, if pH is 14, you know at 25 degrees centigrade, pH plus pOH, this value is 14 at 25 degrees centigrade. Must be knowing this, right? If pH is 14, from here, I'll be calculating pOH. pOH will be 0, right? pOH will be 0. If pOH is 0, what will be the OH negative concentration? It's going to be 10 raised power minus 0. That is going to be 1. So OH negative concentration I could calculate from here. But why do I need OH negative concentration? Have a look. My dear students, KSP of COH whole twice is given. Tell me how the COH whole twice will undergo dissociation. The COH whole twice, how it will undergo dissociation? It will undergo dissociation as Cu dye positive plus what? Plus 2 times OH negative. This is how it will undergo dissociation, right? Now, if I ask you to write the KSP expression, can't you write the KSP expression? It's going to be concentration of Cu dye positive raised power stoichiometric coefficient, multiplied by concentration of OH negative, raised power stoichiometric coefficient. This is how you write KSP expression. Okay. Now, as per the question, is KSP value given? Absolutely, it's given to me as 10 raised power minus 19 is equal to concentration of Cu di positive raised power 1. What about OH negative concentration? OH negative concentration is given to us as 1 molar. I mean, this was not given. I calculated it. Now, you would understand why did I calculate it, right? Because I was supposed to get the concentration of Cu di positive. So finally, I got the concentration of Cu di positive as 10 raised power minus 19 molar. Perfect. Why did we calculate the Cu di positive concentration? To get the QC. So it's 1 divided by 10 raised power minus 19. So the value has to be 10 raised power 19. Okay. So this is your QC. This is your QC. Perfect. This is your QC. Clear? Since you calculate QC, you have N value. What are we supposed to calculate? We are supposed to calculate the reduction potential. Use the Nernst equation. ERED is equal to E naught RED, standard reduction potential. Look at this particular value. Plus 2 to 0. Plus 2 to 0. Decrease. Decrease means reduction. So this SRP only, right? So 0.34 minus 0.0591 divided by N value. N value is 2 and it's log of QC. And QC already, you know, it's 10 raised power 19. Right? Yes. So it's done, right? So it is 0.34 minus 0.0591 divided by 2. Log of m raised power n. Log of m raised power n is n log m, right? So it's going to be 19 log 10. Log 10 is 1. Just solve this particular part. Get the answer in volts. That's the reduction potential of the half cell which I was supposed to calculate. Is this clear? Let me know once in the chats quickly if this is super clear to everyone. Yeah? Everyone in the chats, people. Everyone. Everyone means everyone. Quickly. I said, do you need some lectures of organic chemistry as well? Do you need some lecture? Because physical is almost done, right? You're almost complete physical chemistry. Tell me in the chats with yes or no. Let me know in the chats with yes or no, quickly. Organic or inorganic? Which one? Organic or inorganic? Which one? I want every one of you to say it. Just write it. It's just going to take 2 seconds to write it. Just write it, what you want exactly. Organic or inorganic? In inorganic chemistry, we have already completed bonding, if you remember, right? Okay. So I'll take some of the chapters of inorganic also. Let's start then inorganic with the first chapter, periodic classification. Okay. All right. Chalo, got it. Let's move on to one more question now. Let's move on to one more question and then we shall be discussing a few more concepts. Just a second. Can you solve this particular question? Look at it carefully. Look at this question. Look at this question right now. Look at this question. Look at this question. You're given with a reaction. In this particular reaction, if you observe, 1 electron is gained here. Gain of electrons is a reduction. So this is a reduction, right? This is SRP that's given, right? Calculate the reduction potential in neutral solution. We are supposed to calculate the reduction potential. Now, in this particular question, you're not supposed to write the reaction. The reaction is already given to us, right? So directly do one thing, write QC expression. Right? QC expression. Start with the product. It's partial pressure of NO2 raised by its stoichiometric coefficient, that's 1. H2O is a liquid state, nothing to do with that. Divide by concentration of NO3 negative raised by its stoichiometric coefficient and its concentration of H positive raised by its stoichiometric coefficient. Correct? Now, partial pressure of NO2, we already know. How much is that? 1 bar. Divided by concentration of NO3 negative, that's 1 molar. Right? What is H positive concentration? Well, H positive concentration is not given in the question, but you are given with the pH. If pH is 7, that simply tells you H positive concentration is 10 raised per minus 7 molar. Right? It is 10 raised per minus 7 molar. So, this is 1 multiplied by 10 raised per minus 7 raised per 2. The overall value at the end comes out to be 10 raised per 14. So, this is your QC. This is your QC, right? If you got the QC value, how many moles of electrons are exchanged? 1 mole of electron and value is 1. Now, write the Nernst equation. So, I'll be writing reduction potential of the half cell is equal to E naught RED, standard reduction potential, which is 0.78 minus 0.0591 divided by N value. N value is 1 log of QC. QC value is what? QC value is 10 raised per 14. Perfect. So, it is 0.78 minus 0.0591, right? It's going to be log of m raised per n, which is 14 log 10. Log 10 is 1. Just solve this equation and get the answer exactly in what? Get the answer exactly in volts. I believe that you can solve each and every question in which you are supposed to calculate oxidation potential and reduction potential of what? Of the half cells, right? So let me know once in the chats. Let me know once in the chats quickly. Let me know once in the chats quickly. Is everything done? So till now, we exactly saw how to write the Nernst equation for half cells and how do we calculate the oxidation potentials and reduction potentials of the half cells under non-standard conditions, right? What are you saying, sir? Rate reaction must be negative. Must be minus change or not chemical. I'm not getting what you're trying to say. Just be clear with the words. I'm unable to understand what you're asking. All right, guys. So let's move on now. Let's move on to one more topic, that is Nernst equation for complete reversible cells. Nernst equation for complete reversible cells. Now guys, try to understand. So till now I was showing you how to write the Nernst equation for half cells, right? Why do we need Nernst equation for half cells? To calculate the oxidation or reduction potential of the half cell under non-standard condition. Now you'll be given with a full cell. Full cell means complete galvanic cell, you mean, right? In which you have got 2 electrodes and both the electrodes are connected externally as well as internally. Perfect. And imagine like this. Let's say this is the salt bridge. On the left side of the salt bridge, there is anode, and the anode is like this, zinc solid. Let's say it gives zinc dipositive aqueous, right? On the right side, there is cathode. So let's say this copper dipositive aqueous, it gives copper solid. So first of all, this is your Daniell cell, right? This is your Daniell cell. Now let me show you how do you, this is your Daniell cell. It's a galvanic cell basically. It's one complete cell in which 2 electrodes are used. It's one complete cell in which 2 electrodes are used basically. Now, the point is, how do we write the Nernst equation for complete cells? Okay. My dear students, why do we need the Nernst equation for complete cells? To calculate EMF of a complete cell under non-standard condition. To calculate EMF of a complete cell under non-standard condition, what do I need? I would need the Nernst equation. How exactly are you going to write it? First thing, I'll be writing the reaction at anode. What will be the reaction taking place at anode? Zinc getting converted into zinc dipositive. 0 to plus 2. Increase means oxidation. You know it already. You have discussed this. So reaction at anode is like this. Zinc solid. It gives zinc dipositive aqueous. And with that, you'll be writing 2 electrons. This is the reaction at anode. Similarly, if I ask you what about the reaction at cathode? At cathode, reduction takes place. Copper dipositive gives copper solid. So it is copper dye positive aqueous, right? Plus 2 electrons. It gives copper solid. So this is the reaction at cathode. Now, in both the reactions, electrons are balanced. Now you can directly add these two reactions. You can directly add these two reactions. When you add these two reactions, what do you get? What do we get? So 2 and 2 gets cancelled. So my net reaction becomes zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous plus what? Plus copper solid. This is the net reaction. This is the net reaction. If I ask you how many moles of electrons are exchanged, you'll directly say 2 moles of electrons are exchanged in the net cell reaction. Now after that, I would want you guys to write the QC expression. QC is going to be concentration of zinc dye positive raised by stoichiometric coefficient, that's 1, divided by concentration of Cu dye positive raised by stoichiometric coefficient, that's 1. Right? So this is how you get the QC. After you get the QC, then calculate the E0 cell as well. How do you get the E0 cell? That is your E0 of cathode minus E0 of anode. So SRP of cathode minus SRP of anode. SRP of cathode minus SRP of anode, right? Yes. Now, my dear students, after writing all these things, after getting all these things here, after getting all these things, what do I need to write? At the end, I'll be writing the Nernst equation. And Nernst equation I'll be writing in this format. E cell, which is EMF of the cell, under non-standard conditions, is equal to E0 cell minus 0.0591 divided by N, then it's going to be log of QC. The E0 cell, you would have calculated, right? Because E0 cathode, E0 anode, it will be given to us as per the equation, right? So E0 cell we can calculate, N value we can calculate, QC we have calculated. So put all the parameters here and get the value of E cell basically, right? So this is how you use your Nernst equation to calculate EMF of the cell, right? Perfect. Is this clear? Happy birthday, sir. Whose birthday is it? Is it my birthday? I have no idea. So guys, let me know once in the chats. All the things are clear till here? Are all the things clear? Did you get the idea of how Nernst equation is used? All right. So let's exactly try to see some questions through which you'll get the idea how Nernst equation is used for the complete cells. For example, this is the question. This is the question on your screen. Let's see how this sort of equation is to be solved. Calculate the EMF of the cell. You are given with a cell in which you have used 2 electrodes, right, which are separated with the help of salt bridge. Anode, cathode, right? Now you are supposed to calculate the EMF of this particular cell over here. You are supposed to calculate EMF of the cell. Now, my dear students, it is one complete cell, and you already know how do we calculate EMF of a complete cell. We do it with the help of Nernst equation, and you exactly know the steps to be followed. You exactly know the steps to be followed. So first of all, I'll be writing the reaction taking place at anode. Tell me what will be the reaction at anode. Tell me what will be the reaction at anode. So at anode, oxidation will take place. Tin is getting converted into SN dye positive. So I would say SN solid will be getting converted into SN dye positive aqueous, and with that you'll be writing 2 electrons. This is the reaction at anode. Similarly, reaction at cathode. Reaction at cathode. Pb dye positive is getting converted into Pb solid. So the reaction has to be. Pb dye positive has to get converted into Pb solid, right? So the reaction has to be, I would say, Pb dye positive aqueous plus 2 electrons. Plus 2 electrons. It has to get converted into Pb solid. So So this has to be the reaction at cathode. Now, you got reaction at anode, you got reaction at cathode. If I ask you what about the net reaction? What about the net reaction? So you'll be directly adding them up. When you add them up, this 2 and 2 gets cancelled out, right? So my net reaction has to be SN solid plus PB di positive aqueous. It gives SN di positive aqueous plus PB solid. So this is your net reaction. Okay. Now you are going to write the QC expression. So start with the product. It's going to be concentration of SN di positive raised by stoichiometric coefficient. This is solid, its active mass is 1 divided by. It's going to be concentration of PB di positive, right? Raised by stoichiometric coefficient. Now, as per the question, are we given with the concentration of tin di positive and PB di positive? Concentration of SN di positive is given to us as 1 molar divided by. Concentration of PB di positive is 10 raised by minus 3 molar. So the overall value comes out to be 10 raised by 3. So this is QC. So QC you calculated, right? After calculating QC, you'll be calculating E naught cell. How do we get the E naught cell? E naught cell is going to be E naught of cathode minus E naught of anode, right? Now, which one is your cathode and which one is your anode? Cathode is lead, anode is tin, right? So SRP of cathode, SRP of lead, this is the SRP of lead, which is minus 0.13, minus SRP of anode, SRP of tin, SRP of tin is minus 0.14. The value exactly comes out to be how much? 0.01 volt. So this is your E naught cell as well. So you have calculated E naught cell as well. Perfect. Now, my dear students, all the parameters which are needed in the Nernst equation, you have already calculated them. Now you can directly use the Nernst equation. E cell is equal to E naught cell 0.01 minus 0.0591 divided by N value, that's 2. N value is 2 because 2 moles of electrons are exchanged here, right? So N value is 2. So it's going to be divided by N log of QC. QC value is already 10 raised by 3. So finally it has to be 0.01 minus 0.0591 divided by 2 log of M raised by N, which is N log M. So 3 and log 10 is 1, right? So solve this equation, get the answer exactly in volts. So EMF of the cell is going to be this particular term over here. Yeah? Is this clear to everyone quickly? Let me know once in the chats, people. Is it clear? Perfect. Let's try to see a few more questions so that you can master it properly. For example, guys, you have this sort of a question. Look at this particular question carefully. As per the question, this is the salt bridge. On the left side of it, you have got anode. On the right side of it, you have got cathode. So what are we supposed to calculate? We are supposed to calculate EMF of the cell. EMF of this complete cell. EMF of this particular complete cell. So first of all, what I'll be writing? I'll be writing reaction at anode. At anode, oxidation takes place. Your anode is your hydrogen electrode. And you know when hydrogen electrode behaves like the anode, this has to be the reaction. H2 gas gives 2 times H positive aqueous plus 2 electrons. So this has to be the reaction. Right? Already discussed. So H2 is getting converted into H positives. So this has to be the reaction at anode. Similarly, reaction at cathode. At cathode, you can see iron tri-positive is getting converted into iron di-positive. So I would say iron tri-positive aqueous will be gaining 1 electron and will be getting converted into Fe di-positive aqueous. Perfect. So this is the reaction at cathode. We got reaction at anode, reaction at cathode. Now if I ask you whether the electrons are balanced in both the reactions or not, the electrons are not balanced yet. So this is 2, this is 1. So it's time to balance the electrons. So multiply this particular reaction by number 2. So this has to be 2 times, this has to be 2 times, even this has to be 2 times. Now you can add these 2 reactions directly. And when you add these 2 reactions, what do we get? We get something like this. H2 gas plus 2 times Fe tri-positive aqueous. What does it give? It gives 2 times H positive aqueous. And with that, you get 2 times Fe di-positive aqueous. This is your net cell reaction. This is your net cell reaction. Okay. Now, if I ask you how many moles of electrons are exchanged, you directly say 2 moles of electrons are exchanged in the net cell reaction. So write the expression for QC now. Write the expression for QC. Start with the product. It's going to be concentration of H positive raised power 2, and it's going to be concentration of Fe di positive, raised power 2 divided by partial pressure of H2 gas raised power stoichiometric coefficient 1, and with it concentration of Fe tri positive raised power stoichiometric coefficient. Now concentration of H positive. H positive concentration is how much? 10 raised power minus 3. Raised power 2 comes out to be 10 raised power minus 6. Right? Fe di positive concentration 0.01, which is 10 raised power minus 2. Raised power 2 comes out to be 10 raised power minus 4 divided by partial pressure of H2 gas 10 raised power minus 1. Concentration of Fe tri positive 0.1, that means 10 raised power minus 1. Raised power 2, that means 10 raised power minus 2. So in the numerator you have got 10 raised power minus 10. In the denominator you have got 10 raised power minus 3. So the overall value is 10 raised power minus 7. So this is QC. You have got the QC as well. Okay. Since you got the QC, now it is the time to calculate E naught cell. E naught cell has to be equal to E naught cathode, SRP of cathode. So SRP of this particular electrode is a given. Well, it is Fe di positive gives Fe tri positive. So increase in the oxidation state. So this is SOP, but I need SRP. SRP will be 0.17. SRP of cathode minus SRP of anode. Anode is your hydrogen electrode. Its SRP is 0, right? E naught cell is 0.17 volt. Now all the parameters which are needed to write the Nernst equation, we have wrote that. So what I'll be doing now? I'll be using the Nernst equation. I'll say E cell is equal to E naught cell minus 0.0591 divided by N value is 2, and it's going to be log of QC. QC value is how much? QC value is 10 raised power minus 7, right? Now it's just a matter of calculation. 0.17 minus 0.0591 divided by 2. Log of m raised power n is n log m. So minus 7 comes to the front. Log 10 is 1. You can solve it and get the answer exactly in volts, right? I hope this sort of equation you can easily solve again from now onwards. Is it clear? Let me know once in the chats quickly. Perfect, guys. Okay. Look at this particular question. Look at this particular question now. See, guys, the EMF of the cell is given. EMF of the cell is given 0.81 volts. Calculate the charge on the metal. Calculate the charge on the metal. Okay. See what the question says basically. See what the question exactly says. As per the question is concerned, M is getting converted into Mn positive, right? M is getting converted into Mn positive. So basically, as per the question, we are supposed to calculate the charge present on the metal ion, right? We have to get this particular N value, the charge present on the metal ion. Now, again, I'll be using the same procedure, whatever I have been doing till now, same procedure, similar procedure I'll be doing, and definitely you will be able to solve this question as well and see how exactly. First of all, what has to be the reaction at anode? M gives Mn positive. So the reaction has to be M solid. It gives Mn positive aqueous plus how many electrons? Plus N electrons. This is the reaction at anode. Similarly, reaction at cathode, H positive gives H2. So the reaction has to be 2 times H positive aqueous, since hydrogen electrode is behaving like the cathode. And when it behaves like the cathode, the reaction has to be like this. This is your H2. Perfect. So you got the reaction at anode, you got the reaction at cathode as well. Now, my dear students, if I ask you whether the electrons are balanced or not, the electrons are not balanced in both the reactions. Here you have got n electrons, here you have got 2 electrons. So I'll be multiplying this reaction by number 2. I'll be multiplying this reaction by number n, right? So after multiplying, what do I get? This is 2 times, this is 2 times, and this is 2n times. This will be 2n times, right? This will be 2n times. Perfect. And this is also going to be 2n electrons, and this is going to be n times H2. Okay. Now is the time to add these 2 reactions. When I add these 2 reactions, what do I get? I get 2 times metal solid plus 2n times H positive aqueous. It gives what? It gives 2 times Mn positive aqueous 2 times Mn positive aqueous plus N times H2 gas. So this is your net reaction. Now, if I ask you how many moles of electrons are exchanged in the net cell reaction, will you say N or 2N? I'll say 2N moles of electrons are exchanged. I'll say 2N moles of electrons are exchanged in the net cell reaction. Now tell me one thing, whether you can write the expression for QC or not. Absolutely. It's going to be concentration of Mn positive raised power stoichiometric coefficient 2. This is going to be partial pressure of H2 gas raised power stoichiometric coefficient, that's N, divided by, this is solid, leave it. This is H positive concentration raised power stoichiometric coefficient, that's 2N. So this is how you write QC. This is how you write QC. Now tell me one thing, whether the concentration of Mn positive is given or not. 0.02 molar, which means 2 into 10 raised power minus 2. Raised power 2 means 4 into 10 raised power minus 4. Right? Partial pressure of H2, that's 1. Concentration of H positive, that's also 1. 1 raised power anything is 1. So QC value I directly got. Okay. Now as per the question, let's try to calculate E naught cell. E naught cell is E naught of cathode. Cathode is your hydrogen electrode. Its SRP is 0 minus SRP of anode. SRP of this particular electrode. Look at this. M gives Mn positive. M gives Mn positive. So 0 to plus N. Increase in the oxidation state means oxidation. So this SOP. But what do I need? I need SRP. So this is minus 0.76. So this value is equal to 0.76 volts. So this is your E naught cell as well. Right? So I believe all the parameters are calculated. Now it is the time to use the Nernst equation. What you'll be writing? You'll be writing E cell is equal to E naught cell. Right? E cell is equal to E naught cell minus 0.0591 divided by N. But here you are not going to use N. Here you will be writing 2N because 2N moles of electrons are exchanged. Then you will be writing log of QC. Correct? So E cell value as per the equation, that's 0.81 is equal. E naught cell is 0.76. So 0.81 minus 0.76. How much that comes out to be? That comes out to be 0.05. Right? 0.05. Now multiply that 0.05 with 2N and divide that with 0.0591 will be equal to minus log of QC. Right? I just simplified things, nothing else. I just simplified the things. So it is going to be 0.1 divided by 0.0591 is equal to minus log of QC. Right? Minus log of QC. I think one term is missing, that's N, right? That's N. QC as per the equation is given to us. QC as per the equation is given to us. How much? QC, I mean, we have calculated QC and where the QC is 4 into 10 raised per how much? 4 into 10 raised per minus 4, right? Now do one thing. This minus is here, right? This minus, take it on the other side. Take it on the other side. Now, do a bit of calculation now. Log of m into n is log m plus log n. So log of 4 is 0.6 and this is going to be log of 10 raised per minus 4 is, this is going to be minus 4. So this overall value comes out to be minus 3.4. This overall value comes out to be minus 3.4, minus 3.4. So minus gets cancelled out. So n value will be equal to 3.4 multiplied by 0.0591 divided by 0.1. And approximately, this one is 1, approximate calculation. This one is approximately 2. So approximately n value is coming out to be 1.7. But what is n basically? N is the charge on the metal ion, right? So n value is coming out to be 1.7. Can charge be 1.7? Charge cannot be 1.7, right? It has to be the integer. I mean, it has to be the natural number. So which one is the closest natural number? That's 2, right? So I would say n value is coming out to be 2. That means the charge on this metal ion over here. The charge on this metal ion over here has to be exactly 2. So that's something which we were supposed to calculate. Is this clear now? Is this clear to everyone, people? Quickly. Perfect. I believe you can solve these sort of questions from now onwards, okay? I believe you can solve these sort of questions from now onwards. Let's look at one more topic that's again important. What is it? Nernst equation at equilibrium. what is meant by Nernst equation at equilibrium. What is first of all meant by equilibrium stage? Let's try to understand it. My dear students, if you remember, we have discussed Daniell cell long back, right? We have discussed Daniell cell. I'll just use the Daniell cell to make you understand what equilibrium conditions exactly are. Try to understand. This is the container, right? This one container. And this is one more container. Over here, which electrolyte you have? You have got zinc sulfate. In this particular container, which electrolyte you have? You have got copper sulfate. In this particular container, you are keeping zinc rod, and here you are introducing copper rod. Here you are introducing copper rod. So you have got two electrodes, zinc electrode, copper electrode. Now, my dear students, you are connecting them with the help of what? With the help of ammeter, right? And this is your salt bridge. So this cell I'll be calling as the Daniell cell, right? This cell I'll be calling as Daniell cell. And in Daniell cell, we have discussed in Daniell cell, your zinc electrode behaves like the anode and your copper electrode behaves like the cathode. That's something which we know already. We have discussed that, right? We have discussed that. Your copper electrode, it behaves like the cathode. And your zinc electrode, it behaves like the anode. Okay? Now guys, tell me one thing. For the copper electrode to behave like a cathode, right? For the copper electrode to behave like the cathode, can I say SRP of copper should be more than that of SRP of zinc? Because at cathode, reduction takes place. At cathode, reduction takes place. Can I say copper electrode can only behave like cathode if its SRP would have been more? Absolutely, absolutely. Imagine that. I'm giving you arbitrary numbers. Imagine that SRP of cathode here is 5 volts and SRP of anode here was 1 volt. Imagine, just to make you understand things first. Imagine the SRP of copper electrode was 5 volts, the SRP of zinc electrode was 1 volt. Now, which one has got more SRP? Copper. The one which has got more SRP will easily undergo reduction, and the reduction happens at cathode. So your copper is behaving like cathode and your zinc is behaving like anode right now. Okay. Now guys, tell me one thing. Tell me one thing. Well, these are the arbitrary SRP values which I gave you, just to make you understand, right? Just to make you understand. Just to make you understand. Now tell me one simple thing. When this cell will start working, when the cell starts working, what happens at anode? Oxidation takes place. Oxidation means loss of electron, right? The zinc rod is made up of zinc atoms. The zinc rod, it is made up of zinc atoms, and those zinc atoms will undergo oxidation. Those zinc atoms will get converted into zinc dipositives, and those zinc dipositives will enter into this solution. And when zinc dipositive enter into this solution, at the same time, from the salt bridge, SO4 negative will come and neutralize that. So just tell me one thing. When the cell works, when the reactions takes place at anode and cathode, due to the reaction at anode, what is happening to the concentration of zinc sulfate? Is the concentration of zinc sulfate in the left container increasing or decreasing? What do you think? Is the concentration of zinc sulfate in the left container increasing or decreasing? Since in the left container, what's happening? Oxidation. Zinc atoms are oxidized, getting converted into zinc dipositive. That zinc dipositive enters into this container. And when the zinc dipositive enters into the container, at the same time, from the salt bridge, SO4 negative will come, will neutralize it. So in the left container, I must say, the concentration of zinc sulfate increases with time, right? The concentration of zinc sulfate increases with time in the left container. Whereas in the right container, what happens? Reduction. Reduction of what? Since in this particular container, you have got two types of ions, copper dipositive, SO4 negative. Those copper dipositives will collide with the rod, will take 2 electrons from the rod, will get converted into copper solid, and that copper solid gets deposited on the rod, due to which in this container, the concentration of copper dipositives, in the right container, is it increasing or decreasing? It's decreasing. So eventually I'll say the concentration of electrolyte in the right container is decreasing. So when the cell starts working, the concentration of electrolyte in the left container, that is increasing. Concentration of electrolyte in the right container, that is decreasing. Correct? And a few minutes back, when I taught you Nernst equation, I told you one simple thing. When the concentration of electrolyte increases, reduction potential of electrode increases. Reduction potential of electrode increases. With the increase in the concentration of electrolyte, reduction potential of the electrode increases. With the decrease in the concentration of electrolyte, reduction potential decreases. This is something which I discussed with you a few minutes back. So my dear students, initially the arbitrary value which I gave you, what was the reduction potential of zinc? That was 1 volt. What was the reduction potential of copper? That was, for example, 5 volts. Now when the cell starts working, concentration of electrolyte here increases. If concentration of electrolyte increases in the left container, I would say the reduction potential of zinc will start increase. The reduction potential of zinc will start to increase, right? So the reduction potential of zinc will start to increase when the cell will start working. The reduction potential of zinc will start to increase when the cell starts working, right? So earlier it was 1 volt, now it will increase with time. Similarly, the concentration of copper sulfate in the right container, it decreases. Therefore, the reduction potential of copper will decrease with time. So reduction potential of zinc increase with time and reduction potential of copper that decrease with time. Can I say a stage will come at which the reduction potential of both the electrodes will be same? A stage will arise at which the reduction potential of both the electrodes will be the same, right? Or in general, I'll say a stage will come at which the electrode potential of both the electrodes will be the same. At that point of time, will there be any potential difference between the electrodes? There will be no potential difference between the electrodes. And that particular stage in the cell where the potential difference becomes zero because of same electrode potential of both the electrodes, that particular stage is something which you call as equilibrium stage. I hope you got to know what I exactly said. So what I'm going to conclude, I'll say at equilibrium. At equilibrium, the reduction potential of both the electrodes have become equal. If reduction potential of both the electrodes have become equal, that means their oxidation potentials will be also equal. So in general, I'll say electrode potentials are same. At equilibrium, electrode potentials of both the electrodes will be same. Therefore, the potential difference will be equal to 0. If potential difference is equal to 0, if E cell is equal to 0, delta G for the cell is minus N of E cell, right? If E cell is 0, so delta G for the cell becomes 0. And at this particular point of time, will there be any current drawn from the cell? I'll say no current is drawn from the cell because potential difference of the cell has become 0, right? Potential difference of the cell has become 0. Now, my dear students, if you look at your Nernst equation, if you write your Nernst equation at equilibrium, so first of all, Nernst equation is nothing. That is E cell is equal to E naught cell minus 2.303 P divided by NF. And it used to be log of QC. This was the general form of the Nernst equation. But if I write the Nernst equation at equilibrium, this term becomes 0. And at equilibrium, your QC is replaced by KC or KEQ, you can say. Right? At equilibrium, QC and K are equal. Right? Now, if I write the Nernst equation at equilibrium, you'll be writing it like this. E naught cell is equal to 2.303 RT divided by NF. And then it's going to be log of KEQ. So this is how you exactly write the Nernst equation at equilibrium. This is how you write the Nernst equation at equilibrium. Perfect. So with the help of this Nernst equation at equilibrium, we can calculate E naught cell with the help of this particular expression. We already know how to calculate E naught cell. That's E naught cathode minus E naught anode. That's one way of calculating E naught cell. This is one more way of calculating E naught cell. Just make sure the cell comes at equilibrium. At that point of time, you can write this equation through which you can calculate E naught cell. Right? Now, my dear students, you can use few more things as well. See, if you use T is equal to 25 degrees centigrade, which is 298 Kelvin. Right? If you take the value of F as 96500 coulombs, if R value is taken as 8.314 joules per Kelvin per mole, at that point of time, your Nernst equation looks like this. at that point of time, your Nernst equation, how it looks like, you'll be writing A cell is equal to 0.0591 divided by n. 0.0591 divided by n. Then it's going to be log of KEQ, right? This is your Nernst equation when the temperature is 25 degrees centigrade, right? That means 298 Kelvin. So this expression also you can remember. Now, my dear students, there is one more thing. Do you remember I gave you one equation long back that was delta G is equal to delta G naught plus RT ln of QC. This was the equation which I gave you long back. Now, if I write the same equation at equilibrium, you know, at equilibrium, your delta G is 0 and QC is replaced by what? QC is replaced by KEQ, right? Now, if you write this particular equation at equilibrium, so delta G is 0 and QC is replaced by KEQ. So from this particular equation, what do I get? I get delta G naught is equal to minus RT ln of KEQ, right? This is one more expression. To calculate delta G naught, one of the expression to calculate delta G naught was minus NF E naught cell. So this is one more expression of calculating delta G naught. Well, you can convert it in terms of what? In terms of logarithmic form as well. You can say delta G naught is equal to minus 2.303. This is RT and it's a log of KEQ. Log of KEQ. Perfect. So these are certain expressions which are valid when the cell is at equilibrium, right? Perfect, guys. Is every single thing perfect till here? I believe every single thing is perfect till here, right? Okay, for example, I'm giving you a question. Let me make a question like this. Calculate the equilibrium constant for the following. Calculate the equilibrium constant for the following. Let's say the reaction is like this. Zinc solid plus cadmium dye positive aqueous. Let's say it gives cadmium solid plus zinc dye positive aqueous. Let's say this is the reaction which is given to me. And for example, E naught cell is equal to, let's say E naught cell is equal to, just a second. Let's say E naught cell is equal to 0.46 volts. Okay, you have to calculate equilibrium constant. Can you give it a try and solve this question? See guys, first of all, you have to calculate equilibrium constant. Well, in order to calculate the equilibrium constant, this cell has to be at equilibrium. Right? And when this cell attains equilibrium, I'd say E cell is equal to 0. If E cell is equal to 0, at that point of time, you can use the equation which we got a few minutes back only. E naught cell is equal to 0.0591 divided by n, and then it's going to be log of KEQ, right? E naught cell is given. What is n value? N value will be 2 for this reaction. N value is 2. From here, you can easily calculate KEQ. So one equation, one unknown, nothing to do, right? These are very simple questions. Similarly, this is one more simple question. Similarly, these are basic questions, right? These, I believe, you can do on your own. Calculate delta G for the reaction. When concentration of every ion is 1 molar, temperature is 298 Kelvin. So guys, one thing you have to agree here. If concentration is 1 molar, temperature is 298 Kelvin. Believe the pressure is 1 bar. That means the conditions which are given to us, these are standard conditions. So we have to calculate delta G under standard conditions basically. We have to calculate delta G under standard conditions. And delta G under standard conditions is what? That's basically delta G naught. And delta G naught is what? Minus NF E naught cell. Minus NF E naught cell. So first of all, what do I need to get? I need to get E naught cell basically. I need to get E naught cell. So what is E naught cell? E naught cell is something which is E naught of cathode minus E naught of anode. What is E naught of cathode? That's SRP of cathode minus SRP of anode. Now what is cathode? What is anode? Have a look. This is SRP of tin. This is SRP of copper. Which one has got more SRP? This one has got more SRP, right? Just a second. I think there is something wrong in this question. Yes, the values are not up to the mark. The values are not right. Either the reaction is given in the reverse format, or either the reaction is not right or the values are not right. Just a second. See, copper is getting converted into copper dye positive. So copper has to undergo oxidation. And tin is undergoing reduction. If tin has to undergo reduction, if this SN dye positive has to undergo reduction, so its SRP should be more, right? SRP of SN dye positive, this is SRP. This is also SRP. SRP of SN dye positive should be more, but here it's mentioned as less. So it's a wrong question basically. The values are wrong. Okay? The values are wrong. Perfect. Did you get what I'm trying to say? In the reaction, copper is undergoing oxidation, SN dye positive is undergoing reduction. For SN dye positive to undergo reduction, for SN dye positive to undergo reduction, the SRP of SN dye positive should be more, but here SRP of SN dye positive is less. So there is some discrepancy in the values, right? Anyways, leave the values aside. Leave the values aside. I'm just showing you the approach of the similar type of question which can be of this type. E naught cell you will calculate as E naught cathode minus E naught anode. This is SRP of cathode and this SRP of anode. So from here you can calculate E naught cell. E naught cell, F is 96500. N means number of moles of electrons exchanged, right? Here you will get the answer in joules. You will be dividing with 1000. Then you will be getting the answer in kilojoules. I believe this is clear. I believe this is clear to everyone. Okay? Perfect. So let's do one thing. Let's take a break here for some time. And after the break, we'll get back to the business again. So till what time? Till what time we are going to take the break? It's 8:08. So since it is the dinner time, so break till okay? Every one of you. Every one of you. This is for everyone. Be back on time because we have to complete this EMF part. Right? Well, after the break, it will just take like 1 hour or 1.5 hours, something like that. So let's complete it today only. Why to keep it for the next session? Okay? So be back at 8:35 sharp. Till then, you guys can have your dinner, etc., etc. See you. What's up, people? Are you back? Are you all back? Yeah? Everyone is here or not? Let me know in the chats quickly. Call up everyone. Call up everyone. Let's start. Are you guys done with your dinner, by the way? Are you all done with your dinner? Perfect. So, guys, there is one more important topic which we are going to cover now. That is concentration cells. Okay? Concentration cells. This again one important topic from which question can be asked, right? So let's get to know what exactly these concentration cells are, how many types of concentration cells we have, how do we exactly write the Nernst equation for the concentration cells. Let's get to know about all these things one by one. First of all, in case of concentration cells, what do we do? My dear students, in case of concentration cells, let me tell you a few points, then I'll make you understand one by one. In case of concentration cells, let me tell you two same electrodes are used. Two same electrodes are used. Till now, if you talk about the galvanic cell, in case of galvanic cell, we used to take two different electrodes. We used to connect them externally, we used to connect them internally, then we used to get one complete cell, right? So in the galvanic cells, till now, whatever galvanic cell we have studied, we used to take two different electrodes and connect them. But in case of concentration cells, we are not going to take two different electrodes. We are going to take two same electrodes, right? Point number one. So two same electrodes will be taken in case of concentration cells. Number one. Number two, EMF is, or let me write it like this, EMF of the cell is due to either concentration difference of anode and cathode, or the partial pressure difference between the anode and cathode. What exactly it means, you'll get the idea in some time. First of all, I would want you guys to take a note of these statements. In case of concentration cell, we'll be using two same electrodes. Now, EMF is generated in case of concentration cells due to either the concentration difference in anode and cathode, or due to partial pressure difference in anode and cathode. What this particular statement means, you'll get the complete information of it in some time. Just wait for it. You just tell me one thing. My dear students, if you are taking two same electrodes, for example, you are taking zinc electrode on one side. This is one more zinc electrode only. So these are two zinc electrodes. You are connecting them externally, you are connecting them internally. So you are getting a cell. If I ask you, if you are using two same electrodes, what will be the value of E naught cell? E naught cell is basically E naught of cathode minus E naught of anode. So SRP of cathode minus SRP of anode. Now cathode and anode, they are same, zinc and zinc. So SRP of cathode, SRP of anode. Since both the electrodes are same, so their SRP values will be also same. So first point which you need to know, that E naught cell, in case of concentration cells, do remember this particular value will be equal to 0. This particular value will be equal to 0, right? So in case of concentration cells, I'll be using two same electrodes, right? If you are using two same electrodes, you are connecting them externally as well as internally. You are getting a complete cell. Now, what about E naught cell for this particular complete cell? What about E naught cell for this cell over here? I would say E naught cell will be equal to E naught cathode minus E naught anode. Now, cathode, anode both are zinc electrodes. Their SRP value is same, right? So SRP of cathode, SRP of anode will be the same because both are zinc electrodes. So E naught cell will be equal to 0. So do remember, whenever from now onwards, you will see two same electrodes connected externally and internally, the first point which should come into your mind, that is the E naught cell value will be equal to 0. Okay. Now guys, let's try to analyze this a bit more in detail. But before that, let me tell you one more point. Try to understand what exactly I'm going to say. Okay, have a look, people. Have a look and understand. In order to understand these concentration cells in detail, let me first of all tell you, we divide these concentration cells into two categories. One is going to be electrolytic concentration cell, which we have to discuss in detail. The second one is going to be electrode concentration cell. Both these cells are to be discussed in detail. But right now, I'm just giving you the idea of few things which you are going to remember. In case of electrolytic concentration cells, what do we do? The concentration of anode and cathode. The concentration of anode and cathode are kept different. The concentration of anode and cathode are kept different. But in case of electrolytic concentration cells, in case of electrode concentration cells, partial pressure of what? Partial pressure of anode and cathode. Partial pressure of anode and cathode are kept different. Right? In case of electrolytic concentration cells, concentration of anode and cathode will be kept different, but do remember, partial pressure of anode and cathode will be kept same. Here, partial pressure of anode cathode will be kept different, but concentration of anode cathode will be kept same. This is the point which I want you guys to take a note of first of all. Now it is the time to discuss these concentration cells in detail, my dear students. Okay. So our first topic right here is going to be electrolytic concentration cell. So mark the heading as electrolytic concentration cell. Electrolytic concentration cell. This is the first important topic. Have a look, people. First of all, in case of electrolytic concentration cells, what do I exactly do? I'll be taking two same electrodes. Let me represent it over here. Imagine that this is one container. This is, for example, one more container. In this particular container, let's say we have got Mn positive ions. In this particular container also, we have got Mn positive ions. Let's assume the concentration of Mn positives in the left container is C1 molar. Let's assume the concentration of Mn positive in the right container is, for example, C2 molar. Okay. Now, my dear students, here what exactly I'm going to do? I'm keeping a metal rod. Here also what am I doing? I'm keeping a metal rod. So if I ask you whether the electrodes which I have taken, whether these electrodes are same or different, these are same electrodes. This is M electrode. This is also M electrode. Now, my dear students, I am going to connect these externally with the help of emitter, right? And here you are introducing a salt bridge. So what did we get? We got one complete cell which is made up of two half cells, right? Whenever you see this kind of the cell, whenever you see this kind of the complete cell in which two same electrodes are used, you'll be first of all calling it as the concentration cell. And in case of concentration cells, your E0 cell value has to be right now 0, right? Now, which type of concentration cell this is? My dear students, no doubt you have taken two same electrodes. Where is the difference? The difference lies in the concentration of electrolytes. Whenever you have such type of the concentration cell in which the concentration of anodic and cathodic container is different, you will be calling this particular cell, you will be calling this particular concentration cell as the electrolytic concentration cell. Okay. Now the first point, how do I represent this cell? My dear students, this is the salt bridge. On the left side of the salt bridge, I'll be writing the anode. At anode, your M solid is getting converted into Mn positive. And the Mn positive concentration in the left container, how much is that? That is C1 molar, right? Similarly, on the right side of it, I'll be writing the cathode. At cathode, your Mn positives will get converted into M solid. So Mn positives which were there in the right container, whose concentration was C2 molar, right? They will be getting converted into M solid. Perfect. So first of all, this is how you represent the electrolytic concentration cell, in which two same electrodes are used, but only difference is their concentration is different, right? This is your electrolytic concentration cell. Now, my dear students, the point is, what condition should be followed? What condition this particular cell has to follow so that it can behave like a normal galvanic cell? What kind of condition it has to follow? Let's try to make that condition. Which electrolytic concentration cell has to follow so that it can behave like the galvanic cell, right? So that it can work basically, so that it can produce current basically. Okay. Now try to understand. First of all, for this particular cell to be working, what should happen? At anode, oxidation should happen, right? So first of all, what has to be the reaction at anode? At anode, your M should get converted into Mn positive. So the reaction at anode has to be M solid should get converted into Mn positive with concentration C1 plus N electrons. This has to be the reaction at anode. Now similarly, what should be the reaction at cathode? What do you think? What should be the reaction at cathode? At cathode, reduction should take place. Mn positive should get converted into M. So the reaction has to be Mn positive aqueous with concentration C2 molar. It should gain N electrons and should get converted into M solid. Right? These are the two reactions which should happen first of all. Reaction at anode, reaction at cathode. Now, if I ask you whether electrons are balanced in both the reactions or not, just check it out. If I ask you whether electrons are balanced in both the reactions or not, absolutely in both the reactions, electrons are balanced. When you add them up, N electrons will get cancelled out. This M solid will get cancelled out. So what will be my net reaction? My net reaction here is Mn positive with the concentration C2. It should get converted into Mn positive with the concentration C1. So this has to be my net cell reaction. Okay. Now, my dear students, if I ask you what about the QC value? QC is going to be concentration of Mn positive, that is C1, divided by concentration of Mn positive, that is C2. C1 divided by C2. Simple. If I ask you what about the E0 cell value? E0 cell value will be equal to 0 only because we are using two same electrodes, right? Now comes a point. See guys, if I write Nernst equation for this electrolytic concentration cell, how the Nernst equation looks like? You will write E cell is equal to E0 cell. E0 cell is 0, right? Minus 0.0591 divided by N, and it's going to be log of QC. And QC is just C1 divided by C2, right? You can do one more thing. You can write the same equation like this as well. You can write E cell is equal to multiply this minus with this log it becomes 0.0591 divided by n. Now it becomes log of C2 divided by C. Right? Now it becomes log of C2 divided by C1. Now, my dear students, if you remember, I have told you in the last session, if you remember, for any complete cell to be working, for any complete cell to work like a normal galvanic cell, its E cell value should be positive. Then only delta G will come out to be negative. Right? We have discussed that in the last session. So for this particular cell to be working, I'll write for this particular cell to be working, E cell value E cell should be greater than 0. Right? E cell should be greater than 0. Then only this cell will be working. Then only with this cell is going to produce current. Then only this cell is going to behave like a normal galvanic cell in which current will go from cathode to anode. Right? Perfect. Now guys, the point is when this E cell value will come out to be positive. E cell value will only be positive if log of C2 divided by C1 will be positive. Now the point is, when this log of C2 by C1 will be positive, log of X is positive when X is greater than 1. So log of C2 by C1 will be positive when C2 divided by C1 is greater than 1. Right? Which is only possible if C2 is greater than C1. If C2 is greater than C1. So my dear students, if you try to analyze things properly, can I say I got to know something really interesting here? I'll write for an electrolytic concentration cell. For an electrolytic concentration cell to be working. For an electrolytic concentration cell, just a second. For an electrolytic concentration cell, I'll write involving which electrodes? Metal, metal ion. Involving metal ion electrode. For the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell. In which current is from cathode to anode. To be working like a normal galvanic cell, C2 value should be greater than C1. What is C2? C2 was the concentration of electrolyte in cathode. C1 is the concentration of electrolyte in anode. So I'll say concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. This is the condition which the cell has to follow, which this electrolytic concentration cell has to follow. Then only I can say its E cell value is positive. Therefore, the cell will be behaving like a normal galvanic cell, which electrons will move from anode to cathode and current will shift from cathode to anode. Is this point clear to everyone? Let me know once in the chats. Is this clear to everyone? So this is the first question which is asked. What is the question? The question is for the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell. The concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode, which is obvious also. If the concentration of electrolyte in cathode is more, since you are using two same electrodes, right? If you are using two same electrodes, how come potential difference will generate here? Potential difference will only generate if concentration of electrolyte in cathode is more, right? If the concentration of electrolyte in this container is more. Why is that? Because more the concentration, more the reduction potential. So this concentration should be more, this concentration should be less. If this concentration is more, that means reduction potential of this electrode is more and reduction potential of this electrode is less. If reduction potential of this electrode is more, this electrode is less. That means potential difference again got created. And whenever there is potential difference, current will be there, right? Then only I'll say the current will shift. Current will show its direction from cathode to anode, right? It's obvious. In case of normal galvanic cell, the direction of current is from cathode to anode. Now, how come this particular cell will behave like a galvanic cell? If the direction of current will be from cathode to anode, when can be the direction of current from cathode to anode? If this particular electrode behaves like the cathode, when this electrode behaves like the cathode, if its reduction potential is more, when its reduction potential will be more, when the concentration of electrolyte in this container is kept more. As simple as that. Okay, so this was our first point. Now comes the second point. In electrolytic concentration cell, there is something called as electrolytic concentration cell involving hydrogen electrodes. There is one special type of cell which is what you call as electrolytic concentration cell involving what? Involving hydrogen electrodes. Now, what this cell exactly looks like? Let's have a look. See guys, imagine that you have taken two hydrogen electrodes. You have taken two hydrogen electrodes, okay? You have taken two hydrogen electrodes. It is just the difference in the electrolytic concentration is different, but the partial pressure of hydrogen gas is same. So let me quickly represent this particular cell directly. So this is salt bridge. On the left side, it's going to be anode. So H2 gas at the pressure of, for example, P bar gets converted into H positive, gets converted into H positive aqueous, right? Whose concentration, for example, is C1 molar. And this is platinum solid here. So this is your anode. Similarly, your cathode. In your cathode, H positive aqueous, whose concentration is C2 molar, it will be getting converted into H2 gas, whose pressure is P bar again. And here also, I've used platinum solid, right? So let me quickly show it to you also. This is, for example, your one hydrogen electrode. This is one more hydrogen electrode. Here you have got H positives with concentration C1. Here also you have got H positives with concentration C2 molar, right? Here you have kept hydrogen rod, H2 rod, and you already know how this H2 rod is made. Here is H2 rod. The partial pressure, the pressure at which H2 was introduced, the pressure at which H2 was introduced here, that was P bar, and here also the pressure is P bar only. Perfect. Now you're connecting them externally with the help of emitter and internally with the help of salt bridge. So I got a complete cell. In this particular complete cell, tell me one thing, whether the electrodes are same or different. Electrodes are same, so it's a concentration cell, right? Now, are the concentration of electrolytes same or different? Concentration of electrolytes is different. So it is electrolytic concentration cell involving which electrodes? Involving hydrogen electrodes, right? That's the topic which you wrote. Electrolytic concentration cell involving hydrogen electrodes. Now let's get to know when this particular cell will be working. Let's make a condition. Let's make a condition which this particular cell has to follow such that this particular cell works like a normal galvanic cell. So let's try to frame that condition. First of all, for this particular cell to be working like a normal galvanic cell, at anode what should happen? Oxidation. So first of all, the reaction at anode should be H2 gas, whose pressure is P bar, right? H2 gas, it will get converted into 2 times H positive, whose concentration is C1 plus 2 electrons. This has to be the reaction at anode. Similarly, what should be the reaction at cathode? At cathode, reduction should take place. H positive should get converted into H2. So the reaction has to be 2 times H positive, whose concentration is C2 molar, right? It should gain 2 electrons and it should get converted into H2 gas, whose pressure is how much? Whose pressure is again P bar only. So this has to be the reaction at cathode. This has to be the reaction at anode. This has to be the reaction at cathode. What should be the net reaction? Just add these two reactions. My dear students, when you add these two reactions, which all things will get cancelled out? 2 electrons cancelled, right? Okay, H2 cancelled because their pressure is same. So my net reaction has to be 2 times H positive with the concentration C2 molar. It gives 2 times H positive with the concentration C1 molar. This is my net reaction. In this particular net reaction, if I ask you how many moles of electrons are exchanged in the net cell reaction, you will say N value is equal to 2. If I ask you what about the QC value, QC has to be concentration of H positive, that is C1 raised power 2 divided by C2 raised power 2. So it is C1 divided by C2 whole raised power 2. This is your QC. Since two same electrodes are used, so it's a concentration cell. In case of concentration cells, E naught cell value is taken to be 0. Perfect. Now, my dear students, after this, what exactly am I going to do? What exactly am I going to do? I'll be using now the Nernst equation. And in case of Nernst equation, I'll say E cell is equal to E naught cell. E naught cell is 0 already. Minus 0.0591 divided by N. What is N value? N value is 2. And here it is log of QC. And QC is nothing, that is C1 divided by C2 raised to the power 2. Correct? I believe everything is clear till here. Now, dear students, try to understand few more things. I'll write something like this. E cell is equal to minus 0.0591 divided by 2 log of m raised power n, which is n log m. So 2 comes to the front. It is log of C1 divided by C2. So 2 and 2 gets cancelled out. So you will be writing E cell is equal to minus 0.0591. It is log of m by n now, which is log of m minus log of n. Right? Log of m minus log of n. Okay. Now, if I ask you what is the C1 and what is the C2, see guys, it is minus 0.0591. Log of C1. What is C1 exactly? C1 is the concentration of H positive in anode, right? Minus log of C2. C2 is the concentration of H positive in cathode, right? C2 is the concentration of H positive in cathode. Now, if I further solve it, I'll be getting something like this. E cell is equal. See, take this minus inside. It's going to be 0.0591, right? Now, it is minus log H positive. Minus log H positive means pH, but this is pH of anode. Similarly, this is minus in the middle. Take this minus inside. So, minus log of H positive, which is going to be pH. So, it's pH of what? It is going to be pH of cathode. So, this is the general expression, my dear students, which you are going to remember from now on. This is something which you are going to remember from now on. And this particular equation to calculate E cell, it is valid for all the electrolytic concentration cells, which involves the hydrogen electrodes. Okay. Now, what exactly were we supposed to do? We were supposed to form a condition which this cell should follow such that it behaves like a normal galvanic cell. And in case of normal galvanic cell, the current is from cathode to anode, right? So for this particular cell to be working, like a normal galvanic cell, right, in which the direction of current is from cathode to anode, for this particular cell to be working, I'll say E cell value should be greater than 0. E cell value will be only greater than 0 if pH of anode will be greater than that of pH of cathode, right? So I will say for the cell to be working, like what? Like a normal galvanic cell. Like a normal galvanic cell. For a cell to be working like a normal galvanic cell, I would say pH of anode should be greater than that of what? It should be greater than that of pH of cathode. Then only the difference between the two will come out to be positive. Then only E cell will be positive. Once E cell is positive, I'll say delta G is negative. If delta G is negative, cell reactions will be spontaneous. If cell reactions are spontaneous, that means that anode oxidation will happen, at cathode reduction will happen, electrons will move from anode to cathode, and current will show its direction from cathode to anode, right? So for this particular cell to be working, do remember pH of anode should be greater than that of pH of cathode. Is this clear to everyone? Let me know once in the chats quickly. Let me know once in the chats quickly. Tell me the answer of this particular question. Tell me the answer of this particular question. What do you think? What do you think about this one? Look at this particular cell. On both the sides, you have used zinc electrode, right? So electrodes are same. So it's a concentration cell, number one. Now, which type? Concentration of zinc dye positive here is C2. Here the concentration of zinc dye positive is C1. So concentration is kept different. So it is electrolytic concentration cell. It is electrolytic concentration cell involving which type of electrodes? Involving metal ion electrodes. Now, this particular cell, few minutes back only we have discussed this in detail. Now, look at the options. Look at the options carefully. Choose the correct option. The cell reaction will be spontaneous if C1 is greater than C2. Now, a few minutes back only I told you, for the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell, the concentration of electrolyte in cathode should be greater than that of anode. What is the concentration of electrolyte in cathode? It is C1, right? So C1 value should be greater than C2. C1 value should be greater than C2. Absolutely. C1 value should be greater than C2. Then only this particular cell will behave like a normal galvanic cell in which the direction of current will be from cathode to anode, right? So this particular statement is correct. Cell reactions will be spontaneous, right? It's simple, it's evident. If C1 is greater than C2, C1 here is concentration of electrolyte in cathode, C2 is concentration of electrolyte in anode. If concentration of electrolyte in cathode is greater than that of concentration of electrolyte in anode, then only E cell will come out to be positive. And once E cell is positive, delta G is negative. If delta G is negative, cell reactions are spontaneous. It will behave like a normal galvanic cell, right? So first option is correct. Second, if C2 is greater than C1, if C2 is greater than C1, current will flow from cathode to anode. This is not correct. This is not correct. For the current to flow from cathode to anode, that means for the cell to be working like a normal galvanic cell, concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. So this cannot be the answer. Look at the next one. If C1 is greater than C2, if C1 is greater than C2, cathode concentration greater than anode concentration, current will flow from cathode to anode. Absolutely, it will work like a normal galvanic cell, correct? If C1 is equal to C2, if C1 is equal to C2, my dear students, if C1 is equal to C2, that means C2 by C1 value will be equal to 1. If C2 by C1 is 1, so log of 1 is 0. If log of 1 is 0, that means E cell is 0. If E cell is 0, there will be no current, right? The cell will not work. The cell will not work. This also correct. Done? Is this clear? Is this particular concept clear to you? Let me know quickly in the chats. Is this particular concept clear? See, few minutes back only I told you, I gave you this particular result, right? This was your electrolytic concentration cell involving metal and electrodes. If C1 and C2 are equal, if C1, C2 are equal, so log of 1 is equal to 0. Therefore, E cell is 0. Once E cell is 0, that means the delta G is 0. So leave that part aside. Okay? I believe every single thing is clear till here. Okay. Just a second. Look at this particular question. Look at this particular question. What do you think about this one? First of all, try to identify which cell this is. Are you using two same electrodes? Absolutely two same electrodes. So concentration cell. Now which type? Electrolyte concentration? Electrolyte concentration different. Electrolyte concentration different. So believe it, it is an electrolytic concentration cell. Partial pressure is same. Partial pressure is same. So it is absolutely electrolytic concentration cell involving which electrodes? Involving hydrogen electrodes. Do you remember? Few minutes back only we have discussed this. Electrolytic concentration cell involving hydrogen electrodes. Its E cell is equal to 0.0591 multiplied by pH of anode minus pH of cathode. Few minutes back only we have discussed it, right? What we have to calculate? We have to calculate X. So pH of anodic container we have to calculate. Okay. What is E cell value? It is 0.2364 is equal to 0.0591. pH of anode is X, needs to be calculated. pH of cathode. In the cathode, what is the H positive concentration? That's 1 molar. So I'll say pH of cathode is equal. P stands for minus log. So minus log of H positive concentration of cathode. So which is minus log of H positive concentration of cathode is 1 molar. So the value is 0. So this particular value is 0. So X value from here will be equal to 0.2364 divided by 0.0591. The value will be approximately equal to 4. Right? So what was this X? X was the pH of the anodic container, which we were supposed to calculate. Is this clear to everyone? Is this particular point clear to everyone? Let me know once in the chats quickly. I'll be giving you one question here as the homework, right? I'll be giving you one question as the homework. Look at the question carefully, but be careful with this one. In this one, concentrations are different and partial pressures are same. Concentration is different, partial pressure is same. Or let me solve this question, wait. Let me solve this question. Have a look. See what the question exactly is. The question is, as far as this particular question is concerned, this is your solid bridge. On the left side of it, you are using anode. On the right side, you are using cathode, right? You are using anode and cathode. Perfect. Now try to understand and analyze things. We have to calculate E cell and we have to comment on spontaneity. How can we comment on spontaneity? Spontaneity we can comment only when we have the E cell value, right? So first of all, it's trying to get the E cell, and if E cell is positive, that means delta G is negative, cell reactions are spontaneous. This cell will be working like a normal galvanic cell. If E cell is negative, delta G is positive, cell reactions are non-spontaneous. Okay. So first of all, you have used same electrodes and both are hydrogen electrodes in which concentrations are different, partial pressure is same. So this is again electrolytic concentration cell involving hydrogen electrodes, right? How do we calculate its E cell? Its E cell is equal to 0.0591 multiplied by pH of anode minus pH of cathode, right? So first of all, let's calculate pH of anode. pH of anode is going to be minus log of H positive ion concentration in anode. Now, what is H positive ion concentration in anode? In anode, you have used H2SO4. In anode, you have used H2SO4, which would have got dissociated as 2 times H positive plus SO4 dinegative. The concentration of H2SO4 you have kept as 0.05 molar. 0.05 molar initially. So this would have been 0, this would have been 0. Now this H2SO4 would have been completely dissociated. So this is 0. Now 1 mole gives 2 moles. 0.05 will give 0.1 molar. This is going to be 0.05 molar. So I would say the concentration of H positive in the anodic container, that is 0.1 molar. So calculate the pH of the anodic container. pH of anode is minus log of H positive of anode. H positive concentration of anode is 10 raised to minus 1 molar. Value is 1. So pH of anode is 1. If pH of anode is 1, now calculate the pH of cathode. pH of cathode is going to be minus log of H positive concentration of cathode, which is minus log. What is H positive of cathode? It is HCl. In cathode, you have used HCl. So HCl would have dissociated as H positive plus Cl negative. 1:1:1 stoichiometry. So I can say 1 mole of HCl gives 1 mole of H positive. So 10 raised to minus 3 will give 10 raised to minus 3 only. So concentration of H positive in cathode is 10 raised to minus 3 molar only. So the value comes out to be 3. So you calculated the pH of anode, you calculated the pH of cathode, right? You calculated the pH of anode, you calculated the pH of cathode. So this value is 1, this value is 3. So 1 minus 3, the value will be overall what? The value will be overall negative. So first of all, you calculated E cell. After calculating E cell, then you got the sign of E cell as well, which is negative. And you know when E cell is negative. You know when E cell is negative. At that time, delta G will be positive. If delta G is positive, I'll say cell reactions, will they be spontaneous or non-spontaneous? I'll say cell reactions will be non-spontaneous. Will this particular cell be working like a normal galvanic cell? This particular cell won't be working like a normal galvanic cell, right? Is this clear? Is this clear, people? Quickly in the chats. Quickly let me know in the chats, everyone. Everyone in the chats, quickly. All right. Now, we have got one more concentration cell. What is that? That is electrode concentration cell. Do you know what is electrode concentration cell now? In case of electrode concentration cell, we'll be keeping the concentration same in anode and cathode, but we'll keep the partial pressures different. For example, I'm making the cell here. I'm writing first of all platinum solid, right? And here I'm writing, let's say, H2 gas, whose partial pressure is P1. It gets converted into H positive, whose concentration is, for example, C molar. This is the salt bridge. On the right side, I'll be writing cathode. Let's say in the cathodic container, there are H positives, whose concentration is C molar, right? That is getting converted into H2 gas. And the partial pressure of H2 gas here, I'm keeping as P2 bar. And here I'm using again the platinum solid. Look at this particular cell carefully. In this particular cell, again, you are using two same electrodes. Again, you are using two same electrodes. So it is the concentration cell. Its E cell has to be 0. Now, Is the concentration same or different? The concentration is same, but partial pressure is different. Whenever you see this kind of the cell, in which you will be using two same electrodes, concentration of anode and cathode will be same, but partial pressure will be different. My dear students, you will be calling this particular cell as electrode concentration. Now, what condition this cell has to follow so that it can behave like a normal galvanic cell, so that the direction of current will be from cathode to anode, so that the cell reactions will be spontaneous. Let's try to make those conditions as well. So, for this particular cell to be working like a normal galvanic cell, what should be the reaction at anode? At anode, oxidation happens. H2 is getting converted into H positive. So I'll say H2, whose pressure is P1, it has to get converted into 2 times H positive, whose concentration is C molar plus 2 electrons. This has to be the reaction at anode. Right? Similar reaction at cathode. H positive has to get converted into H2. So at cathode, reduction has to happen. So 2 times H positive with the concentration C molar, it has to gain 2 electrons. Then only it will be getting converted into H2 gas, whose pressure here is P2 bar. Right? So you wrote the reaction which has to happen at anode and cathode. Now, are the electrons balanced? The electrons are balanced in both. My dear students, if electrons are balanced, you can directly add these two reactions. And when you add these two reactions, what is the net reaction? Which all terms will it cancel out? 2H positive cancel because their concentration is same, right? So my net reaction is going to be H2 with partial pressure P1. It gives H2 with partial pressure P2. Now tell me how many moles of electrons are exchanged? I'll say 2 moles of electrons are exchanged in the net cell reaction. Okay, N values 2. Now if I ask you what about QC? QC value is going to be, start with the product. It is partial pressure of H2 here, which is P2, divided by partial pressure of H2 here, that is P1. So QC we got. Since it's a concentration cell, so its E naught cell value has to be 0. Now, my dear students, one more thing. E naught cell has to be 0. We got to know that. Now, write the Nernst equation. E cell is equal to E naught cell, that's 0, minus 0.0591 divided by N value. N value is 2. Log of QC. QC is nothing, that is P2 divided by P1. P2 divided by P1. I believe it's clear till here. Now tell me one simple thing. If I multiply this minus with this log, what I'll be getting exactly? I'll be getting E cell is equal to 0.0591 divided by 2. It's going to be log of P1 by P2. It's going to be log of P1 divided by P2, right? So this is the result which I got till now. This is the result which I got for E cell. Now, for this electrode concentration cell to be working like a normal galvanic cell, its E cell should be also greater than 0, right? So E cell value should be greater than 0. Then only this cell will be working like a normal galvanic cell. Then only the cell reactions will be spontaneous. Then only electrons will move from anode to cathode. Then only current will go from cathode to anode, right? So E cell has to be greater than 0. Because if E cell is 0, then only delta G for the reactions will be negative. Then only I'll say the cell reactions are spontaneous. Now tell me one thing. When this particular E cell will be greater than 0? I'll say E cell will be only greater than 0 if this particular term is greater than 0. When will be log of P1 by P2 greater than 0? When will be log of P1 by P2 greater than 0? When P1 divided by P2 value will be greater than 1. That means when P1 will be greater than what? When P1 will be greater than P2. What was P1 and what is P2? Look at it carefully. P1 was the partial pressure of anode and P2 is the partial pressure of cathode. So can I say something like this? For the above cell, which is basically gas ion cell. It is basically, the cell name is for the above cell involving, let me write it like this, for the above cell involving which electrodes? Involving gas ion electrodes, right? For the above cell involving gas ion electrodes to be working like a normal galvanic cell. That means for its cell reactions to be spontaneous, P1 should be greater than P2. P1 is the partial pressure of anode. Directly say partial pressure of anode has to be greater than that of partial pressure of cathode. Partial pressure of anode has to be greater than that of what? It has to be greater than that of partial pressure of cathode, right? This is the condition which the cell has to follow. Then only the cell reactions involved in the cell will be spontaneous. Is this clear? Is this clear to everyone? Let me know once in the chats quickly. Let me know once in the chats quickly, quickly, guys. Quickly. Look at this question. Will you be able to solve this question? Only thing here is, see, pressure is 2 atm, here it's 1 atm. So pressure is different. Concentrations are also different. So you won't be using any formula directly. You'll be using the general procedure. You'll write the reaction at anode, reaction at cathode, net reaction. Then you'll get the actual QC, right? Actual QC. E naught cell is 0. Then you'll be using the Nernst equation. You'll be at the end getting E cell. And if E cell comes out to be positive, cell reactions will be spontaneous. If they come out to be negative, they'll be non-spontaneous. Is this clear? Is this clear to you? Will you be able to solve this question, or you want me to solve this question? Do you want me to solve this question, or you will be doing it on your own? Because it's a simple question. Nothing different or difficult to do here. Let me know quickly. Will you be solving this question? Let's say yes or no in the chats quickly, yaar. So I would want its answer in the comment section then. If you guys are saying that you will solve it, then right after the session, I would want its answer in the comment section. And I'll exactly see who all are the ones who will at least try this question, right? The answer can be right or wrong, leave that part aside. At least trying part, I want you guys to do. Okay? Danir, every book is best when it comes to PYQs, because PYQs are same everywhere. Whatever book you want to consult for PYQs, right? On every book, PYQs will be same only. What kind of question this is? Which book is best for PYQs? Every book is best for PYQs, right? Because PYQs, they'll never change, whatever publication you have. Got it? I think you asked the same question yesterday in the J channel as well. Yeah? Guys, one last topic in the EMF part. One last topic in the EMF part. What is that? One last topic in the EMF part, that is thermodynamics of the cell. That is thermodynamics of the cell. They can ask a question related to thermodynamics of the cell as well. What does that mean? They can ask you, calculate delta G for the cell, which already you know, right? How to do. They can ask you, calculate entropy change. They can ask you, calculate enthalpy change. These are the three things which they can ask you related to thermodynamics part of the cell. They can ask you, when the galvanic cell is working, what will be the delta G for the galvanic cell? What will be the entropy change, right? What will be the calculate the entropy change, right? Calculate the enthalpy change. These are the three things which they can ask. Now, how to deal with these three things? How do we get them? My dear students, if you remember, in thermodynamics, I've given you one equation. If you remember, the equation was like this. Dg is equal to VdP minus SdP. Do you remember this equation? And I had told you, this particular equation is valid only for reversible processes. It is valid only for the reversible process. When I taught you Gibbs free energy variation with pressure and temperature, when I asked you the Gibbs free energy variation, when I taught you the Gibbs free energy variation with pressure and temperature, at that point of time, I used this particular equation. Ag is equal to VdP minus SdT. My dear students, if I write the same equation at constant pressure, at constant pressure, can't I say dP value is 0? Change in pressure is 0. If dP is 0, I'll say dG is equal to minus S dt. But my dear students, when it comes to reactions, in case of reactions, we do not define entropy. We define entropy change for the reaction, right? In case of reactions, we do not define Gibbs free energy. What do we define? We define Gibbs free energy change for the reaction. In case of what? In case of reactions. In case of reactions, you do not define entropy, you define entropy change of the reaction. Similarly, you define what? You define Gibbs free energy change of the reaction. Okay? Now, for a particular reaction, instead of this particular equation, I can write D of G. Instead of G, I'll be writing delta G for the reaction is equal. It's going to be minus, instead of S, it's going to be delta S for the reaction multiplied by what? Multiplied by dt. Perfect. Now, why am I doing exactly all this? Why am I doing all this? See, guys. See, try to understand what exactly we'll get here. Can I write something like this? Just a second. Okay, can I write D of delta G for the reaction? D of delta G for the reaction divided by dt. It comes out to be equal to minus delta S for the reaction. Okay. Now tell me one thing. What about delta G for the reaction? That is minus NF E cell, right? So minus comes out, N comes out, F comes out. It becomes D of E cell divided by dt, right? And this particular term is valid at constant pressure. You have kept pressure constant in the beginning, right? And this particular term is equal to minus times delta S for the reaction. So minus gets cancelled out. So the first result which we got, which you are going to remember from now on, whenever they ask you calculate the entropy change in the galvanic cell, right? You'll be writing this expression NF dE upon dt at constant. My dear students, this particular result you will be using to calculate what? To calculate entropy change in case of the galvanic cell. N, number of moles of electrons exchanged. F, Faraday's constant, 96500. This dE by dt, this is something which you call as temperature coefficient of the cell. Temperature coefficient of the cell, which can be positive as well as negative. If you ask me the units of temperature coefficient, dE by dt, this is change in EMF, change in temperature. EMF is volt, temperature is Kelvin. So its SI unit is going to be volt per Kelvin. This temperature coefficient. Perfect. So this is how you are going to calculate delta S for the cell reactions. Similarly, if they ask you to calculate delta G for the reaction, delta G is simple, minus NF E cell, right? So two parameters are done. If they by chance ask you about delta H for the reaction, you know your delta G, as per thermodynamics, delta G is equal to delta H minus T delta S, right? Now, when it comes to the cell reactions, you'll write RR everywhere. Perfect. Now, delta G value you know, delta S value you know. From here, you can calculate delta H. Let's get to know what will be the value of delta H. Let's try to understand. See, guys, we know delta G is equal to delta H minus T delta S, right? So from here, you can say delta H will be equal to delta G plus T. This is delta S, right? So I would say delta H for the reaction is equal. Delta G is minus NF E cell, right? Plus T. Delta S is NF dE upon dt. NF dE upon dt at constant pressure. So let's make a finalized result. So delta H for the reaction is equal. If I take NF common, it's going to be what? It's going to be minus E cell plus it's going to be dE upon dt, which is what you call as temperature coefficient of the cell at constant pressure multiplied by T. So this is the general result which you can remember also to calculate delta H for the galvanic cell. So they'll be asking few questions. First, they can ask delta G for the cell, for the galvanic cell, or they can ask delta S for the galvanic cell, or they can ask delta H for the galvanic cell. And these are the equations which you can use to calculate delta G, delta S, or delta H. Or sometimes they might ask you about the efficiency of the galvanic cell. Sometimes they can ask you about the efficiency of the galvanic cell as well. And how do you calculate the efficiency of the galvanic cell? It is simple. Mod of delta G of the cell divided by mod of delta H for the cell multiplied by 100. This is the general expression which you can use to calculate the efficiency of the galvanic cell. Perfect. Provided you know delta G value, you know delta H value, just divide them, multiply with 100, get the efficiency of the galvanic cell as well. Okay. Perfect. Perfect, guys. Now here there can be a question asked too. I'm writing the topic as variation of EMF with temperature. How EMF varies with temperature. This can be asked too. How EMF varies with temperature, right? My dear students, I'm going to divide this topic into two categories here. I'll be dividing this topic into two categories. It's simple, it's very simple. Those galvanic cells whose temperature coefficient is positive. This is my first category of galvanic cells. And those galvanic cells whose temperature coefficient is negative, right? So I've got two types of galvanic cells. First, those galvanic cells with temperature coefficient positive and those galvanic cells with temperature coefficient negative. Let's see how their EMF varies with temperature. Does EMF increase on increasing the temperature or does it decrease? Let's get to know. See. So first of all, I'm talking about that particular galvanic cell whose temperature coefficient is positive. Right? Now, my dear students, for example, in this particular cell whose temperature coefficient is positive, if you increase the temperature of the cell, upon increasing the temperature, what will happen to dT value? Change in temperature. Change in temperature is final minus initial. Final temperature minus initial temperature. This term will be positive. Simple. When you increase the temperature, dT will be positive. Change in temperature is positive. Now this overall term is positive. And already we know, since we increase the temperature, upon increasing the temperature, dT value is positive. So dT value is positive. Denominator is positive. If denominator is positive and the whole term is also positive, for the whole term to be positive, I'll say dE value should be positive as well. It should be positive as well. dE positive means when dE will be positive, when change in EMF will be positive, if the final EMF will be greater than initial EMF. So what exactly you concluded from here? You saw upon increasing the temperature, EMF, is it increasing or decreasing? E2 is greater than E1. I'll say upon increasing the temperature, the EMF, it increases, right? The EMF, it increases. So directly you can say E cell is directly proportional to temperature for those cells which have got temperature coefficient positive, right? Which have got positive temperature coefficient. I hope this is clear. Similarly, those galvanic cells which have got temperature coefficient negative, how their EMF varies with temperature. See, for example, if you increase the temperature here, upon increasing the temperature, dT value will be positive. Absolutely, dT is positive. So denominator, dT, it is coming out to be positive. Denominator is positive. But whole term, overall term has to be negative. Since denominator is positive and overall term has to be negative, for the overall term to be negative, I'll say this dE value has to be negative. This dE value, it has to be negative, then only the overall value will be negative. Now tell me one thing. When this dE will be negative, dE is change in EMF. It is only negative if E2 will be less than E1, right? Change in EMF will be only negative if final EMF will be less than initial EMF. So upon increasing the temperature, what is happening to EMF? EMF is decreasing. I'll say E cell here will be inversely proportional to temperature. But it is valid for those cells which have got temperature coefficient as negative. Is this clear? Is this clear to everyone? Let me know quickly in the chats if this is super clear to everyone. Right? Quickly. So what you exactly, these are the two things which you have to remember at the end, nothing else. E cell is directly proportional to temperature for those cells which have got temperature coefficient positive. E cell is inversely proportional to temperature for those cells which have got temperature coefficient negative. That's it. Okay. Okay, guys. Is every single thing clear till here? Is everything is dealt with detail? Everything is done with detail. Okay. And here you have to remember how many results? Delta S result you have to remember. Delta G result you have to remember. And delta H result you have to remember. If you do not want to remember the delta H, it's okay also. Because once you get delta G value, once you get delta S value, you can easily calculate delta H from this particular equation. One and the same thing. Okay? Perfect, guys. Do you want to solve one question on this particular topic? Do you want to solve one question on this particular topic? Let me know once quickly. Do you want to do that? Okay, let's have a look on the question which can be asked from here. I'm writing the question, okay? Just a second. One simple question I'm giving you. The question is like this. The EMF of the cell, it is given to us as 1.018 volt. EMF of the cell is given to us as 1.018 volt. Temperature coefficient of the cell, dE upon dt at constant pressure. This temperature coefficient of the cell is given to me as -5 multiplied by 10 raised power -5 volt per Kelvin. Okay. What are we supposed to calculate? Calculate delta G, delta H, and delta S. And delta S for the reaction. And the reaction is like this. Cadmium dye positive plus 2 electrons, it gives cadmium solid, right? And temperature, this reaction is carried out at temperature 25 degrees centigrade. This is one of the questions which can be asked from this topic. Look at the question carefully. The reaction is given. So first of all, how many moles of electrons exchanged? 2. So N value is 2 first of all. N value is 2. This is something which you got. Now, delta G. Delta G. Delta G is nothing, that's minus N of E cell. Right? So minus N value is 2. Faraday's constant 96500 coulombs. Right? E cell value is also given. 1.018 volts. So every value is taken as per SI system. That means delta G value will be also coming as per SI system. As per SI system, the value of delta G is joules. So the final answer will be in joules. Number 1. Number 2. Delta S is simply going to be equal to NF dE upon dt. NF dE upon dt at constant pressure. So what is N value? N value is 2. Faraday's constant is 500 coulombs. dE by dt. What is dE by dt? Temperature coefficient. That is -5 into 10 raised power -5. So by solving this particular equation, you'll be getting the value of delta S. And delta S units you already know. Delta S is basically Q by T, right? Entropy change, Q by T. So it has to be joules per Kelvin. Now delta H. Delta H, you have to calculate. How you'll be calculating delta H? Either you'll be using the direct result, which I gave you, or you can use this equation directly. Delta G is equal to delta H minus T delta S. Now, my dear students, delta G already you calculated. Delta S you calculated. Temperature is given. Converted in Kelvin. So from here you can calculate delta H. Nothing else. Right? Delta H value will be also in joules. Right? These sort of questions can come. These sort of questions can come. And there has been, I mean, in your NEET examination, question has never been asked from thermodynamics of the cell. So this time they might ask it from here. So I believe we have completed the EMF part. EMF part of electrochemistry is completed. Now it is time to enter into one more part of the chapter, that is electrolytic part. And that electrolytic part we shall be starting on Thursday, day after tomorrow. So Thursday, Thursday at 6 p.m. we'll have one more session in which we shall be completing the electrolytic part of this particular chapter as well. Okay? Perfect, people. I think this much is enough for today. Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know in the chats quickly with the thumbs ups. Good evening, people. Good evening and welcome back. Good evening and welcome back. So can you all hear me? All perfect? Yes, all perfect. All perfect, people. All right, so my dear students, as you all must be knowing, it is going to be the last session of the chapter Electrochemistry today, right? And in this particular session, what all things we are going to cover? Let me tell you that. So in this particular session, we are going to start with electrolysis. Number one, we'll see the products of electrolysis. We'll see the Faraday's first law of electrolysis, Faraday's second law, different types of questions which can be asked from these topics. And we shall be talking about the conductance part as well, right? Which involves those terminologies. I'm sure you would have heard it already. Resistance, resistivity, conductance, conductivity, etc., etc., right? And at the end, we shall be discussing about the Kohlrausch law as well, okay? Lecture duration will be 3 hours. Yeah, in 3 hours, I believe all these topics will be like cleared properly with all the problem patterns, okay? Perfect. So let me know once in the chats, are you guys done with the first 3 sessions of the chapter? Are you guys done with the first 3 sessions of the chapter? Let me know once in the chats quickly. Are you guys done with that? Quickly, let me know in the chats. Are you all done with the first 3 sessions of the chapter? All right, perfect. So basically, in the first 3 sessions, we have completed the EMF part, right? Whatever we were discussing till the last session, that was EMF part of the chapter. And I believe I have discussed all the topics related to EMF, all the problem patterns. Now, you can consult any study material, any book, and I believe all the problem patterns you can easily solve if you have followed the first 3 sessions, right? And by following this particular session, after completing this particular session, I believe you can solve all the types of the problems which can be asked from the chapter Electrochemistry, provided you have made the notes and everything properly. Yeah? Perfect, guys. So let's get going then. Let's get started with something called as electrolysis, okay? Let me first of all write the definition of electrolysis. Then exactly I'll make you understand what this electrolysis is all about. Okay. Electrolysis. Electrolysis, my dear students, it is the process. It is basically the process of decomposition of an electrolyte, into its elements by the supply of direct current. What it means, you'll get the idea in some time. First, take a note of this statement. Number 1. Number 2. The device in which electrolysis is carried out. is carried out. That device is called as electrolytic cell. Electrolytic cell. That device is called as electrolytic cell. Point number 2. Take a note of this. Point number 3. Point number 3. If you remember, in case of galvanic cells, the cell reactions used to be spontaneous, right? They used to be spontaneous. In case of your Daniel cell, galvanic cell, etc. Right? In case of electrolysis, I'll say reactions are made spontaneous. Reactions are made spontaneous by the help of direct current. Reactions are made spontaneous by the help of direct current, which are otherwise non-spontaneous. Which are otherwise non-spontaneous. Okay. One more point I'm mentioning here. In the electrolytic cell, we'll be using 2 electrodes. One is your anode, one is your cathode. And do remember, in case of electrolytic cell, the anode carries the positive charge and the cathode carries the negative charge. Whereas in case of your galvanic cell, if you remember, in case of galvanic cell, the rod of anode used to carry the negative charge and the rod of cathode used to carry the positive charge. Here it's reverse. Anodic rod here carries the positive charge, cathodic rod here carries the negative charge, right? And all the other things are same. At anode, oxidation takes place, which involves loss of electrons, and at cathode, reduction takes place, which involves the gain of electrons. Now let's try to understand all these things in detail. I believe you have taken a note of all these things. Okay, so let's try to understand all these things in detail now. My dear students, in order to make you understand the electrolysis, I'll be taking one example, with the help of which you'll particularly understand what this electrolysis is all about. Okay, what this electrolysis is all about. So I'm going to do the electrolysis of molten NaCl, and automatically you'll get the idea what this electrolysis exactly is. Okay. So first of all, I will be taking a container over here. So imagine this is the container, right? My dear students, in this particular container, let's say I am keeping molten NaCl. In this particular container, I am keeping molten NaCl. Now, first of all, you must be thinking what this molten NaCl is all about. Imagine that you have taken NaCl solid in the container, and you have heated it up, and you have heated NaCl solid till the extent it gets converted into liquid, right? So imagine you have taken solid NaCl in the container and you have started heating it up. There will be a time when this NaCl solid will get converted into NaCl liquid. And that NaCl liquid is something which I call as molten NaCl. So I have got molten NaCl in this particular container. Okay. Now, my dear students, one thing. If there is molten NaCl in the container, can you let me know how many types of ions will be there in the container? There will be 2 types of ions. One is going to be your Na positive and one is going to be your Cl negative. Correct? Now, dear students, what exactly we shall be doing? I'll be inserting 2 rods here in this solution. These are the 2 rods which I have inserted in this particular solution. And these 2 rods I'm connecting with the battery. These 2 rods I'm connecting with the battery over here. Okay. That rod which is connected with the negative terminal of the battery will carry the negative charge. And that rod which is connected with the positive terminal of the battery will carry the positive charge. And as I told you, the negatively charged rod here is what I call as cathode, and the positively charged rod here I'll be calling as anode, right? And you know, at cathode what happens? At cathode reduction takes place, and reduction is nothing, it is just the gain of electrons. And similarly, at anode I must say oxidation takes place, right? and oxidation involves loss of electrons. Okay. Now, my dear students, let's exactly get to know what, when you connect these rods with the external battery, let's get to know what happens at anode and cathode. Let's get to know what happens at anode and cathode. So first of all, let's try to analyze the things which are going to happen at cathode. Cathode is your negatively charged rod. Can I say this negatively charged rod is going to attract the positively charged ions from the solution? Absolutely, this negatively charged rod is going to attract the positively charged ions from the solution towards itself. So this Na positive is attracted by this particular rod, and similarly, Cl negative is attracted by this particular positively charged rod. Perfect. So can I say this Na positive is going towards cathode? This Na positive is going towards cathode, and at cathode what happens? Reduction happens. So the Na positive which is going towards cathode, I must say this Na positive at cathode will undergo reduction. Reduction involves gain of electrons. So I must say at cathode, your Na positive, it will undergo reduction. It will gain one electron and will get converted into Na solid, right? And this particular Na solid, it will start getting deposited on this particular rod. It will start depositing on this particular rod. The first question which is asked, the products of electrolysis. What is happening at cathode when you do the electrolysis of molten NaCl? You'll directly say at cathode, it is the sodium metal which is being deposited. It is the sodium metal which is being deposited. In the similar way, if I ask you what is happening at anode oxidation takes place, right? At anode, Cl negative will go and will undergo oxidation, right? Cl negative at anode will undergo oxidation. Oxidation involves loss of electrons. So the reaction has to be 2 times Cl negative, right? It will get converted into Cl2 gas, and with this, you will be getting 2 electrons as well. Perfect. So my dear students, the question that's asked here, what is happening at cathode? What are the products of electrolysis? You'll directly remember at cathode, it is basically the sodium metal which is being deposited. Sodium metal is being deposited. And if I ask you what is happening at anode, it is the gas which is getting liberated. So at anode, Cl2 gas is getting liberated, right? At anode, it is the Cl2 gas which is being liberated. Okay, this is the first point which you need to remember in case of this particular electrolysis, right? I hope you got the idea of how this electrolysis exactly happens. Now, my dear students, tell me one thing. The device in which electrolysis takes place. What do you call this device as? You call this as electrolytic cell, right? You call this as electrolytic cell. My dear students, can I say in this electrolytic cell, an external voltage, an external supply is used, an external source is used, which is sending the current in the solution, then only these reactions are happening. Absolutely. Right? You have used an external battery here. You have used the battery here, right? So what this battery exactly does, it is sending the current in the solution due to which these reactions are happening over here, right? So with the help of current, the reactions are happening. So the reactions which were supposed to be non-spontaneous, we are making them spontaneous with the help of this external current, with the help of this particular current. Okay? So can I say the non-spontaneous reactions are made spontaneous, right? We are making sure the reactions which were otherwise being non-spontaneous, we are making those non-spontaneous reactions to happen with the help of the current. Okay, with the help of the current. Perfect. This particular cell in which the cell reactions are happening with the help of the current which goes into the solution. This overall process is something which you call as electrolysis. I believe it's clear to everyone. Yeah? Is it clear to everyone? Let me know once in the chats quickly. Let me make you understand one more. Look at this particular scenario. Let's do the electrolysis of molten PbBr2. You'll understand it in a better way. See, first of all, This is the container which I have. And in this particular container, what have I kept? I have kept PbBr2. PbBr2, which is molten PbBr2. So basically in the container, what kind of ions do we get? We'll be having Pb di positive ions and Br negative ions in this particular container, right? So insert two rods here. You have inserted two rods here. Now connect these rods with the battery, right? This is negative, for example. This is positive. Negative over here is called as cathode. This positive over here is called as anode, right? Now, can you let me know what's going to happen? Can you let me know what's going to happen? At cathode, reduction takes place. Reduction means gain of electrons. So this particular cathode, this negatively charged rod, is going to attract Pb di positive towards itself. And this positively charged rod is going to attract Br negative towards itself, right? So I would say at cathode, Pb di positive will undergo reduction. At cathode, reduction takes place. And at cathode, Pb di positive is going. So Pb di positive will go to the cathode and undergo reduction, right? So what has to be the reaction? The reaction has to be Pb di positive will undergo reduction, will gain 2 electrons and will get converted into Pb solid, right? Similarly, what is happening at anode? What is happening at anode? I'll say at anode, Br negative will go and will undergo oxidation. Oxidation means loss of electrons. So the reaction has to be 2 times Br negative will give Br2, and with that you'll be writing 2 electrons. So just tell me in the nutshell what is happening at cathode and anode. So you'll directly say at cathode, lead is being deposited. At cathode, lead is being deposited. And at anode, it is Br2 which is being liberated, right? Simple. Simple, guys. So right now I'm doing the electrolysis of molten electrolytes. Perfect. I believe you can do the electrolysis of anything. Any molten electrolyte you can do. Now, my dear students, there comes a point. Since I've told you how to do the electrolysis of what? How to do the electrolysis of molten electrolytes. Now, you can keep the electrolyte in aqueous form as well. What about aqueous NaCl? What about the electrolysis of aqueous CuSO4? Right? What about the electrolysis of aqueous PbBr2? What about them? There are few things which you need to know before going into the details of the electrolysis of aqueous electrolytes. Right? Okay, let's try to understand. In simple way. First of all, I want you guys to remember two reactions. One reaction is something which I'll be calling as oxidation reaction of water. Another reaction I'll be calling as the reduction reaction of water. These are two reactions which I would want you guys to remember first of all. One is oxidation reaction of water, one is reduction reaction of water. Okay, have a look. Have a look, my dear students. Have a look, understand. If I ask you, what is the oxidation state of this oxygen here? It is -2. What is the oxidation state of oxygen here? It is 0. So -2 to 0 means increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. Oxidation involves loss of electrons. So in this particular process, when water will be getting converted into O2, what will happen? Loss of electrons will happen, right? Loss of electrons will happen. And this particular reaction, you are going to remember directly from now onwards. That too in the balanced format. This reaction is called as oxidation reaction of water. In the similar way, in the reduction reaction of water, what is going to happen? Electrons are not going to be lost. Electrons are going to be gained. Have a look. If you look at this particular hydrogen, its oxidation state is +1. This hydrogen, its oxidation state is 0. +1 to 0, decrease in the oxidation state. +1 to 0, decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. And reduction means gain of electrons. Have a look, electrons are being gained here. Electrons are being gained here. This particular reaction I'm calling as the reduction reaction of water. So first, take a note of these two reactions. They are important. Why they are important? You will get the idea in some time. First one is called as oxidation reaction of water, in which loss of electrons is happening. Second one is called as the reduction reaction of water, in which gain of electrons is happening. Right? In which gain of electrons is happening. Perfect? Right, guys? Now, there is a term that's called as discharge potential. How do you define the discharge potential? How do you exactly define the discharge potential? It is defined as the potential at which an ion is discharged at the electrode. the potential at which an ion it is discharged at the electrode. Let me make it simple for you. Let me make it simple for you, right? If I make it simple for you, just a second. Let me make it simple for you. Let me write it like this. The work to be done by the electrode. The work to be done by the electrode in order to attract the oppositely charged ion, in order to attract the oppositely charged ion towards itself. See, discharge potential, actual definition is this. The potential at which the ion is discharged at the electrode, right? But just to make you understand in simplified manner, I've mentioned it like this. Now, what it means exactly, let's get to know that. See, guys. For example, I have to do the electrolysis. Let's say I have to do the electrolysis of aqueous NaCl. Imagine that I have to do the electrolysis of aqueous NaCl, right? My dear students, this is the container which we have. And in this particular container, what I'm keeping aqueous NaCl. If I'm keeping aqueous NaCl, that means there is NaCl as well as water, right? So how many types of ions will be there? There'll be Na positive, there'll be Cl negative. Since there is water also in the container, so there'll be H positive ions, there'll be OH negative ions. As simple as that, right? Now, my dear students, imagine you have introduced two rods here. These are the two rods which you have introduced, correct? Now you're connecting them with the external battery. This rod gets negative, this rod gets positive. Negative one, that's your cathode. Positive one, that's your anode. Okay, that's your anode. Perfect. Now guys, try to understand. This cathode, this negatively charged rod, this cathode, it carries a negative charge, right? Now this negatively charged rod, it will try to attract the positively charged ion towards itself. So it will try to attract this one as well as this one towards itself. Perfect. Similarly, the positively charged rod will try to attract this one as well as this one towards itself, right? This is clear. Now tell me one thing. Since this negatively charged rod is attracting Na positive as well as H positive towards itself. So basically, both Na positive as well as H positive, they would want to undergo reduction here at cathode. Similarly, Cl negative as well as OH negative, both the anions would want to go to anode and both the anions would want to get oxidized at anode, right? Perfect. See, we have got two cations here. Perfect. So both these cations, they would want to go to the cathode and they would want to undergo reduction. Similarly, both these anions would want to go to anode and they would want to undergo oxidation. But among these two ions, which one will actually undergo reduction? Among these two ions, which one will undergo oxidation? That depends on the discharge potential of these ions. Right? Let me tell you that cation among the two, which has got lower discharge potential, will undergo reduction among the two. That anion among the two which has got lower discharge potential will undergo oxidation at anode. In simpler words, if you guys want to understand this in simpler words, I wrote a statement here. The work to be done by the electrode in order to attract the oppositely charged ion towards itself. Have a look. This electrode, it is going to attract Na positive as well as H positive, right? So when this electrode will be attracting this Na positive towards itself, that means the electrode is performing some work here. It's attracting the Na positive towards itself. The electrode is attracting H positive towards itself. It is performing some work, right? So wherever the amount of work to be done by the electrode is less, I'll say that particular ion will have the lesser discharge potential, right? So among these two ions, again I'm telling you, among these two cations, that cation which has got lower discharge potential, that cation wherein electrode has to perform lesser amount of work to attract it, that cation will undergo reduction. Okay. Similarly, look at these two. These are anions basically. They would want to go to anode, they would want to undergo oxidation. But I'm telling you that an anion whose discharge potential is less will undergo oxidation. So I would say among these two anions, that anion for which electrode has to do lesser amount of work to attract it towards itself, that anion will undergo oxidation. I hope this is clear. Now, how come you can tell whether among these two, which one has got lesser discharge potential? Among these two, which one has got lesser discharge potential? For that purpose, I want you guys to remember one series over here. This is something which I want you guys to remember. One is the discharge potential series of cations and one is the discharge potential series of anions. Imagine in the container, there is H positive and there is Na positive. Okay. Now, which one has got lesser discharge potential? H positive has got lesser discharge potential than that of Na positive. So if I ask you which ion among the two will undergo reduction at cathode, you'll directly say it is H positive which will undergo reduction at cathode, right? Because its discharge potential is less, right? Actually, how do we define discharge potential? The potential at which the ion is discharged at the electrode. That potential at which ion is discharged at the electrode. Perfect. And this ion gets discharged at lower potential basically. That's why it will undergo reduction at cathode. Similarly, if you look at the anions, in the case which I gave you a few minutes back, aqueous NaCl, right? There are Cl negative ions and OH negative ions. There were Cl negative ions and OH negative ions. Now, among these two ions, which one has got lesser discharge potential? It's Cl negative, right? Among Cl negative and OH negative, which one has got lower discharge potential? It is Cl negative. So Cl negative will undergo oxidation at anode. Cl negative will undergo oxidation at anode. As simple as that. Correct? Perfect. Cl negative, its discharge potential is less. It gets discharged at lower potential basically. Okay? Or I can tell it in simpler ways. In order to attract Cl negative towards itself, anode has to do lesser amount of work. Right? I hope this is clear. Now try to understand all these things in detail now. See guys. For example, the first topic which I'm mentioning here, what is that? Just a second. For example, I'm writing the heading as electrolysis of. Try to understand this. Electrolysis of aqueous NaCl. And my dear students, the electrodes which I'm using, they are inert electrodes. Which I'm using. Okay, now tell me one thing. Let's say this is your electrolytic cell. In this electrolytic cell, you have got aqueous NaCl. That means there will be Na positive, there will be H positive, there will be Cl negative, there will be OH negative in this container. So two types of cations, two types of anions. This is a rod. This is one more rod connected with the external battery, right? This is negative, this is positive. Negative is your cathode, positive is your anode. Perfect. Now, this negatively charged rod, it will try to attract Na positive as well as H positive towards itself. So both these ions would they would want to undergo reduction at cathode. But that cation will undergo reduction whose discharge potential is less. Now compare Na positive and H positive. Na positive and H positive. Which one has got lesser discharge potential? Na positive and H positive. Which one has got lesser discharge potential? Na positive and H positive. Which one has got lesser discharge potential? It is H positive which has got lesser discharge potential. My dear students, if H positive has got lower discharge potential, can I say it is going to be H positive which will undergo reduction here? Absolutely. Right? Absolutely. Now among Cl negative and OH negative, which one will undergo oxidation at anode? Cl negative, its discharge potential is less, so it will undergo oxidation at anode. Right? So if I ask you what will be the reaction at anode now? At anode, Cl negative is undergoing oxidation. It will lose electrons. So the reaction has to be 2 times Cl negative. It gives Cl2 plus 2 electrons. Right? Now if I ask you what will be the reaction at cathode? What will be the reaction at cathode? At cathode, reduction will take place. Reduction of what? A reduction of H positive. This H positive has come from where? This H positive has come from where? H positive has basically come from water. So I would write the reduction reaction of water here. I would write the reduction reaction of water here. Right, my dear students? And I hope you remember what about the reduction reaction of water? Few minutes back only I told you. What about the reduction reaction of water? Look at this particular slide. This is the reaction. This is the reaction which is what you call as the reduction reaction of water. And this is going to happen. This is going to happen at cathode. This is going to happen at cathode. Right? This is going to happen at cathode. Let me know once in the chat if it is clear. So this is going to happen at the cathode. Perfect. So at cathode, it's 2 times water plus 2 electrons. It gives H2 plus 4 times OH negative. This is the reaction which is taking place at cathode. So in short, tell me one thing. When we do the electrolysis of aqueous NaCl, at cathode, what is happening? At cathode, it's H2 gas which is being liberated. It is H2 gas which is being liberated. And at anode, what is happening? At anode, something was being deposited, I guess, or gas was liberated. Gas was liberated. Which one? At anode, Cl2 gas was liberated. So at anode, you got to know Cl2 gas is liberated. At cathode, you got to know H2 gas is liberated. Right? I hope this is clear to everyone. Clear, guys? Let me know once in the chats. Let me know once in the chats quickly. Right? So the reaction has to be 2 times water plus 2 electrons. 2 times water plus 2 electrons gives H2 plus 2 times OH negative. This is the reduction reaction which is happening at the cathode, and it's your H2 gas which is being liberated at the cathode. So these are the 2 things which I want you guys to remember. For example, you are doing the electrolysis of aqueous CuSO4. Let's imagine that you are doing the electrolysis of aqueous CuSO4. Imagine this rod carries the negative charge. Imagine this rod carries the positive charge, right? And in the solution, how many types of ions will be there? In the solution, how many types of ions will be there? Tell me that. In the solution, how many types of ions are there? You are doing the electrolysis of aqueous CuSO4. So there are Cu di positive ions, there are SO4 di negative ions, there are H positive ions, and there are OH negative ions. Correct? So this particular cathode, and this is your anode, right? At cathode, reduction will happen. Now this negatively charged rod will attract Cu di positive as well as H positive towards itself. But among these two, which one will undergo reduction here? The one which has got lesser discharge potential. The one which has got lesser discharge potential. Now tell me, among Cu di positive and H positive, which one has got lesser discharge potential? It is Cu di positive. So Cu di positive is undergoing reduction at cathode. So the reaction has to be Cu di positive plus 2 electrons gives what? It gives copper solid. So basically here, it is copper solid which is being deposited. It is copper solid which is being deposited. Similarly, you have got 2 types of anions, OH negative, SO4 di negative. Now both would want to go to the anode and both would want to undergo oxidation. But among these two, which one will undergo oxidation? The one which has lesser discharge potential, that's OH negative. OH negative has got lesser discharge potential, so it will undergo oxidation at anode. But if I ask you, from where this OH negative has come, you will say this OH negative has come from water. This OH negative has come from water, right? So OH negative has to go to the anode and will undergo oxidation, but this OH negative has come from the water. So you'll write the oxidation reaction of water. This was your oxidation reaction of water. And due to the oxidation of water, what is happening? O2 gas is liberated. O2 gas is liberated. And at cathode, copper solid is deposited. So these are the products of electrolysis which you have to remember. Is it done? Is it done, guys? Is it clear? Let me know once in the chats quickly. Let me know once in the chats quickly. Yeah? Say yes or no in the chats quickly. I believe you got the concept, right? The electrodes which I used during the electrolysis, those were your inert electrodes, right? Those were your inert electrodes like platinum. The actual topic, my dear students, which we have to discuss, what is that? The actual topic which we are going to discuss, that is Faraday's laws, from which questions frequently come in your examination, right? Faraday, it has given two laws here in electrolysis. So we are going to discuss these electrolysis, these Faraday's two laws in detail, right? So tell me once in the chats whether you can do the electrolysis of all the electrolytes with the help of discharge potential series. Right? Whatever electrolyte I give you, with the help of discharge potential series of cations and anions, can you do the electrolysis of every electrolyte? Right? Will you be able to guess what is happening at cathode and what is happening at anode? Just tell me that. Just tell me that. Perfect. Then let me move on to Faraday's first law of electrolysis. Have a look, people. So till now we got to know at the electrodes either metal is being deposited or gas is being liberated, right? On the electrodes we saw either metal getting deposited or gas being liberated. Now what Faraday's first law suggests that? Faraday's first law tells you that, say, on passing current in an electrolytic solution, the amount of substance deposited or liberated at the electrode, that is directly proportional to the charge which goes into the solution. Basically, you connected the electrodes with the battery. What battery does? It is sending charge into the solution. More the charge that goes into the solution, more will be the amount of substance getting deposited or liberated at the electrode. So mathematically, I can say it like this. The mass of substance in grams, the mass of substance deposited or liberated. This W represents the mass of substance which is being deposited or liberated. That is directly proportional to the charge which goes into the solution. Now, my dear students, if you remove the proportionality sign here, you'll get a constant, which I represent with Z. So it's Z multiplied by Q. What this Z exactly is? This Z is called as electrochemical equivalent. Right? And it is equal to E divided by 96500. What is this E? E is the equivalent weight of same substance which is being deposited or liberated. So I'll say, as per Faraday's first law, mass of the substance deposited or liberated is equal to, instead of Z, you're going to write E. Divide by what? Divide by 96500. Multiplied by what? Multiplied by Q. And Q is the charge. And charge is nothing. That is current multiplied by time. So this is the first result which I would want you guys to remember from now on. With the help of this particular result, we can easily calculate the mass of substance which is being deposited at electrode. Or we can easily calculate the mass of the gas. Which is being liberated at the electrode. Perfect. Which is being liberated at the electrode. This is the result number one. Now result number two. Have a look. Can I write it like this? Mass of the substance deposited or liberated in grams is equal. What is E? E is the equivalent mass of the same substance which is being deposited or liberated. And equivalent mass of the substance which is being deposited or liberated is equal to molar mass of the same substance which is being deposited or liberated divided by n factor of same substance. Right? And in the denominator, what do we have? 96500. In the numerator, we have got I multiplied by T. If you take this molar mass here in the denominator, so what do we get? W divided by M. Mass of substance deposited or liberated divided by molar mass of the same substance. Given mass by molar mass, that's called as moles. So N represents the number of moles of the substance which are being deposited or liberated. N represents number of moles of substance which are being deposited or liberated. It's equal to I multiplied by T divided by n factor of same substance which is being deposited or liberated multiplied by 96500. This is something which I want you guys to remember again. Right? This is something which I want you guys to remember again. Perfect. After this, my dear students, one more thing. For example, this was your question number one. This was your question number two. For example, if they ask you to calculate the volume of the gas liberated at STP. If they ask you how much volume of the gas is liberated at the electrode at STP, so for that purpose, to calculate the volume of the gas liberated at STP, first of all, you will be calculating the moles of the gas liberated. And once you calculate the moles of the gas liberated, after that, you will say volume of the gas liberated will be equal to moles of the gas liberated multiplied by what? Multiplied by 22.4 liters, right? If they ask you to calculate the volume of the gas liberated at STP, this is how you do it. First, you will calculate the moles of the gas liberated multiplied by 22.4 liters. If they do not mention STP, then in the question, they'll give the pressure, they'll give the temperature. Then you'll be using the ideal gas equation and calculate the volume of the gas liberated, right? I'll try to do certain questions with you so that you get familiar with the types of the questions which can be asked from these results, okay? But before that, there is one more thing which I would want to discuss with you. One more simple thing which I would want to discuss with you. My dear students, in this particular reaction, if I ask you how many moles of electrons are exchanged, in this particular reaction, as you can see, 12 moles of electrons are exchanged, right? If I ask you if this is a balanced chemical equation, first of all, if this is a balanced chemical equation and I'm asking you to calculate the n factor of A. From the balanced chemical equation, you can easily calculate n factor. How exactly? Let's say n factor of A will be equal to moles of electrons exchanged, that is 12, divided by stoichiometric coefficient of A, that's 1. N factor of A, you'll directly say as 12. For example, if I'm asking about n factor of B, how many moles of electrons exchanged? 12 divided by stoichiometric coefficient 2. So 12 divided by 2 is 6. 12 divided by 2 is 6. So 6 I'll be calling as n factor of B. Similarly, what is the n factor of C? 12 divided by 3, that's 4. 12 divided by 4, 3. 12 divided by 12 divided by 6, that is 2. So these are the respective n factors of these reactants and products. So basically, whenever you'll be given with a balanced chemical equation, from the balanced chemical equation, you can easily talk about the n factors of different substances. What you have to do? Moles of electrons exchanged divided by stoichiometric coefficient of reactant or product, the one whose n factor is to be calculated. Remove this particular thing as well. Now, why am I telling you this thing? See guys, the types of the questions will make you understand why am I exactly telling you all these things. Look at the question carefully. The simplest of all the questions. A solution of aqueous CuSO4. A solution of aqueous CuSO4 is electrolyzed for 10 minutes. With a current of 1.5 amperes. So basically, a current of 1.5 amperes is going into the solution for 10 minutes. What will happen? Electrolysis will happen, right? And due to electrolysis, a reaction would have happened at cathode, a reaction would have happened at anode. Perfect. Reaction would have happened at cathode and reaction would have happened at anode as well. Now the question is asking, what is the mass of copper deposited at cathode? They're asking you what is the mass of copper which is deposited at cathode. So first of all, my dear students, you should know when we do the electrolysis of aqueous CuSO4, what is the reaction at cathode. If you remember, a few minutes back only I told you, at cathode, when we do the electrolysis of aqueous CuSO4 at cathode, this is the reaction through which copper is getting deposited. Right? Right, people? Now you will directly use Faraday's first law. We have to calculate the mass of copper deposited, right? Tell me first of all, what is the n factor of copper? What is the n factor of copper here in the reaction? Is equal to moles of electrons exchanged 2 divided by stoichiometric coefficient 1. So n factor of copper is 2 here, right? N factor of copper is 2. Now, I'll be using the equation. Mass of copper deposited in grams is equal to equivalent mass of copper multiplied by I multiplied by T divided by what? 96500. I believe you are done. Equivalent mass of copper is molar mass of copper 63.5 grams divided by n factor of copper. N factor of copper is 2. In the denominator, you have got 96500. What is the value of current? 1.5 amperes of current is passed into the solution for 10 minutes, but use the time in seconds. So multiply it with 60, right? One equation, you're done, right? I think after solving this, you'll be getting the value exactly around 0.3 grams. So what is the 0.3 grams exactly? You can say when we do the electrolysis of aqueous CuSO4, when a current of 1.5 amperes is passed into the solution for 10 minutes, you will say 0.3 0.3 grams. 0.3 grams of copper would have got deposited at the cathode, which is something I was supposed to calculate. I believe it's clear. Let me know once in the charts if it is clear. So 0.29 grams is the answer. Yeah? Quickly, guys, quickly. Let me know fast so that we can end the chapter fast. Because we have a lot of things to discuss. So let me know quickly in the chats if it is clear. Yes or no, everyone. Everyone in the chats. Sir, when do you take coordination compounds? When am I going to take coordination compounds? You tell me. Guys, which chapter do you want the next after this electrochemistry? Which chapter do you want the next? Majority wins. Majority wins. Tell me. Which chapter do you want the next? Quickly. After electro, which one do you want to do here? Quickly, quickly, everyone. Just say it, everyone. Nothing is wrong in it. I can see majority is looking for atomic structure. Okay, let me go with atomic structure. Next will be atomic structure. Right? All right. Look at the next question, guys. Look at the next question. See. Or just wait. Let's not do this question first. Let me see. Just a second. Let's do this particular question first. Look at this question carefully. The question is, what is the volume of oxygen? What is the volume of O2 liberated at anode at STP during the electrolysis of aqueous CaSO4? So we are doing the electrolysis of aqueous CaSO4, and you know when we do the electrolysis of aqueous CaSO4, which gas is liberated? It is O2 gas which is liberated. This is something which we know, right? O2 gas is liberated. Now they are asking you to calculate volume of O2 gas liberated at STP. So what do I calculate first? First of all, I'll calculate the moles of O2 liberated. Use the formula. I multiplied by T divided by N factor of what? N factor of O2 which is being liberated. N factor of O2 multiplied by 96500. Right? Now tell me, number of moles of O2 liberated is equal to current, how much? Current of 2 amperes is passed for how many seconds? For 8 minutes. So 8 multiplied by 60, then only it comes in seconds. N factor of O2. N factor of O2 is moles of electrons exchanged. 2 divided by stoichiometric coefficient, that's 1 by 2. The value is 4. So N factor of O2 is 4. Multiplied by what? Multiplied by 96500. So from this particular equation, what do we get? We'll be getting the moles of O2 produced. But am I supposed to calculate moles or volume? I'm supposed to calculate volume. So volume of O2 produced will be equal to moles of O2 produced multiplied by 22.4 liters. Right? This is something which you'll be calculating from here, and you'll have to multiply it with 22.4. You'll be getting the volume of O2 produced. Is that clear? Is that clear to you people? If you want to have a look on the exact values, so moles are 0.002 and volume of O2 liberated is 0.05 liter. Yeah? Perfect. I believe this is clear to everyone, right? Let's try to solve 5 more questions. Look at this particular question, guys. Look at this particular question. Look at this particular question. As per this particular question is concerned, a current of 96.5 amperes, is passed for 10 seconds through 1 liter of a solution of 0.5 molar aqueous copper sulfate. Calculate the pH of the solution. Calculate the pH of the solution. Try to understand what the question says. As far as this particular question is concerned, we are again doing the electrolysis of aqueous CaSO4, right? That's something which we are doing. We are doing the electrolysis of aqueous CaSO4. And my dear students, we already know that when we do the electrolysis of aqueous CaSO4, we already know the reactions which happen at anode and cathode. This is the reaction at cathode. This is the reaction at anode, right? Now at cathode, what is happening? At cathode, it is just copper is being deposited. Now at anode, what is happening? At anode, water is undergoing oxidation, due to which first O2 gas is produced. At the same time, H positives are also produced, right? H positives are also liberated. At anode, water undergoes oxidation, due to which O2 gas is produced. O2 gas is liberated. And H positives are also generated. And those H positives will enter into the solution. The H positives which we get at anode, these H positives will definitely enter into the solution. Yeah, these H positives will enter into the solution. My dear students, can I say this is the reaction which is going to take care of the pH? This is the reaction which is going to take care of the pH, because through this particular reaction, H positives are generated and those H positives are going into the solution. Right? Perfect. What am I supposed to calculate? I'm supposed to calculate pH. Try to understand one thing. I'm supposed to calculate pH. What is pH basically? P stands for minus log. So minus log of H positive concentration we have to calculate. So can I say in order to calculate pH, we should know what is the total H positive concentration in the solution after the electrolysis is done? Once the electrolysis is complete, after that, you'll find H positives in the solution. Now, we will have to calculate the concentration of H positives in the solution after the electrolysis is complete, right? How do I calculate the H positive concentration? Concentration is nothing. It is moles per unit volume. So basically, it is going to be number of moles of H positive divided by volume of solution in liters. So can I say in order to calculate the H positive concentration, I should know the number of moles of H positive which are liberated into the solution. Now, how do I calculate number of moles of H positive liberated? With the help of Faraday's first law. I'll say number of moles of H positive liberated is equal to I multiplied by T divided by what? Divided by N factor of H positive multiplied by what? Multiplied by 96500. Correct? So number of moles of H positives which are liberated in the solution is equal to, what is current? Current is 96.5 amperes. For how much time? 10 seconds divided by, what is the N factor of H positive? N factor of H positive. Moles of electrons exchanged divided by stoichiometric coefficient. 2 by 2 is 1. This is 1. Multiplied by what? 96500. The value comes out to be 10 raised per minus 2. So I'll say these many moles of H positive have gone into the solution. In the solution, you'll find these many moles of H positive. Once you get the moles of H positive, tell me what will be the concentration of H positive in the solution. Moles of H positive in the solution divided by volume of solution in liters. So it is 10 raised per minus 2 divided by, what is the volume of solution? That's 1 liter. So the value comes out to be 10 raised per minus 2 only. So 10 raised per minus 2 molar is the concentration of H positive in the solution. If you got the concentration of H positive in the solution, you can easily calculate pH of the solution. P stands for minus log. It is minus log of H positive. So pH is going to be equal to minus log of 10 raised per minus 2. The value exactly comes out to be 2. So 2 is the pH of the final solution which we get after the electrolysis is done. Let me know once in the chats if it is clear. Quickly guys, quickly in the chats. Quickly in the chats. Similar sort of question. Give it a try. Read the question first, then let me know whether you can solve this or not. Read this question first. Read this question quickly. The question is very simple. 1 farad of electricity is passed through 10 liter of an aqueous solution of NaCl. So as per the question, you are doing the electrolysis of aqueous NaCl. And since you are doing the electrolysis of aqueous NaCl, what are we supposed to calculate? We are supposed to calculate pH of the solution. My dear students, don't you remember? When we do the electrolysis of aqueous NaCl, don't you remember the reactions at anode and cathode? The reaction at anode, the reaction at cathode. Now, tell me one thing. Which reaction among the two should I consider to calculate the pH of the solution? You tell me. Which reaction among the two should I consider to calculate the pH of the final solution after the electrolysis is done? You tell me. Is it going to be reaction at anode or cathode? My dear students, at anode, nothing is happening. Only Cl2 is being liberated. But if you look at the cathode, at cathode, OH negatives are also produced. At cathode, OH negatives are also produced. And those OH negatives will enter into the solution. Yeah? Those OH negatives will enter into the solution. Now see, how am I going to tackle this question? First of all, if I ask you, what about the N factor of OH negative? What about the N factor of OH negative? Quickly. It's going to be equal to moles of electrons exchanged divided by stoichiometric coefficient. So 2 divided by 2 is 1. This is the N factor of OH negative. Okay. Now, my dear students, the first thing which I'll be doing, I'll calculate the moles of OH negative. Moles of OH negative which are being produced, which are being liberated into the solution. Moles of OH negative as per the formula. I multiplied by T divided by N factor of OH negative multiplied by 96500. But do you see, current is not given, time is not given. Current is not given, time is not given. Okay. But I multiplied by T is what we call as Q. Instead of I into T, instead of I multiplied by T, I can declare Q. So I'll say N factor of OH negative, my dear students, will be equal to, what is Q? Q is 1 farad. 1 farad means 96500 coulombs. 1 farad is 96500 coulombs. Divide by N factor of OH negative, that's 1. Divide by 96500. The value is coming out to be 1. So you got to know 1 mole of OH negative is liberated into the solution. Right? During this electrolysis, once this electrolysis is done, you'll find 1 mole of OH negative in the resulting solution. If you got the moles of OH negative, can't we get the OH negative concentration in the container? It has to be equal to moles of OH negative in the container divided by volume of solution in liters. Now tell me, how many moles of OH negative do we have? 1. Volume of solution in liters, that's 10 liter. The value is 10 raised power minus 1 molar. 10 raised power minus 1 molar. So this is the concentration of OH negative in the final solution once the electrolysis is complete. Okay. If you got the OH negative concentration, we calculate POH. P stands for minus log. It's minus log of OH negative concentration. So it is minus log of 10 raised power minus 1. The value comes out to be 1. So you got the POH. If you got the POH, you know at 25 degrees centigrade, pH plus POH is always equal to 14 at 25. So pH from here will be equal to 14 minus 1, which comes out to be 13. Is this clear? Is this clear, people? Is this clear? Let me know in the charts quickly. Done? Look at this particular question. Look at this particular question. Calculate how much current is required. Calculate how much current is required to produce H2 gas at the rate of 1 ml per second under STP. Read the question carefully. Calculate how much current is required to produce H2 gas at the rate of 1 ml per second at STP. So as per the question, we are doing some electrolysis, right? We are doing some electrolysis, due to which what is happening? What is happening? H2 gas is getting produced. Now, as per the question, we have to do electrolysis in such a way that 1 ml of H2 gas should get produced. So how much ml of H2 gas should get produced? 1 ml of H2 gas should be liberated in how much time? In 1 second. Right? We have to perform electrolysis in such a way that 1 ml of H2 gas should get liberated in 1 second. In order to liberate 1 ml of H2 gas in 1 second, how much current should enter the solution? That's something which you're supposed to calculate. How much current should enter into the solution such that 1 ml of H2 gas is liberated in 1 second at STP. Correct? There are many ways of solving this question, right? The kind of approach which I've been using till now, I'll use the same approach. See guys, this is the condition is STP, right? How much volume has to get liberated? 1 ml. If I ask you, how many moles of H2 are supposed to be liberated? How many moles of H2 are supposed to be liberated? It's going to be 1 divided by 22400. So these many moles of H2 should be liberated. In how much time? In 1 second. Now you already know, can't I write like this? Number of moles of H2 liberated has to be equal. It has to be equal. I multiplied by T divided by N factor of H2. multiplied by 96500. Right? Now, my dear students, first of all, you should understand how H2 gas is produced. How H2 gas is produced. How H2 gas is produced. If you remember, H2 gas is only produced when water at cathode undergoes reduction. When water at cathode undergoes reduction. Due to the reduction reaction of water. Due to the reduction reaction of water, H2 is produced. Right? Due to the reduction reaction of water, H2 is produced. Do you remember that? Do you remember that? Due to reduction reaction of water, H2 is produced. So, you can write either the reduction reaction of water, or in simpler ways, you can write the reaction in this manner. You can either write reduction reaction of water, right? Or you can write the reaction in this manner. Perfect. The choice is all yours. Answer will be same. Okay. Now, what is the n factor of H2 here? Moles of electrons exchanged divided by stoichiometric coefficient. So 2. So number of moles of H2. Number of moles of H2 liberated. We already know it. That's 1 upon 22400. So number of moles of H2 liberated is 1 upon 22400 is equal to current. We have to calculate time 1 second. N factor of H2, that is 2, multiplied by 96500. One equation, one unknown. Can't you get the I value from here? Can't you get the I value from here? And as far as I remember, the value of I will come out to be 8.61 amperes. So what is meant by this 8.61 amperes? Just tell me that. Just tell me that. What is meant by it? It means that 8.61 amperes should pass into the solution. Then only 1 ml of H2 gas will be produced in 1 second at cathode. Yeah? Is it clear? Is it clear, guys? Quickly. Look at this question. Just tell me, can you solve this question on your own? Can you solve this question on your own quickly? Let me know in the chats. Let me know in the chats quickly. Can you solve this question on your own? Till then, let me find one more question. One more different type of question, which can be asked from the same. This is something which you can solve now, right? It is of similar pattern. Similar pattern. It is just volume is given in liters here. So you do not have to divide with 22400. You have to divide with 22.4. I'm giving you this as the homework. You are going to try it and write the answer in the comment section at the end. In the last session, I gave one question. Only 6 people gave the correct answer. Only 6 people gave the answer in the last session. Right? But I want you guys to, everyone to solve this question and write the answer in the comment section. Okay? Now, let me give you one more question. The question is like this. I'm writing the question. The question is, for example, the density. The density of copper is equal to 8.95 grams per centimeter cube or grams per ml. Find the charge. Find the charge required. Find the charge required to plate an area Find the charge required to plate an area of 100 centimeters square. Of 100 centimeters square to a thickness of 10 raised power minus 2 centimeters. 10 raised power minus 2 centimeters using copper sulfate solution. Using CuSO4 solution. Look at the question carefully and give it a try. Look at the question carefully and give it a try. First, read the question. First, read the question. First, read the question. Sorry. Okay. Guys, have a look. I'll solve this question. You just have a look on and remember the approach. The question is, the density of copper is 8.95 grams per centimeter cube. Find the charge required to plate an area of 100 centimeters square to a thickness of 10 raised power minus 2 centimeters using copper sulfate solution. My dear students, When we do the electrolysis of aqueous CuSO4, what happens at cathode? At cathode, Cu dye positive gains 2 electrons, gets converted into copper solid. And that copper solid is deposited on the cathode, right? Let's assume that this is your cathode. It's a plate. It is your cathode, for example. This is your cathode. And at cathode, what is happening? Reduction is happening. Reduction of what? Cu dye positive. So Cu dye positive from the solution is gaining 2 electrons, getting converted into copper solid. This is your cathode. On which this copper solid is being deposited. So this is a plate on which copper solid is being deposited. Copper solid is being deposited on this plate, right? As per the question is concerned, the area of cross section of this particular plate, it's 100 centimeters square. Dear students, if the area of cross section of this plate is 100 centimeters square, that means the copper which is being deposited here, that has to cover the area of 100 centimeters square, right? So the copper which is being deposited, it has to cover the area of 100 centimeters square, right? Since we are doing the electrolysis of copper sulfate, what is happening? At cathode, reduction is happening. Copper solid is being deposited. We have to continue the electrolysis. Till number 1, till the entire surface gets covered with the copper. And after that, the thickness of the copper on this plate should be 10 raised power minus 2 centimeters. Till then, we have to continue the electrolysis. I hope you're getting this, right? We have to continue the electrolysis till the entire surface of the plate, till the entire surface of the electrode is covered. And at the same time, first entire surface should get covered. After that, the thickness of the copper on the plate should be 10 raised power minus 2 centimeters. So if I ask you, indirectly, how much volume of copper are we depositing on this plate? How much volume of copper are we depositing on the plate? Tell me that. Area of cross section multiplied by thickness. Area of cross section is 100 centimeters square. Thickness is 10 raised power minus 2. So 100 multiplied by 10 raised power minus 2 is going to be 1 cubic centimeter. So this much volume of copper, basically we are depositing on this plate. Right? This much volume of copper we are depositing on the plate. Correct? Now tell me, is the density of copper given to you? Absolutely. How much? 8.95 grams per centimeter cube. Can I say density of copper is nothing? It is mass of copper deposited divided by volume of copper. Volume of copper in centimeter cube. This is basically 8.95 grams per centimeter cube. Correct? Agreed? What is the volume of copper which is being deposited? 1 centimeter cube. 1 centimeter cube is being deposited. So 1 multiplied with this. So I'll say mass of copper deposited has to be 8.95 grams. So first of all, you got to know the mass of copper which you are depositing. So we have to deposit 8.95 grams of copper, right? We have to deposit 8.95 grams of copper. In order to deposit 8.95 grams of copper, what is the charge? What is the charge which should go into the solution? Calculate the charge that should go into the solution. Okay, calculate the charge that should go into the solution so that 8.95 grams of copper is deposited. So I'll directly say mass of copper deposited as per Faraday's first law has to be equal. Equivalent mass of copper multiplied by I multiplied by T divided by 96500. Correct? So what mass of copper we are going to deposit? 8.95 grams is equal to equivalent mass of copper is molar mass of copper divided by what? Divided by n factor of copper. Calculate the n factor of copper. Electrons exchanged divided by stoichiometric coefficient. So this is 2. In the denominator, it's 96500. Right? I multiplied by 2, I can call directly as charge Q. I multiplied by T is something which you call as Q. Perfect. So from this particular result, can't you get the value of Q? Yeah? Can't you get the value of Q? Can't you get the value of Q? Perfect, guys. Is it clear? Is it clear to everyone? Quickly in the charts. Quickly, everyone. Hi, Wassim sir. How are you? I'm doing good, bro. How are you doing? Glad to know that, Rohit. I think this Believers was my last year student. You the same? Who used to follow me on YouTube on the last platform? Right? There was one regular student whose name was Believers. Maybe you're the same. Anyways, have a look. So from this particular equation, we can easily get the Q value, right? And Q from here, you are going to get in coulombs, right? Perfect. So I believe you can easily solve these sort of questions now, right? I believe you can easily solve these sort of questions. So let's move on to the Faraday's second law of electrolysis. Let's move on to the Faraday's second law of electrolysis. First of all, tell me in the chats, whatever types of questions I showed you in the Faraday's first law, will you be able to solve all the types? Will you be able to solve all the types of questions? Say yes or no in the chats. I believe every single thing is clear, yeah? Perfect. Now let's have a look on Faraday's second law of electrolysis. What this Faraday's second law of electrolysis states. Let's have a look on the definition first, then I'll make you understand. Okay. If a current is passed in two or more electrolytic solutions containing different electrolytes, the mass of substance deposited or liberated in different cells will be in the ratio of their equivalent masses, or the number of equivalents deposited in all the cells will be the same. Now, what is meant by this whole statement? Let's try to understand. See, guys, as far as this particular question is concerned, imagine that I have got, for example, 3 electrolytic cells like this. Let's say I've got 3 electrolytic cells like this. Assume that in this particular container, there is one electrolyte, for example, AB, just to make you understand. In this particular container, there is one more electrolyte, for example, CD. Let's say in this particular container, there is one more electrolyte, for example, EF. So we have got 3 different electrolytes present in 3 different containers. Okay. Now what exactly I'm doing? Let's put the rods inside. These are the 2 rods in the solution. 2 rods in this particular solution. 2 rods in this particular solution, right? Let me connect these rods. Let me connect these rods. And at the end, let me connect them with the external battery as well. I've connected them with the battery as well. So first thing, my dear students, that rod which is connected with the negative terminal will carry the negative charge, and that rod which is connected with the positive terminal will carry the positive charge. If this is positive, this has to be negative. If this is negative, this has to be positive. This has to be negative, and this has to be positive, right? Okay. Tell me one thing. We have got more than one electrolytic cells containing different electrolytes in series. This is the series combination. This is first of all the series combination, right? This is the series combination. And you know, in the series combination, current remains the same. You know it. So can I say same amount of current is going into this solution? Same amount of current is going into this solution. Same amount of current is going into this solution. So in all the 3 cells, what will happen? Electrolysis will happen. Due to electrolysis, something would be happening at electrodes. Either metal will be deposited or gas will be liberated. That's something, right? Let's assume, my dear students, let's assume at this particular electrode, let's assume A is being deposited and B is being liberated. For example, just to make you understand, let's assume at this particular electrode, what is happening exactly? At this particular electrode, just a second, guys, just a second. Just a second. Let's assume that on this particular electrode, A is being deposited and here, for example, B is getting liberated. Let's say here, C is getting deposited and here D is getting liberated. For example, here on this electrode, let's say E is getting deposited and E is getting deposited and here F is getting liberated. This is something which I'm assuming. Now, as per Faraday's second law is concerned, whenever you'll be having two or more than two electrolytic cells connected in series containing different electrolytes, the gram equivalence deposited or liberated at every electrode will be the same. That means I can say the gram equivalence of A deposited at the first electrode will be same as that of gram equivalence of B liberated at the second electrode, which will be same as that of gram equivalence of C deposited, which will be same as that of gram equivalence of D liberated, which will be same as that of gram equivalence of E, similarly, which will be same as that of gram equivalence of F. Perfect. Perfect. This is something which we call as Faraday's second law. Gram equivalence deposited or liberated at every electrode will be the same only. Perfect. Now, I hope you guys remember how do we calculate gram equivalence. Gram equivalence of the substance is equal to, do you remember? Mass of substance divided by equivalent mass of the substance. Or you can say number of moles of the substance multiplied by n factor of the substance. This was the result to calculate gram equivalence, studied in Redox. Right? Perfect. Perfect, guys. Now, at the same time, one more thing, then I'll do certain questions so that you can understand it properly. See, guys, for example, I'm taking one electrolytic cell. Which contains an electrolyte. Right? It is connected with a battery, due to which this gets negative, this gets positive. Right? Negative is what you call as cathode here. This is your anode. Let's assume at cathode, some substance A is getting deposited, and let's assume at anode, gas B is getting liberated. Just to make you understand. Now you can use Faraday's second law here as well. You can say gram equivalence of A deposited here should be equal to gram equivalence of B liberated here. You can write it like this. Gram equivalence of A deposited on the first electrode will be always equal to the gram equivalence of B liberated. At the same time, you can do one more thing. You can write the same statement in terms of milli equivalence as well. You can say milli equivalence of A deposited will be equal to milli equivalence of B liberated, right? And my dear students, if you got to know how to write these statements, you're done. You can solve any question of your NEET standard from Faraday's second law. Let me show you one. Look at the question. Let's see what the question is first of all. The question is, during electrolysis of aqueous CuSO4, we are doing the electrolysis of aqueous CuSO4. The mass of metal deposited is equal to 63.5 grams. Calculate the mass of gas released and volume of the gas released at STP. These are 2-3 questions. Yeah? Try to understand. See, guys. As far as the question, we are doing the electrolysis of aqueous CuSO4, right? And when we do the electrolysis of aqueous CuSO4, at cathode copper gets deposited. And at anode, O2 gas gets liberated. This is something which we already know. At cathode copper gets deposited. At anode, O2 gas is released. What Faraday's law says? Can't I say the number of gram equivalence of copper deposited should be equal to the number of gram equivalence of what? The number of gram equivalence of O2 produced. Just equate their gram equivalence, nothing else. Now tell me one thing. Gram equivalence of copper can be written as mass of copper deposited divided by equivalent mass of copper. Similarly, gram equivalence of O2 produced will be equal to mass of O2 produced in grams divided by equivalent mass of O2. Yeah, I think we are done. Aren't we done? Now, my dear students, try to understand. What is the mass of copper which is being deposited? Calculate the mass of gas released. Okay, the mass of copper which is being deposited, that is 63.5 grams. So 63.5 grams of copper is deposited. Divide by equivalent mass of copper. Equivalent mass of copper is molar mass of copper divided by n factor of copper. What is the n factor of copper? 2 divided by 1. That's 2 is equal to mass of O2 produced That's something which we have to calculate. Mass of O2 produced divided by equivalent mass of O2 will be equal molar mass of O2 divided by n factor of O2. N factor of O2 will be equal electrons exchanged divided by stoichiometric coefficient. So 2 divided by 1 by 2, that comes out to be 4. This term cancel. The value comes out to be 2, right? 4, 1, 4, 8. So that 8 is here. And this is mass of O2. Perfect. The value comes out to be 16 grams. So you got to know 16 grams of O2 is liberated. You got to know 16 grams of O2 is liberated at anode. 16 grams of O2 is liberated at anode. So we were supposed to calculate the mass of gas released. We got to know 16 grams of O2 is released. And at the same time, we have to calculate volume of gas released too. Right? Yeah? Right? Yash is saying, sir, please show effect of external cell on galvanic cell if possible. I think that is something which I've taught already. Check the first part. Check the first part. That is something which I've discussed with you in the first part. What happens when external battery is connected with the galvanic cell with reverse polarity? I believe I've discussed that. Guys, have I discussed that in the first part? I think yes. Okay, let's solve this question first, then I'll see whether I have taught that or not. See, so mass of O2 produces 16 grams. What else we have to calculate? Volume. But before volume, let's calculate moles of O2 produced. Moles of O2 produced will be equal to mass of O2 produced divided by molar mass of O2. So these many moles of O2 are produced. So volume of O2 produced has to be moles multiplied by 22.4 liters. The value has to be 11.2. So 11.2 liters of O2 is produced. Yeah? Clear? Yes, I'll teach Kohlrausch law as well in this lecture only. My dear students, I believe you can solve these sort of questions. Okay? I believe you can solve these sort of questions. Let me first of all check whether I have taught you external this or not. Just a second. Happening. Just a second, guys. This is our playlist. Where is electrochemistry part 1? Because that is important topic. I think I would have discussed that. Electrochemistry part 1. This is part 1, right? This is your Daniel cell. This is salt bridge. This is your Daniel cell. Was this? Wait. Was the representation? This was the first lecture. Where is the second one? Guys, just give me a second, okay? This is the topic, right? Here, when I'm making you understand the EMF, this is the external battery which I have connected with the Daniel cell in reverse polarity. Here, you can check this one. You can check this one again. Yeah, you can check this particular topic. This is the part 2. Here you can see this is your Daniel cell and external battery is connected with the Daniel cell with reverse polarity. And through this particular diagram, through this particular concept, I have taught you how do we calculate EMF of the cell basically. Okay. Right, with the help of potentiometer. Okay, so this is taught. Perfect. Leave it aside now. Where were we? We were discussing this. This question is clear? This question is clear? Perfect. Let me move on. Let me move on to the next question. Look at this particular question. Read the question carefully and let me know whether you can solve this or not. Just read it carefully first. Just read it carefully. Three electrolytic cells containing zinc sulfate, AgNO3 and copper sulfate respectively are connected in series. A current of 2 amperes was passed until 1.08 grams of silver was deposited at cathode of cell B. How long did the current flow? Okay. What mass of copper and zinc was deposited? Read the question. Tell me, can you solve this question on your own? If you can do, then I'll move on to the next topic. Tell me whether you can solve this question on your own or not. Read it quickly. You solve it. Okay, I'll solve it. See guys, as per the question is concerned, we have taken three electrolytic cells. So imagine this is one electrolytic cell, imagine this one more, and imagine this one more. So we have got three electrolytic cells. The first one is containing zinc sulfate, the second is containing AgNO3, and the next one is containing what? It's containing CuSO4. All right. Now there are two rods here. Two rods are here as well, and two rods are here as well. Now we will be connecting them with the external battery, right? This is the battery here, negative, this is positive. Perfect, one is negative, one is positive. The negatively charged rod, the negative terminal of the battery is connected here, so it carries a negative, this carries positive, this is negative, this is positive, this is negative, and this is positive. Perfect. Now guys, negative one is called as cathode here. On this particular cathode, as per question, what is getting deposited? Zinc. Here at this negative, at this cathode, what is getting deposited? Silver. And here, what is getting deposited? Over here, copper is getting deposited. Perfect. Copper is getting deposited, right? And these are the reactions through which these elements are getting deposited. Zinc dye positive from the solution is getting 2 electrons, getting converted into zinc solid, and that zinc solid is deposited here. Similarly, Ag positive in the solution will be getting 1 electron and will be getting converted into Ag solid. That Ag solid is deposited here. Similarly, copper dye positive getting 2 electrons, getting deposited as copper here. Perfect. Now in the question, a current of 2 amperes was passed. Okay, current of 2 amperes is passing in every electrolytic solution. Current of 2 amperes was passed until 1.08 grams of silver was deposited. So as per the question, it is given that 1.08 grams of silver is deposited, right? Is deposited. First, he's asking you how long did the current flow? How long did the current flow? Right? He's asking you T value. How long did the current flow? In what duration of time current flowed? So look at the second cell, my dear students. In this second cell, if I use the Faraday's first law, I can say in the second cell, mass of silver deposited has to be equivalent mass of silver multiplied by I multiplied by T divided by 96500. Now what is the mass of silver deposited as per the question? It's 1.08 grams is equal to equivalent mass of silver is molar mass of silver divided by n factor of silver. N factor of silver, electrons exchanged divided by stoichiometric coefficient. That's 1. Multiplied by what? Multiplied by 96500. Now I, current is 2 amperes multiplied by time. So one equation, one unknown. Can't you calculate T from here? T can be calculated. And as far as I remember, T value will be something 482.5 seconds. Right? So this is the time duration in which current has to flow. Right? In which the current has to go into the solutions. So the question was asking, how long did the current flow? Current has flown this long, 482.5 seconds. Number one. Number two, what mass of copper and zinc was deposited? What mass of copper and zinc was deposited? Now use Faraday's second law. What Faraday's second law states? Faraday's second law states that the gram equivalents deposited or liberated at every electrode will be the same, right? So first of all, I'll write like this. Gram equivalents of zinc, that is mass of zinc, divided by equivalent mass of zinc. Gram equivalents of zinc deposited has to be equal to gram equivalence of copper deposited. Sorry, gram equivalence of silver deposited, which is mass of silver divided by equivalent mass of silver. Right? Gram equivalence of zinc deposited should be equal to gram equivalence of silver deposited. Correct? Gram equivalence of zinc deposited is mass of zinc deposited divided by equivalent mass of zinc. Gram equivalence of silver deposited is equal to mass of silver deposited divided by equivalent mass of silver. Now, dear students, have a look. What is the mass of zinc which is being deposited? That's something which has to be calculated. Divided by equivalent mass of zinc is molar mass of zinc divided by n factor of zinc. N factor of zinc is 2 here. Is equal. What is the mass of silver which is being deposited? 1.08 grams as per the question. Divided by equivalent mass of silver. That is molar mass of silver divided by n factor of silver. So from this particular equation, you can easily calculate the mass of zinc which is deposited, and that too the answer will be in grams. Correct? Similarly, after this, once you get the mass of zinc deposited, you can equate gram equivalence of Ag with gram equivalence of silver. Sorry, gram equivalence of Ag with gram equivalence of copper. From there, you can calculate the mass of copper deposited. Is this question clear now? Is this question clear? So T value is 482.5 seconds. Mass of zinc deposited is 0.325. Mass of copper deposited you can calculate through this particular equation. You have just equated the gram equivalence of Ag deposited with the gram equivalence of copper deposited. That's all. Is this clear to everyone? Is that clear to everyone, people? Perfect. So I believe you can solve the Faraday's first law and second law electrolysis questions easily. Now comes one more part of the chapter, that is electrolytic conductance. Electrolytic conductance. This is something important. This is also important. So have a look, people, what it means, what kind of questions can be asked. Just a second, let me see whether I have added questions here or not. These questions are added. Okay. So my dear students, let me mark the heading as terminologies involved. Terminologies involved in electrolytic conductance. Terminologies involved in electrolytic conductance. Or let me just write terminologies involved in electrolytic conductor. You can also call it as conductivity cell. You can also call it as conductivity cell. Now, what this conductivity cell, first of all, is all about. Try to understand what exactly I'm going to talk about. Yeah? Have a look, people. Since we have discussed the electrolytic cell, okay? Again, I'm going to make the electrolytic cell here. Again, I'm going to make the electrolytic cell. Try to understand, guys. This is important. See, this is first of all. Let me make the electrolytic cell here. This is one container. This is one container. And my dear students, in this particular container, what do we have? Imagine that in this particular container, we have got an electrolytic solution. There is electrolytic solution in the container. So in short, I'll say there is electrolyte in the container. There is electrolyte in the container. Which electrolyte? Let's call this as AB electrolyte. There is AB electrolyte in this particular container. Okay. Now what exactly I'm doing? I'm going to place two electrodes here, right? I'm going to place two plates, basically. Two metal plates I'm placing, which are your electrodes. So here, this is your one metal plate, which works like one electrode, right? Similarly, this is one more metal plate, which works like one more electrode. Perfect. I've taken two electrodes here. Now, my dear students, you are connecting these electrodes with the help of battery. This electrode, this plate got the negative charge. This plate got the positive charge. Correct? Now, my dear students, first of all, imagine. Can I say this is the part of the electrode which is in contact with the solution? Yes, this is the part of the electrode which is in contact with the solution. So basically, This is the part of the electrode which is dipped into the solution. Similarly, this is the part of the electrode which is dipped into the solution as well. Perfect. My dear students, let me make one diagram here. Have a look. Let me connect this with this. Let me connect this with this. Let me connect this with this, and let me connect with this with this. Do you see? Do you see any diagram here? Do you feel something different here? Do you feel something different here? Try to understand. Just a second. Just a second. What did I get? What did I get? What did I get? It's a cube. It's a cube, right? What this cube is containing basically? What is present inside this cube? What is present inside this cube? Can I say in this cube, electrolytic solution is present? Basically, a solution is present which contains electrolyte in this cube. Let me take this cube out from the container. Imagine I'm taking this cube out of the container. When I take the cube out of the container, the cube will look like this. Let me show it to you. I've taken the cube out of the container. The cube is looking like this, right? What is this particular one? It is the part of the plate. It is the part of the electrode. It is the part of the electrode which is inside the solution. This is the part of one more electrode which is inside the solution, right? This electrode carries negative. This electrode carries positive. And in between these electrodes, what do I have? I've got a solution which contains an electrolyte, okay? Right? In this cube, you've got an electrolytic solution. Perfect. Which electrolyte I had taken? AB. So basically in this cube, what you will find? In this cube, you will find A positive ions and B negative ions, right? First of all, my dear students, this particular cell which I made over here, this particular cell is something which I call as conductivity cell. This is something which you call as conductivity cell, correct? Yeah. This is something which I call as conductivity cell. Now, my dear students, let me assume certain things. Let's assume the distance between these two electrodes. Let's assume the distance between these two electrodes is L centimeter. Let's say this area of cross-section of the electrode, that area of cross-section of the electrode which is inside the solution, right? That means this one. This area of cross-section of the electrode which is inside the solution, right? Let's call this as A centimeter square. A centimeter square is the area of cross-section of the electrode which is inside the solution, which is in contact with the solution. Yeah? So this particular cell is something which you call as conductivity cell. Now tell me one thing. This particular plate carries negative charge. This particular plate carries positive charge. Can I say this negatively charged plate is going to attract B negative towards itself? Absolutely. And this positively charged plate is going to attract, negatively charged plate is going to attract A positive towards itself, correct? And this positively charged plate is going to attract B negative towards itself. Now tell me one thing. When A positive will be moving towards negatively charged plate, when this A positive will be moving towards negatively charged plate, during the moment of A positive, can I say there will be some B negatives which will be attracting the same A positive towards itself? Yeah? Similarly, when this B negative will be going towards positively charged plate, when this B negative will be going towards positively charged plate, during its moment, can I say there will be some A positive which will be attracting this B negative towards itself? Absolutely. Do you see any obstruction in the moment of the ions? Absolutely, there is obstruction in the moment of the ions. And that obstruction in the moment of the ions, that is the reason why we say this particular electrolytic solution shows the resistance. So what is the resistance of this cell? It is simply the obstruction during the moment of the ions, right? What is the resistance of this particular cell? It is the obstruction during the moment of the ions, when the ions are moving towards the respective electrodes. Perfect. So my first terminology, my dear students, that is resistance. That is resistance, which is denoted by R. Which is denoted by R. I'm not going to write its definition because you already know it. Obstruction in the movement of the ions, right? How do you calculate this R? Tell me that. How do you calculate this R? You know it already. R is equal to rho L by A. R is equal to rho L divided by A. Perfect. R is equal to rho L by A. If I ask you, first of all, what are the units of resistance? Resistance units are ohm. Resistance unit is ohm. Right? How do you represent it? This is how you represent it. Right? This is how you represent it. Clear to everyone? Now, my dear students, in this particular expression, what did we get here? We got this term rho. What is rho? Rho is called as resistivity. Rho is called as resistivity. Resistivity is your rho. So tell me this rho. Can I say rho is equal to RA divided by L? Resistivity rho is equal to RA divided by L. Resistivity rho is equal to RA divided by L. How do you define this resistivity first of all? How do you define this resistivity? How do you define this resistivity? Understand. My dear students, imagine that the area of the cross section A is 1 centimeter square. This particular area, imagine it's 1 centimeter square. Imagine that the distance between the electrodes is 1 centimeter, right? Distance between the electrodes is 1 centimeter. If this cross section area is 1 centimeter square, distance between them is 1 centimeter. Can you let me know what will be the volume of this cube? Volume of this cube will be 1 centimeter cube. Volume of this cube will be 1 centimeter cube. This is the volume of the cube right now. Tell me one thing. When A is equal to 1 centimeter square, L is equal to 1 centimeter, can I say at that point of time, your rho is basically equal to R? Can I say your rho is equal to R? Perfect. Can I say resistivity is basically the resistance? Resistivity is basically the resistance. It is basically the resistance shown by this particular electrolyte. When the distance between these plates is 1 centimeter and the dipped area of cross section, that is 1 centimeter square. Or I can define it like this as well. Since the volume of the cube is 1 centimeter cube, if the volume of the cube is 1 centimeter cube, if I ask you, what is the volume of the electrolytic solution in this container? I'll say volume of the electrolytic solution in the container right now is 1 centimeter cube. I'll say resistance shown by 1 centimeter cube of electrolytic solution. Resistance shown by 1 centimeter cube of electrolytic solution, right? That's something which I call as resistivity. Perfect. Right? So it is the resistance. It is the resistance shown by what? By 1 centimeter cube of electrolytic solution. Can you let me know what will be the units of resistivity? Units of resistivity, tell me that. R is ohm, A is centimeter square, this is centimeter. So it has to be ohm centimeter. This is basically the unit of resistivity, ohm centimeter. Clear? So this was my second terminology, that is resistivity. Talking about my third terminology. Just a second. My third terminology is, it is conductance. It is conductance. Conductance is basically represented by G. How do you define this conductance? Conductance is defined simply as inverse of resistance shown by the conductivity cell, right? Inverse of resistance. Now tell me one thing. 1 divided by R is rho L divided by A. So this is A here. Perfect. This is A here. So my dear students, tell me just one thing. Look at this particular expression. Okay. Let me tell you the units of this conductance. It is 1 by R. The unit of conductance is going to be, either you'll write ohm inverse, or you'll write mho mho, or you'll write it as M. This is the unit of conductance, right? And Simon, it's denoted by S. That's all. Okay. Now, similarly, my fourth terminology, that is conductivity. Conductivity. Conductivity is represented by kappa, right? Now, the point is, how do you define this conductivity? How did we define conductance? Conductance was inverse of resistance. So, how do I define conductivity? Conductivity, or you call it as specific conductance. You call it as specific conductance. Tell me, how do you define it? Specific conductance is nothing. It is inverse of I'm sorry guys, I think I'm going to fall ill. I think there is going to be cold cough soon. Okay, conductivity. How do we define conductivity? It is defined as inverse of resistivity. Inverse of resistivity. Now tell me one thing. 1 divided by, what is rho exactly equal to? Rho is equal to RA divided by L. Rho is equal to RA divided by L. So this is R, this is A, and this is L here. This is L here, right? You can write it like this. 1 divided by R multiplied by L by A. Perfect. This is one of the expressions which I would want you guys to remember, because I'll be using frequently this expression in the questions. Your conductivity kappa, that's equal to 1 divided by R multiplied by L by A. 1 by R multiplied by L by A. Second thing guys, have a look. I'm talking about conductivity, specific conductance. That is your kappa. That's your kappa. So kappa is equal to 1 by R is something which you call as conductance. L by A is something which you call as cell constant. This is conductance. This term is called as cell constant, right? So I'll write something like this. Conductivity is always equal to conductance multiplied by what? Multiplied by cell constant. Multiplied by cell constant, right? Your cell constant is what? Your cell constant is L by A. This is cell constant, this is conductance, and this is conductivity. Now, if I ask you what are going to be the units of conductivity? Units of conductivity. Say, conductivity is equal to conductance multiplied by cell constant. So, units of conductivity is going to be, this is conductance. You can write it as Simon. Cell constant. This is centimeter square. So, it's going to be centimeter inverse. So, you can write it as Simon centimeter inverse. It is basically the unit of what? It is the unit of conductivity, right? Perfect. It is the unit of conductivity. Simon centimeter inverse. Perfect. Now, my dear students, one more important thing. Before talking about the other terminologies, one more important thing which you should remember from now on. Imagine this is your one electrolytic solution. This is your one more electrolytic solution. Okay? 2 electrolytic solution I have in 2 containers. Right? Imagine the resistance of the first solution is Ra, the resistance of the first solution is Rb. Right? Imagine the conductance of the first solution, conductivity of the first solution is Ka and conductivity of the second solution is Kb. These are 2 solutions. Solution number 1, solution number 2. Now what you are doing, you are mixing it, you are adding them into a final container. So in this final container, we got 1 plus 2. Perfect. You got 1 plus 2. Now, my dear students, remember one important thing. You are not going to say resistance of the final solution is equal to Ra plus Rb. This is a wrong statement. You are not going to do the question in this format, but you will do the question in terms of conductivity. You will say conductivity of the final solution, that is equal to Ka plus Kb. You will solve the question in terms of conductivity, not in terms of resistance, right? You take a note of this point. It's important. From this particular point, you'll get one question. From this particular point, you'll get one question. If you are adding 2 solutions, having the resistance Ra, Rb, conductivity kappa I, kappa B, right? The final solution which you get, you are not going to say its resistance is Re plus Rb. You are going to solve the question in terms of conductivity. You can write conductivity as conductivity of the final solution as conductivity of A plus conductivity of B. Conductivity of A plus conductivity of B. Yeah? Right? Now guys, before doing the other stuff, let me talk about one more important terminology. What is that? That is molar conductivity. Molar conductivity. Molar conductivity is represented by lambda m. Molar conductivity is represented by lambda m. Let me first of all write its definition, then I'll make you understand. molar conductivity lambda, it is defined as the conductance. The conductance shown by all the ions, the conductance shown by all the ions when 1 mole of electrolyte is present, when 1 mole of electrolyte is present in a given volume of solution, in a given volume of solution. Try to understand what it means exactly. See guys, few minutes back, we made a conductivity cell here. Imagine this is the conductivity cell, okay? Imagine this is the conductivity cell. Can I erase all this part? Can I erase all this part? Say yes or no. I just need some space here. Can I erase? Okay, leave it as such. I'm erasing this part. I hope you got to know how this conductivity cell was made. I'm erasing this part. All right. See guys, there is something important which I'm going to discuss with you now. This is your conductivity cell, and this conductivity cell, what is there in this conductivity cell? Electrolytic solution, correct? Imagine volume of the electrolytic solution, volume of the solution here in the container is V centimeter cube. It can be anything, 10 centimeter cube, 1000 centimeter cube, 50 centimeter cube, whatever. This is the volume of the solution, V centimeter cube. I'm assuming that in a given volume of solution, I'm assuming that in a given volume of solution, 1 mole of electrolyte is present. I'm assuming in a given volume of solution, 1 mole of electrolyte is present. So 1 mole of electrolyte is present in a given volume of solution. My dear students, whenever 1 mole of electrolyte is present in a given volume of solution, the conductance of all the ions shown at this particular point of time is something which you call as molar conductivity. So molar conductivity, it is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. I hope it's clear. It is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. Correct? Now guys, I'm directly going to give you the result. I'm not deriving the result. I'll be directly giving you the result. Molar conductivity of the solution is always equal to kappa multiplied by 1000 divided by molarity of the solution. This is the result which you guys will be using to calculate molar conductivity of the solution when you have to calculate molar conductivity in Siemens centimeter square per mole. When you have to calculate the molar conductivity in Siemens centimeter square per mole, this is the equation which you will be using. Kappa multiplied with 1000 divided by molarity of the solution. For example, you have to calculate the molar conductivity in Siemens meter square per mole. If you have to calculate the molar conductivity in Siemens meter square per mole, this is not the relation which you will be using. You will be using the relation like this. Kappa conductivity divided by 1000 multiplied by molarity of the solution. Perfect. My dear students, I want you guys to remember these two expressions. Is this clear? I hope you got to know what molar conductivity exactly is. Say yes or no in the chats. Say yes or no in the chats. Okay. All right. There is one more similar terminology that's called as equivalent conductivity. Which is represented by lambda EQ. Now, how do you define this equivalent conductivity? Let me write its definition. It is similar. Equivalent conductivity is defined as the conductance shown by all the ions when 1 gram equivalent. When 1 gram equivalent of electrolyte. When 1 gram equivalent of electrolyte is present in a given volume of solution. The conductivity cell which I took few minutes back. Imagine in the given volume of solution, there is 1 gram equivalent of electrolyte present. When 1 gram equivalent of electrolyte is present in a given volume of solution, whatever will be the conductance shown by ions at that point of time in the conductivity cell, that is something which I'll be calling as equivalent conductivity. As simple as that. There is one difference only. Instead of 1 mole of electrolyte, you are using 1 gram equivalent of electrolyte, nothing else. Rest everything is same. Okay? Only difference is instead of 1 mole of electrolyte, you are using 1 gram equivalent of electrolyte. That's it. Now, the point is, how do we calculate it? Lambda EQ, one of the result. Kappa multiplied by 1000 divided by normality. This is the equation which you will be using to calculate the equivalent conductivity. To calculate the equivalent conductivity in Siemens centimeter square per equivalent. If you will have to calculate equivalent conductivity under these units, this is the expression which you will be using, right? But if you will have to calculate the equivalent conductivity in Siemens meter square per equivalent, what is the formula which you will be using? It's going to be kappa divided by 1000 multiplied by normal. Perfect. Correct. Now, my dear students, if I ask you, what is going to be the relation between molar conductivity and equivalent conductivity? If I ask you what is the relation between molar conductivity and equivalent conductivity? Molar conductivity and equivalent conductivity. What is going to be the relation? See, since one of the relations I told you, lambda EQ is equal to kappa multiplied by 1000 divided by normality. This is one of the results which I told you, right? Which I gave you. Now tell me one thing. How do I write it like this? Kappa multiplied by 1000 divided by. Instead of normality, I'll write molarity multiplied by n factor. You know it? Normality is equal to molarity multiplied by n factor of solute. Solute is your electrolyte. So normality is molarity of the solution multiplied by n factor of electrolyte. Correct? This particular term, my dear students, this particular term, what do we call this as? We call this as lambda m. So it is going to be lambda m divided by n factor. So from this particular result, you got equivalent conductivity is always equal to molar conductivity of the solution divided by n factor of electrolyte. N factor of electrolyte. This particular result is also important. Is this clear? Is this clear to everyone? Let me know once in the task quickly. Is it clear? Perfect, right? Let's try to do a few questions on the same concepts which we have discussed. Then we'll move on to a few other concepts too. Look at this particular question. Look at this particular question, guys. The specific conductance. Specific conductance means conductivity of 0.1 molar solution of MgCl2 is given. The cell electrodes of 1.5 centimeter square area and placed 0.5 centimeters apart in the solution. How much current should flow if potential difference between electrodes is 5 volts? What are we supposed to calculate? We are supposed to calculate current, right? We are supposed to calculate current. Use the Ohm's law. I is equal to V divided by R, right? Potential difference is 5 volts divided by resistance of the cell we do not know. So we have to calculate resistance of the cell, right? We have to calculate resistance of the cell. Few minutes back, I gave you one result, important result I told you at that time. That is kappa is equal to 1 divided by R multiplied by L by A, right? Now tell me, can't you calculate R from here? 1 divided by kappa multiplied by L by A. It's going to be 1 divided by. This is specific conductance. How much is it? It is 0.009 multiplied by distance between electrodes. Distance between electrodes is 0.5 centimeter. divided by area of cross section of the electrodes, that is 1.5 centimeters square. So from here, you can easily calculate your what? Resistance. Once you get the resistance value, put the value of resistance in this particular equation, you'll get the current. Are you getting this? Are you getting this, people? Right? So resistance is coming as 0.075 ohm and current is coming out to be 0.135 ampere. I believe it's clear. I believe it's clear to everyone. Okay? Let's solve one more question. Let's solve one more question. Look at this. You can easily solve this as well. Now these are simple questions. The resistance of 0.01 normal solution of an electrolyte is 210 ohm. Resistance is given. Cell constant is given. Calculate conductivity and equivalent conductivity of the solution. So we have to calculate conductivity as well as equivalent conductivity. Conductivity is kappa, which is equal to 1 divided by R multiplied by L by A, right? So kappa is going to be equal to 1 divided by R. R is the resistance, which is 210 ohms. L by A is the cell constant. Cell constant is given to us as 0.88 centimeter inverse, right? When you solve this, you get the answer in Simon centimeter inverse. This is your conductivity. This was the first question. Second is calculate equivalent conductivity. Equivalent conductivity is equal to, you have to calculate equivalent, by the way, we have to calculate equivalent conductivity in Simon centimeter square per equivalent. These are supposed to be the units in the question. So lambda EQ is going to be kappa multiplied by 1000 divided by normality, right? Divided by normality. Perfect. Kappa you have already calculated. Normality of the solution is also given. Put it here and get the equivalent conductivity of the solution in Simon centimeter square per equivalent. Done. These are just the formula based ones, right? Just the formula based ones. So kappa you have calculated, put it here and get the equivalent conductivity. That's it. Nothing else to do. These are the basic questions now. These are the basic questions now. Okay? Let's have a look on this question. The equivalent conductivity. The equivalent conductivity of 0.1 normal solution of CaI2 is 100. And its units, you already know, it is Simon centimeter square per equivalent. If the cell constant is this much, how much current will flow when the potential difference between the electrodes is 5 volts? Right? Can you give it a try? Can you give it a try? See guys, what are we supposed to calculate? Again, we have to calculate current. Current is nothing, it's potential difference, voltage divided by R, right? Well, potential difference is given to us as 5 volts again. Now, we have to calculate R. How do we calculate R exactly? How do we calculate R exactly? How do we calculate R exactly? Quickly, how do we calculate R? I told you a few minutes back only, your kappa is equal to 1 divided by R multiplied by L by A. Correct? So R you can calculate as 1 divided by kappa multiplied by L by A. Perfect. Now as per the question, this particular term cell constant, this is given to me. Correct? But this kappa is not given to me. So I have to calculate kappa as well. I have to calculate kappa as well. From where I calculate the conductivity. For that purpose, equivalent conductivity is given. Equivalent conductivity is given to me as 100 Simon centimeter square per equivalent. This is the equivalent conductivity which is given to me. Now you know, equivalent conductivity is equal to kappa multiplied by 1000 divided by normality, right? This is equal to 100. Tell me one thing. Is the normality of the solution given to me? Yes, it's given to me, right? If normality is given, from here, it is given to me as 0.1. From here, you can calculate kappa. Conductivity can be calculated. If conductivity is calculated, put it here. Cell constant already you know, you'll get the resistance. If you got the resistance, put it here, you'll get the current. That's something which you were supposed to calculate, right? Is it clear, people? Is it clear to everyone? Is it clear to everyone? I think we should take a break for some time, then we'll start again, okay? What is the time right now? It is 8:10. So till what time you want the break? Let's meet up at 8:30 again, huh? Or let's meet up at 8:35. We have to complete this chapter, okay? So after the break, we'll have to discuss Kohlrausch law and its applications. Okay? See you after the break, guys. Till then, you guys can have your dinner or something. Okay? But be back on the time. Be back on time, people. Okay? Chalo, see you. See you in some time. Is everyone back? Is everyone back? Yes, let me know in the chats quickly. Let me know in the chats quickly, people. Yes? Yes, chemical kinetics is done in the Concur batch. Yes, yes, you can check it out. Chemical kinetics is done. So, my dear students, let me know quickly in the chats if all the things are clear till here, so that we can move ahead and do the last part of the chapter. Let me know once in the chats if all the things are clear. Quickly, everyone. So, let's talk about first of all the effect of dilution. Effect of dilution on conductivity, molar conductivity, and equivalent conductivity. What happens to conductivity, molar conductivity, and equivalent conductivity with dilution? Let's have a look, people. All right. See, first of all, if I particularly talk about conductivity, how do you exactly define conductivity? We have already defined it. I hope you remember. How did we define conductivity? Conductivity was defined as, the conductance shown by 1 centimeter cube of an electrolytic solution, right? The conductance shown by 1 centimeter cube of electrolytic solution, correct? Try to understand what exactly I'm going to say, my dear students. First of all, I'm going to make the conductivity cell again. So first of all, this is the cube which I'm making over here. From this particular cube, you'll get the idea what happens to conductivity, okay? So imagine this is the conductivity cell which I'm again making, and these are the plates. These are the plates which are basically inside the electrolytic solution. I hope you remember from where we got this conductivity cell, right? Now, my dear students, inside this particular cube, we have got the electrolytic solution. I hope you remember. This is something which we have already discussed. Let's call this as the negatively charged plate. Let's call this as the positively charged plate. Perfect. If you remember from where we got this cube, we got this cube from the electrolytic cell basically. We took this cube out. And this shaded part, what is this shaded part? It is the part of the electrode that is inside the solution. Actually, this is the actual size of the electrode. This is basically the actual size of the electrode, right? This is the actual size of the electrode, and this part of the electrode is inside the solution. I hope this is clear. Okay? And my dear students, if you remember, the distance between these two electrodes is represented by what? It's represented by L centimeters. And that area of cross section which is inside the solution, that is represented by A centimeter square. Perfect. My dear students, how do we define the conductivity? It is the conductance shown by 1 centimeter cube of the solution. Imagine the volume of this particular solution, the volume of this electrolytic solution, for example, is 100 centimeter cube. It is 100 centimeter cube. Let's assume that in this 100 centimeter cube electrolytic solution, let's assume that there are, for example, some 500 ions present. There are some 500 ions present. Okay. So if in 100 centimeter cube, there are 500 ions present, can you let me know in 1 centimeter cube, how many ions will be present? 500 by 100, that comes out to be 5 ions. So if in 100 centimeter cube solution, there are 500 ions, that means in 1 centimeter cube of solution, there are 5 ions present. Perfect. So that means whatever will be the value of conductivity, that is due to these 5 ions. Correct? Now try to understand. Imagine that you are adding some extra solvent here. So you are doing the dilution. That means you are doing the dilution. You are adding some extra solvent here. My dear students, on adding the extra solvent, what will happen to the volume of solution? Volume of solution will increase. Initially, the volume of solution was 100 centimeter cube, right? Now, due to dilution, let's assume that the volume of the solution reached 1000 centimeter cube. Imagine due to dilution, volume of the solution reached 1000 centimeter cube. What did we do? We just added solvent. Did I do anything to the solute? Did I add some more electrolyte here? No. The amount of electrolyte in the container is same. It is just I'm adding more solvent. Okay. After the addition of more solvent, this volume of the solution increased. Volume of the solution increased to 1000 centimeter cube. Now, in 1000 centimeter cube, how many total ions will be there? Total ions will be still 500 only. Because I did not add some electrolyte. I did not add more electrolyte. Electrolyte is same. Now tell me, this was the case of before dilution. And this is the case of after dilution. Tell me one thing. If in 1000 centimeter cube, there are 500 ions. Tell me, in 1 centimeter cube of solution, how many ions will be there? How many ions will be there? Let me not call it as 5000. Let me call it as, just a second, otherwise calculation will be wrong. Let's say after dilution, the volume of the solution is 500 centimeter cube. After dilution. So 500 centimeter cube of solution contains 500 ions. So 1 centimeter cube of solution will contain 1 ion. 1 centimeter cube of solution will contain 1 ion. My dear students, can I say, due to dilution, due to the addition of extra solvent, the number of ions per unit cube of the solution, decreased? Can I say something like that? Initially, before dilution, in 1 centimeter cube of solution, there were 5 ions, right? So conductivity was due to 5 ions. Now, due to dilution, volume of the solution increased. Now, for example, volume of the solution now is 500 centimeter cube. Now, in 500 centimeter cube, I must say there are still 500 ions only, right? So, in 1 centimeter cube of solution, there is 1 ion. So, due to dilution, what is happening? Number of ions per unit volume. Number of ions per unit volume were initially 5. And now, due to dilution, number of ions per unit volume is 1. So, I would say due to dilution, number of ions per unit volume of the solution decreases. Right? I'll say due to dilution, I would say number of ions in 1 centimeter cube of solution, 1 centimeter cube of electrolytic solution, that decreases. And my dear students, it's understood, if number of ions in 1 centimeter cube of solution decreases, what will happen to conductivity? Conductivity automatically will decrease. So do remember, conductivity of the electrolytic solution, it decreases with dilution. Is this point clear to everyone? This was our first point. Okay? Let me know once in the chats if this point is clear. Number of ions in 1 centimeter cube of solution are decreasing. If number of ions are decreasing, that automatically tells you that conductivity of the solution is decreasing, right? Because what is conductivity? It is the conductance shown by all the ions in 1 centimeter cube of solution. If in 1 centimeter cube of solution, number of ions are decreasing due to dilution, that automatically tells you the conductivity is decreasing with the dilution. Perfect. So this was your conductivity part. Now let's have a look on molar conductivity now. What happens to the molar conductivity? What happens to the molar conductivity with dilution? What happens to the molar conductivity with dilution? First of all, how do you define the molar conductivity? Do you remember? How do we define the molar conductivity? It is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. I hope you remember. Let's say this electrolytic solution which is there in the container. Let's say volume of this electrolytic solution is, for example, V centimeter cube. Volume of this particular electrolytic solution is V centimeter cube. And in this given volume of solution, let's assume that there is 1 mole of electrolyte present. There is 1 mole of electrolyte present. So I'm assuming 1 mole of electrolyte is present in this given volume of solution. So whatever conductance this particular solution shows right now, that is something which I call as molar conductivity. That is something which I call as molar conductivity. Now what happens to molar conductivity with the dilution? That is the discussion. Imagine that in this particular solution, the electrolyte which we have used, for example, that is a strong electrolyte. For example, that is a strong electrolyte. I'm assuming that in this particular given volume of solution, there is 1 mole of strong electrolyte present. There is 1 mole of strong electrolyte present. Strong electrolyte is the one which gets completely dissociated into its ions. So if 1 mole of strong electrolyte is in this particular solution, that 1 mole of electrolyte would have got completely converted into its ions. Now, my dear students, what all types of ions will be there in the container? There will be cations and anions in the container. There will be cations as well as anions in this particular container. Perfect. Now, imagine you are doing dilution. If you are doing dilution, that means you are adding some extra solvent. If you are putting some extra solvent in this solution, what is happening to the volume of solution? Volume of the solution is increasing. If volume of the solution is increasing, the distance between the oppositely charged ions, that will increase. And if the distance between oppositely charged ions increases, the force of attraction between them decreases. And if the force of attraction between these ions is decreasing due to dilution, I'll say due to dilution, since force of attraction between these ions is decreasing, I'll say due to dilution, the ions will start moving freely comparatively. And more the movement of ions, more has to be the molar conductivity. Done and dusted, right? Clear, guys? Clear? So I had 1 mole of strong electrolyte in this solution. And whatever conductance this solution was showing, that was called as molar conductivity of this solution. Now you are adding some extra solvent. Due to the addition of extra solvent, what is happening to the distance between the ions? It is increasing. Force of attraction between the ions, it's decreasing. Now the ions can comparatively move freely, right? Ions can comparatively move freely. If the ions can comparatively move freely, I would say molar conductivity of this solution automatically increased, right? So do remember, in case of strong electrolytes, with dilution, molar conductivity of the strong electrolyte, that increases. What is the reason? Reason is the distance between the ions, that increases, right? I'll say the reason is distance between the oppositely charged ions, that increases. Hence, force of attraction between the ions decreases, and eventually the ions start moving comparatively freely. Ions start moving comparatively freely. I hope this point is clear to everyone. Is this point clear to everyone? Quickly in the chats. Yeah. Now, my dear students, as I told you, With dilution, molar conductivity completely increases. It keeps on increasing. With dilution, molar conductivity keeps on increasing. So if I keep on doing the dilution, if I keep on adding the solvent, molar conductivity of this solution will keep on increasing. Molar conductivity will keep on increasing. And my dear students, there will be a time when this particular solution shows maximum molar conductivity. And when this particular shows maximum molar conductivity, when the distance between the ions will be infinite, at that time, there will be no force of attraction between the ions. At that time, ions can completely move freely. Okay? So with dilution, molar conductivity of this solution, of this electrolytic solution, it is increasing, right? If you keep on continuously doing the dilution, molar conductivity will keep on increasing. The ions will go far, right? Okay? There will be a time when these ions will be at infinite distance apart. At that point of time, force of attraction between the ions will be zero. So at that point of time, there is maximum free movement of these ions. So if there is maximum free movement of ions, I'll say molar conductivity value of this particular solution will be maximum. And at that point of time, when the molar conductivity of the electrolytic solution attains its maximum value, we say that dilution at which the molar conductivity of the solution attains its maximum value, that dilution is something which we call as infinite dilution. Let me know once in the chats if you got the idea of what infinite dilution is. So I'll write it over here. If I keep on doing the dilution continuously, then there'll be a point which is what we call as infinite dilution. There'll be a time which is what you call as infinite dilution. So at infinite dilution, distance between the ions is infinite. Force of attraction, zero. Ions will move freely. I'll say lambda m, molar conductivity, attains its maximum value. And the maximum value of molar conductivity, is something which you call as molar conductivity at infinite dilution, or it is represented like this, lambda m infinite. Perfect. Is this clear? Same thing happens to equivalent conductivity as well. Equivalent conductivity also increases with the dilution. And at infinite dilution, equivalent conductivity attains its maximum value, which is what you call as equivalent conductivity at infinite dilution. Right? Perfect. I'll say equivalent conductivity also increases and hence attains its maximum value, which is what you call as equivalent conductivity at infinite dilution, or you can represent it like this. Perfect, guys. So in case of strong electrolytes, if the electrolytic solution contains a strong electrolyte, with dilution, its molar conductivity as well as equivalent conductivity increases because ions, they go far. So when you keep on doing the dilution continuously, at infinite dilution, there'll be maximum distance, infinite distance between the oppositely charged ions in the container, due to which no force of attraction between the ions, due to which ions are moving freely. So the maximum molar conductivity value or the maximum equivalent conductivity value will be there at infinite dilution. Perfect. My dear students, if you want to understand it with the help of graph, if I plot a graph for a strong electrolyte, and the graph is between lambda m versus under root of C, where C is the concentration of electrolyte in the container. So first of all, what is C? Concentration. Concentration means moles per unit volume. Perfect. Tell me one thing. This graph I'm plotting for the strong electrolyte first of all. Okay. At this particular point of time, what is root C value? Root C value here is 0. At this point, root C value is 0. If root C is 0, that means C is 0. When will be C 0? C will be 0 at infinite dilution, when volume of the solution, volume of the electrolytic solution had become infinite, right? So this point represents your infinite dilution. And infinite dilution, molar conductivity of the strong electrolyte, right? Molar conductivity of the electrolytic solution that attains its maximum value. And that maximum value is lambda naught m. So at this point represents your infinite dilution. This point represents infinite dilution. At infinite dilution, molar conductivity attains its maximum value, which is lambda naught m. Let's assume that this point is lambda naught m. This point is lambda naught m. Now tell me one thing. This is infinite dilution, at which volume of solution had become infinite. Now, if you go in this direction, in this positive x-axis direction, what is happening to root C value? If you go in this direction, root C value is increasing. If root C is increasing, that means C is increasing. If root C is increasing, that means C is increasing. C increasing means volume of the solution is decreasing. At this point of time, volume of the solution was infinite. Now you are going in this direction. C is increasing, right? That means V is decreasing, volume of the solution is decreasing. Initially, the volume of the solution was infinite. Now, volume of the solution is decreasing. If volume of the solution is decreasing, that means the oppositely charged ions in the container, they are coming closer. If they are coming closer, distance between them decreases. If distance between the oppositely charged ions decreases, force of attraction between them increases. Now the ions cannot move the way they were, right? The way they were moving. Therefore, what will happen to molar conductivity? Molar conductivity will decrease. So, molar conductivity value, it will keep on decreasing with time. Perfect. But this particular graph, it is valid for what? It's valid for strong electrolyte. Okay. Now tell me one thing. Since this particular graph, can you tell me what will be its equation? Its equation. See, there is an intercept, there is a negative slope. So it will follow this type of the equation. Y is equal to minus mx plus c. This particular graph will follow this particular equation. Y is equal to minus mx plus c. Now along y-axis, what are you plotting? Along y-axis, you are plotting lambda m is equal to minus. M is the slope of the curve. Let's say slope of the curve is represented by a. What is x? Along x-axis, you are plotting root c. And what is this particular c? C is the intercept. Intercept is the distance from here to here, which is lambda naught m. This is the equation which correctly represents the behavior of strong electrolyte when the behavior of molar conductivity of strong electrolyte when it undergoes dilution. Perfect. This particular equation is valid for a strong electrolyte when it undergoes dilution. I hope this is clear. Right? I hope this is clear. Now, my dear students, when you talk about the weak electrolytes, imagine that in this container, you have got a weak electrolyte. Imagine that you have got 1 mole of weak electrolyte. You have got 1 mole of a weak electrolyte in a given volume of solution. Okay? Right? Imagine that you have got 1 mole of weak electrolyte in a given volume of solution. So whatever conductance this particular solution will be showing, what you call as molar conductivity, right? Now, if there is weak electrolyte in the container, what will happen to the dilution? Let's check that too. For example, there is a weak electrolyte in the container. If there is weak electrolyte in the container, tell me about weak electrolyte. Weak electrolyte gets partially ionized. That does not get 100% dissociated into its ions. Now, my dear students, with dilution, if you remember, with dilution, degree of dissociation of a weak electrolyte, what happens to it? With dilution, the degree of dissociation of a weak electrolyte that increases, correct? That increases. With dilution, degree of dissociation of a weak electrolyte that increases as per Ostwald's dilution law, right? Now, if the degree of dissociation of a weak electrolyte increases, can I say number of ions in the solution, they are increasing. If number of ions in the solution are increasing, I directly say molar conductivity of the solution increases as well as equivalent conductivity of the solution increases. So molar conductivity as well as equivalent conductivity of the weak electrolytic solution that also increase with dilution. But the reason is different. Reason here is, as the dilution is done, degree of dissociation of the weak electrolyte increases, more ions will enter into the solution, more the ions, more will be the molar conductivity as well as equivalent conductivity, right? And molar conductivity at infinite dilution, that's what you call as lambda naught m. Similarly, equivalent conductivity at infinite dilution, that is lambda naught EQ. Now, my dear students, if you try to draw the graph between lambda m versus root c for a weak electrolyte. For a weak electrolyte, the graph comes like this. The graph comes like this. It's a hyperbola, right? The graph comes like this, right? The graph comes like this. Now tell me one thing. At this particular point, root C value is 0. That means C is 0. When is C 0? I told you a few minutes back. When is C 0? C is 0 when volume of the solution is infinite. That means this particular point, it represents infinite dilution. It represents infinite dilution. Since I told you with dilution, the degree of dissociation keeps on increasing, right? If you continuously keep on doing the dilution, can I say there will be a time when the weak electrolyte would have got 100% ionized? And that point when the weak electrolyte would have got 100% ionized, that dilution I call as infinite dilution, right? If this point represents infinite dilution, so I would say at this particular point of time, the electrolyte would have got 100% ionized. The electrolyte would have got 100% converted into its ions. So at infinite dilution, there will be maximum ions in the container. So molar conductivity as well as equivalent conductivity would have attained its maximum value, which is what you call as molar conductivity or equivalent conductivity at infinite dilution, right? Perfect. That's why the graph started somewhere here. Now, my dear students, as you go in the right direction, root C is increasing. If root C is increasing, that means C is increasing. If C is increasing, that means volume is decreasing. If volume is decreasing, volume of the solution is decreasing, what does that mean? That means the degree of ionization of the weak electrolyte. What is happening to that? Or let me make it simple. I told you, when you do the dilution of the weak electrolyte, number of ions in the container increases, right? Due to dilution, volume of the solution increases. So in short, I'll say, when the volume of the solution keeps on increasing with dilution, number of ions in the solution keeps on increasing, right? Now the volume of the solution is decreasing. In this direction, volume of the solution is decreasing. If volume of the solution is decreasing, what does that mean? That means number of ions in the solution will be decreasing. If number of ions in the solution are decreasing, I'll say molar conductivity as well as equivalent conductivity, they'll be decreasing also. Perfect. But from this graph, are you able to find the molar conductivity at infinite dilution? See, from this particular graph, you were able to find the molar conductivity at infinite dilution with the help of this intercept. But in this particular curve, do you have any intercept? There is no intercept. So from this particular curve, which is valid for a weak electrolyte, from this particular curve, you cannot calculate the molar conductivity at infinite dilution for a weak electrolyte. But for strong electrolytes, we can do with the help of the graph, with the help of its intercept. Now the point is how to calculate the molar conductivity and equivalent conductivity at infinite dilution for a weak electrolyte. If it cannot happen through this particular graph, if you are unable to get the molar conductivity at infinite dilution for a weak electrolyte from the graph, if you are unable to do that, then how do we get the molar conductivity at infinite dilution for a weak electrolyte? My dear students, in order to get the molar conductivity at infinite dilution as well as equivalent conductivity at infinite dilution for a weak electrolyte, in order to get those values, I'm going to introduce one more topic, that is what you call as Kohlrausch law. That's what you call as Kohlrausch law. Kohlrausch law. So what this Kohlrausch law exactly states? See, you can read its definition. This law states that the equivalent conductivity of any electrolyte at infinite dilution is the sum of equivalent ionic conductivities of cation and anion given by the electrolytes at infinite dilution. What it means exactly? What it means? Let's try to understand. First of all, whenever there is infinite dilution, at infinite dilution, 100% electrolyte is ionized. At infinite dilution, the distance between the oppositely charged ions in the solution, that is infinite. Force of attraction between the oppositely charged ions, that is 0. So that means I can say at infinite dilution, ions, they move freely, right? They move freely. So at infinite dilution, the ions move freely. This is something which is understood. Now, my dear students, try to understand. Try to understand what exactly I'm going to say. See, for example, in the conductivity cell, Let's say you have got an electrolyte like NaCl. You have got an electrolyte like NaCl. Perfect, like NaCl. First of all, how this NaCl would have got dissociated? It would have got dissociated as Na positive plus Cl negative. Stoichiometric coefficient 1, here it is 1, here it is 1. Perfect. Now, Kohlrausch law says that molar conductivity of this NaCl, for example, at infinite dilution is the sum of conductivities of its ions, basically. So basically, since this electrolyte at infinite dilution, it's 100% ionized, right? Number one, it's 100% ionized. There is no force of attraction between the ions. Ions are moving freely. So it is the ions basically which contribute. Towards the molar conductivity of the electrolyte at infinite dilution. So molar conductivity of the electrolyte at infinite dilution, as per Kohlrausch law, is the sum of those contributions. Which are made by the ions. What it means? Have a look. Molar conductivity of NaCl at infinite dilution. See, how do you write it as per your Kohlrausch law? The stoichiometric coefficient here is 1. So write 1 first, then write molar conductivity at infinite dilution for Na positive plus, this is 1 also, right? Molar conductivity at infinite dilution of Cl negative. Correct? For example, you have got electrolyte like this. You have got, for example, BaCl2. At infinite dilution, BaCl2, first of all, it would have got completely dissociated into its ions, right? And at the same time, the force of attraction between the oppositely charged ions at infinite dilution will be 0, right? So these ions will be moving freely. Now, as per Kohlrausch law, lambda naught m of BaCl2, will be equal. The stoichiometric coefficient here is 1. So 1 multiplied by lambda naught m of Ba di positive plus 2 multiplied by lambda naught m of Cl negative. Correct? Perfect. For example, you have got electrolyte like this. Al2SO4 whole thrice. How it would have got dissociated at infinite dilution? It is 2 times Al tri positive plus 3 times SO4 di negative. Now, if you want to write the molar conductivity at infinite dilution for Al2SO4 whole thrice, you can write it like this. Start with 2, then write molar conductivity at infinite dilution for Al tri positive plus 3 times the molar conductivity at infinite dilution for SO4 di negative. Perfect. Can you write these statements for every electrolyte? You should be able to write these particular statements, correct? You should be able to write these particular statements for the electrolytes. Now, my dear students, let me tell you one more thing. Since you are getting the molar conductivities of electrolytes at infinite dilution, like this, if I ask you how do you get the equivalent conductivity of the electrolyte at infinite dilution? Already, if you remember, I've already discussed one relation with you. Equivalent conductivity is equaled molar conductivity divided by n factor of the electrolyte. We have discussed this relation. Perfect. So, if you get molar conductivity at infinite dilution of the electrolytes, once you get the molar conductivities, you can easily calculate their equivalent conductivities at infinite dilution. So, equivalent conductivity at infinite dilution will be equaled molar conductivity of the electrolyte at infinite dilution divided by n factor of this particular electrolyte. I hope this is clear. I hope this particular statement is clear. Right? I hope this particular statement is clear. Perfect. Perfect, guys. One more thing. For example, I'm writing a statement like this. Let's say I already know equivalent conductivity at infinite dilution of Na positive. Let's say this is something I know. I already know equivalent conductivity of Cl negative at infinite dilution in equivalent conductivities, right? I already know equivalent conductivity at infinite dilution of Ba di positive. These are the terms which I already know, correct? Now, if you want to write directly the equivalent conductivity of NaCl, when you directly want to write equivalent conductivity of NaCl in terms of equivalent conductivity at infinite dilution for their ions, in terms of their ions. Listen to me carefully. Imagine equivalent conductivity at infinite dilution for Na positive, you know, this one you know, this one you know, right? Now I want you directly to write the equivalent conductivity of at infinite dilution for NaCl, right? That too in terms of the equivalent conductivities of their ions. That too in terms of their equivalent conductivities of their ions at infinite dilution. You do not have to talk about these stoichiometric coefficients at that particular point of time. You can directly write lambda naught EQ of Na positive plus lambda naught EQ of Cl negative. Perfect. For example, here I was writing the molar conductivity of BaCl2. I was taking into consideration these stoichiometric coefficients. But if you are directly writing the equivalent conductivity at infinite dilution in terms of the equivalent conductivities of their ions, then you do not have to talk in terms of, you do not have to write the stoichiometric coefficients here. For example, let me make it clear. Let's say I'm writing equivalent conductivity at infinite dilution of BaCl2. If you want to write it in terms of equivalent conductivities of their ions, you do not have to, you have got nothing to do with the stoichiometric coefficients. You'll directly write equivalent conductivity of Ba di positive plus equivalent conductivity of Cl negative. Nothing to do with their stoichiometric coefficients. But if you are writing molar conductivity at infinite dilution for BaCl2, right, you will be writing lambda naught m of Ba di positive plus 2 times lambda naught m of Cl negative. I hope these two statements are clear to you. Yeah? I hope these two statements are clear to you. Perfect, guys? And at the same time, if you directly know the molar conductivity at infinite dilution of an electrolyte, divide it with the n factor of electrolyte, you will get directly the equivalent conductivity of the same electrolyte at infinite dilution. One more important thing. All these things are very, very important, guys. All these things are very, very important. These are very small things wherein majority of the students, they do the mistake. Okay? Perfect. Now, let's exactly get to know how this Kohlrausch law is, how this is used basically. Where all do we use this Kohlrausch law? Number one, Kohlrausch law exactly is used to calculate the limiting molar conductivity of a weak electrolyte. Limiting molar conductivity of a weak electrolyte means Kohlrausch law is used to calculate the molar conductivity of a weak electrolyte at infinite dilution. Because from the graph, we could not get the molar conductivity at infinite dilution of a weak electrolyte. So it is the Kohlrausch law which is going to give us the molar conductivity at infinite dilution of a weak electrolyte. This is the first application. To calculate, you can write it as like this. To calculate the limiting molar conductivity. Of a weak electrolyte. This is the first application. This is the first application of the Kohlrausch law. To calculate the limiting molar conductivity of a weak electrolyte. To calculate the molar conductivity at infinite dilution of the weak electrolyte. Okay. Now, how exactly? It's simple, guys. Have a look. Understand properly. For example, molar conductivity at infinite dilution for HCl is given to us. Okay. NaCl is also given to us. CH3COO Na is also given to us. These are few parameters which are given to me. And by looking at these parameters, we have to calculate the molar conductivity at infinite dilution for CH3COH. Correct? How exactly I'll get this particular term from these terms? Now understand. Simple thing it is. Understand it properly. So first of all, lambda naught m of HCl. I can write it as lambda naught m of H positive plus lambda naught m of Cl negative. Correct? Because stoichiometry is 1:1. And this value is already given to me as 426 centimeters square per mole. Lambda naught m of NaCl, I can write it as lambda naught m of Na positive plus lambda naught m of Cl negative. And this particular term is given to me as 126. Lambda naught m of CH3CONA. It is going to be equal to lambda naught m of CH3CO negative plus lambda naught m of Na positive. And this value is equal to 91. So how many equations do I have? How many equations do I have? I have got 3 equations. From these 3 equations, I have to get this particular value, lambda naught m of CH3COH. First of all, how do you break this CH3COH? I say basically I have to get this value, lambda naught m of, I have to get basically the value of lambda naught m of CH3CO negative plus lambda naught m of H positive. Basically, this is the value which I need to get. This is the value which I need to get. Perfect. Now, my dear students, how do you get this value? How do you get this particular value out of these 3 equations? This is equation 1, call this is equation 2, call this is equation 3, right? How do you get it? How do you exactly get it? What do you need exactly? You need lambda naught CH3CO negative and lambda naught H positive. So you need this term and you need this particular term. Perfect. Rest all the terms should get cancelled. Rest all the terms should get cancelled. Perfect. So I'll be adding equation 1 with equation 3 and I'll be subtracting equation 2. I'll be adding 1 with 3 and subtracting 2 at the end. Perfect. If I subtract 2, this becomes minus, this becomes minus, this becomes minus. Perfect. What do I get at the end? I'll say this particular term gets cancelled. This particular term gets cancelled. What do I get at the end? Lambda naught CH3CO negative plus lambda naught. After doing this particular operation, what am I left with? I'm left with lambda naught of H positive plus lambda naught of CH3CO negative. Perfect. Lambda naught H positive plus lambda naught CH3CO negative. What do I call this as? I'll be calling this particular term as lambda naught M of CH3COH. Perfect. How did I get this? By doing this particular operation. Same operation you are going to do with these molar conductivities. So 1 plus 3 minus 2. So 1 plus 3 minus 2. So it has to be 426, 1 plus 3 minus 2. Whatever value you get from here, that is going to give you the molar conductivity at infinite dilution for this particular weak electrolyte. Did you get it? Did you get it properly? Let me know once in the chats quickly, guys. Quickly, everyone. Did you get this particular term? Let me give you one more question. Let me see if you can solve this or not. The question is like this. I'm giving you lambda naught M of NaCl. This value I'm giving you as, for example, 126.5 Simon centimeter square per mole. This is the value which I give you. Second value I'm giving you as lambda naught M of HCl. This is something which I'm giving you again. This value is something 425.9 Simon centimeter square per mole. Right? Similarly, I'm giving you one more value. Lambda naught M of NaI. This value is 91 Simon centimeter square per mole. And I'm asking you to calculate lambda naught M for HI. This is something which you are supposed to calculate. Can you give it a try? Can you give it a try? My dear students, same thing you have to do. Same thing you have to do. First of all, lambda naught M of NaCl can be written like this. Lambda naught M of Na positive plus lambda naught M of Cl negative. This particular term I'll be writing as lambda naught M of H positive plus lambda naught M of Cl negative. This particular term I'll be writing as lambda naught M of Na positive plus lambda naught M of I negative. This particular term I'll be writing as lambda naught M of H positive plus lambda naught M of I negative. This is something which is to be calculated. Let's call this as equation 1. Let's call this as 2. Let's call this as 3. From these equations, in total there are 1, 2, 3, 4, 5, 6 terms. Out of 6 terms, from these 6 terms, I should get only lambda naught H positive plus I negative. So there should be only H positive and there should be I negative. Rest all the things should be cancelled out. So what I should be doing? I'll be just doing one thing. I'll do equation 2 plus equation 3 minus equation 1. Let's see what I'll be getting. I'm subtracting equation number 1. So lambda naught Na positive is cancelled. Lambda naught Cl negative, lambda naught Cl negative is cancelled. So what I'm left with? I'm left with lambda naught H positive plus lambda naught I negative. So I got lambda naught H positive plus lambda naught M of I negative. This is something which I call as lambda naught M of HI. Now, how did I get this basically? How did I get this? By adding second with third and subtracting first. Adding second with third and subtracting first. Do the same operation with their molar conductivity values. So 2 plus 3. So this plus this minus this. So the answer has to be 425.9 plus 91 minus 126.5. Solve it. Whatever value you get, the answer is going to be Simon centimeter square per mole. This is the molar conductivity at infinite dilution for this particular electrolyte HI. I hope this is again clear to everyone. So this was the first application of the Kohlrausch law, right? To get the limiting molar conductivity, to get the molar conductivity at infinite dilution for a weak electrolyte, correct? Now what about its second? What about its second application? Its second application is calculation of degree of dissociation for a weak electrolyte. Calculation of degree of dissociation for a weak electrolyte. This is one more application part of Kohlrausch law. This is one more application part of Kohlrausch law. My dear students, understand. Degree of dissociation. I'm directly going to give you the result. I'm not going to derive it, right? I'll give you the result and we'll try to apply it in the questions. Okay? Directly I'm giving you the result. Degree of dissociation of a weak electrolyte as per Kohlrausch law is equal to molar conductivity of a weak electrolyte at a given concentration divided by molar conductivity of the same weak electrolyte at infinite dilution. What is the given concentration? What is infinite dilution? See, you know it already. I'm directly giving you the result. I'm not deriving it again and again, right? See guys, for example, you have got weak electrolyte like this, CH3COH. Let's assume I've got 0.1 molar CH3COH. Perfect. When the concentration of CH3COH is 0.1 molar, let's assume its molar conductivity at that point of time. For example, to make you understand, let's say it's 1 Simon centimeter square per mole. Perfect. Now, my dear students, let's assume you already know the molar conductivity of CH3COH at infinite dilution. Let's say it's 100 centimeter square per mole. Perfect. This particular term I'll be calling as molar conductivity at a given concentration. This is something which you call as molar conductivity at infinite dilution. So molar conductivity at given concentration divided by infinite dilution. So this divided by this will give you the value of alpha for CH3COH. It will give you the value of alpha for CH3COH. Remember it directly. I hope you got to know what is molar conductivity of a weak electrolyte at a given concentration. I hope you got to know that. Now, where do we use it? That is the point. My dear students, this alpha, you can talk about its one more application. Say, for example, you have got a weak electrolyte. Let's say you have got a weak electrolyte AB. Perfect. If it is a weak electrolyte, it will definitely be in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. Correct, guys? Let's assume its degree of dissociation is alpha, and initially at time t is equal to 0, its concentration is C. I'm assuming that the ionization constant of this weak electrolyte is Ki. Ki represents ionization constant of the weak electrolyte. My dear students, we can calculate ionization constant of a weak electrolyte in terms of lambda m and lambda naught m. We can do that. How exactly? Dekho. This is C. This has to be 0 initially. This has to be 0. Now, at equilibrium, this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. If I want to write the expression for ionization constant of this weak electrolyte, expression will be simply C alpha square divided by 1 minus alpha. Right? It is C alpha square divided by 1 minus alpha. Now, my dear students, already alpha you know. Alpha is equal to what? Alpha is molar conductivity of the weak electrolyte at a given concentration divided by molar conductivity of the same weak electrolyte at infinite dilution. So this is C. Alpha is molar conductivity of the same weak electrolyte at a given concentration divided by at infinite dilution. What? Raise power 2. This is C alpha square. C alpha square divided by 1 minus alpha. 1 minus alpha. Now, when you solve it, you get the ionization constant of the weak electrolyte like this. C, you are going to write as such. This is molar conductivity at a given concentration, the square, right? The square divided by, it's going to be lambda naught m multiplied by lambda naught m minus lambda mc, correct? This is how you get the ionization constant. This is how you get the ionization constant of the weak electrolyte in terms of lambda m naught and lambda mc. Perfect? Or in short, if you will be given with a weak electrolyte, just calculate its alpha first of all in terms of these two values. If you got its alpha value, if you got alpha, put it here in this expression, get the Ki value. No need to get this one as well. No need to write it. No need to remember it. Perfect? Right, guys? Is it clear? Is it clear? Is it clear? Let me know once in the chats. Let's try to do few questions on the same concept. Then only you will try to understand where it is used exactly. My dear students, I'm going to write a question. The question is like this. Just a second. The question is molar conductivity at infinite dilution of CH3COH. It is given to me as 390.7 Simon centimeter square per mole. This is the value which is given to me. At the same time, when the concentration of CH3COH is kept 0.1 molar. When the concentration, 0.01 molar this is. When the concentration of CH3COH is kept 0.01 molar. At that point of time, it's molar conductivity. So it is molar conductivity at a given concentration. It is molar conductivity at a given concentration for CH3COH. This particular value is given to me as 3.907 Simon centimeter square per mole. What am I supposed to calculate? I'm supposed to calculate degree of dissociation of CH3COH, and at the same time, I'm supposed to calculate pH of solution. These are the two things which I'm supposed to calculate. Can we give it a try? My dear students, the weak electrolyte that's given to me as CH3COH. Its molar conductivity at infinite dilution is given. Its molar conductivity at 0.01 molar concentration is also given. We have to calculate alpha as well as pH. Now, what is alpha basically? Alpha is nothing. It is molar conductivity of CH3COH at a given concentration divided by molar conductivity of CH3COH at infinite dilution. This is equal to this particular term. It is given to me as 3.907, and this particular term, it is 390.7. The value comes out to be 10 raised power minus 2. So you got the alpha value. You already got the alpha value. Perfect. Now second thing. We have to calculate pH as well. Now tell me, this CH3COH, how it would have undergone dissociation. It would have undergone dissociation like this. CH3CO negative plus H positive. Correct? CH3CO negative plus H positive. Right, people? Now, initially, I'm keeping its concentration as C, which is equal to 0.01 molar. This is 0, this is 0. Now tell me at equilibrium, this is going to be C minus C alpha, this will be C alpha, this will be C alpha. So if I ask you, what about the concentration of H positive here? Concentration of H positive in the solution will be C alpha. C value already you know, that is 0.01. Alpha value you got, that is 0.01. So the value comes out to be 10 raised power. This is 10 raised power minus 2. C, alpha is 10 raised power minus 2. So this is 10 raised power minus 4. So you got the H positive concentration. If you got the H positive concentration, can't you calculate pH? pH is nothing, that's minus log of H positive concentration. So it is minus log of 10 raised power minus 4. So the pH of the final solution comes out to be 4. Isn't this clear? Isn't this clear to everyone, people? Yeah? Perfect. Perfect. Now, one last application of the Kohlrausch law, and with that, we'll end the session, okay? Guys, is it clear till here? Let me know in the chats quickly. The last application part of the Kohlrausch law, what is that? That is calculation of solubility and solubility product for a sparingly soluble salt. I hope you have studied ionic equilibrium, which I did a few days back only on this channel, right? First of all, sparingly soluble salt is the one whose solubility is very, very, very less. You know that, right? Sparingly soluble salt is the one whose solubility is very, very, very less. So basically, whenever I talk about the sparingly soluble salt, it means the salt with very less solubility. The salt with very less solubility. So imagine that you have got a solution in which you have got sparingly soluble salt. That sparingly soluble salt is very less soluble. What does that mean? That means the concentration of the salt in the solution will be very, very, very less. Right? If you have got a sparingly soluble salt in the container, for example, in the solution, for example, that means the solubility of the sparingly soluble salt is very less. Correct? What does that mean? That means the concentration of the salt in the solution will be very less. Concentration of salt in the solution is very less means concentration of the salt is approaching towards zero. You have got a sparingly soluble salt. My dear students, sparingly soluble salt, its solubility is very less, right? So its concentration in the solution will be very, very, very less. So I would say concentration of the sparingly soluble salt in the solution will be approaching towards zero. Perfect. Right? Now, molar conductivity of the sparingly soluble salt, I'm representing with lambda m. I'm representing with lambda m. Do you remember when the concentration is zero? When the concentration exactly is zero? At infinite dilution. Concentration is zero at infinite dilution, if you remember. At infinite dilution, root C is zero. That means C is zero. So concentration is equal to zero represents infinite dilution. Concentration is equal to zero represents what? Infinite dilution. So can I say molar conductivity of a sparingly soluble salt will be taken equal to the molar conductivity of it at infinite dilution? Both the things will be taken same. Did you get this particular point? Did you get this particular point? So, I believe this particular point is clear to everyone. Let me know in the chats if this particular point is clear. This is important, guys. Sparingly soluble salt, its solubility is very, very, very less. Its concentration in the solution will be approaching towards zero. So I'll say molar conductivity of a sparingly soluble salt is same as that of its molar conductivity at infinite dilution. Right? Because at infinite dilution, C value is zero. Now, let me tell you, there is one very important result. I'm not deriving it, I'm just giving you the result. We'll show its application. Molar conductivity at infinite dilution of a sparingly soluble salt. It is always equal to conductivity multiplied by 1000 divided by solubility of the sparingly soluble salt. This is one result. This is one result which you have to remember. This is one result which you have to remember. And its units are simply going to be Siemens centimeter square per mole. Whenever you will have a sparingly soluble salt, its molar conductivity at infinite dilution is always equal to kappa multiplied by 1000 divided by solubility of the sparingly soluble. I'll show you its application. We'll get to know how it exactly works. Where do we use all this? But before that, my dear students, do you remember your KSP solubility product? How do you get the solubility product? Imagine that you have got the electrolyte in this format, AXBY. Imagine How it will undergo dissociation first of all? This y is going to be y positive here. This x is going to be x negative here. Now we have got how many a's here? X. So this is x, a plus y, b minus x. Imagine its solubility is S. So its concentration of A plus Y will be X times S. This will be Y times S. Something which we have discussed in ionic equilibrium, if you remember. If I want to write the expression for KSP, I'll start with the product. It's going to be concentration of A plus Y raised by stoichiometric coefficient. Concentration of B minus X raised by stoichiometric coefficient. So KSP expression has to be equal. Concentration of A plus Y, that's X times S raised by X. This is y times s raised power y. You can write the expression like this. KSP is equal. This is x raised power x multiplied by y raised power y. This is s raised power x plus s raised power x plus y. So this is how you get the KSP expression, correct? This is how you get the KSP expression. Perfect. Now, my dear students, try to understand one simple thing. First of all, if you will be given with a sparingly soluble salt, let's say you are given with a sparingly soluble salt. You are given with its molar conductivity at infinite dilution. You are given with its conductivity as well. So easily you can calculate solubility, right? Once you get the solubility, you can easily write the expression for KSP, right? So whenever you are supposed to calculate KSP, so first of all, you have to calculate the solubility. Solubility you are going to calculate from the expression which I gave you, right? From that expression, you will calculate solubility, put it here in this expression, get the KSP of the sparingly soluble salt. For example, I'll be giving you certain questions. Let me see if you can solve those questions or not. 1-2 questions will do, and we are done with the chapter. And then we are done with the chapter. Okay. The first question which I'm writing on the screen, and I would want you guys to solve it. The question is like this. The question is the specific conductance of a saturated solution of AgCl is equal to, it is given to me as 2.28 into 10 raised power minus 6, right? Minus 6. Perfect. The question is find the KSP. Find the KSP of AgCl. Find the KSP of AgCl if lambda naught m of AgCl is equal to 138.3 Simon centimeter square per mole. Look at the question carefully and let me know if you can solve this question or not. What do you think? What do you think, guys? Quickly. What do you think? KSP we have to calculate. KSP we have to calculate. I'll just show you the procedure of solving this question. Well, my dear students, conductivity kappa value, it is given to us. Conductivity of AgCl is given to us. How much is that? I'm just writing the value 2.28 into 10 raised power minus 6, right? At the same time, molar conductivity at infinite dilution for this saturated solution of AgCl, this is 138.3 Simon centimeter square per mole. What am I supposed to calculate? KSP. I told you in order to get the KSP, we have to get the S value. How do we get the S? 2 minutes back only I gave you a relation, molar conductivity at infinite dilution of this AgCl. Can I write it as kappa multiplied by 1000 divided by solubility? Perfect. This value is given to me. This value is given to me. So from here, you can easily calculate solubility. You can easily calculate solubility of AgCl. Now, my dear students, tell me just one thing. This AgCl, how it would have undergone dissociation? Ag positive plus Cl negative. If its solubility is S, this will be S, this will be S. Correct? Can you write the KSP expression here? KSP is going to be concentration of Ag positive raised power 1, concentration of Cl negative raised power 1. So that's going to be S ka square at the end. S value, you will calculate from here and put the value of S here, and S ka square will give you the value of KSP. Done, understood? This is the approach of solving the equation. Then calculation part, I'm sure you can do on your own. Right? I'm sure you can do that. Clear, guys? One more question I'm writing. Let me see if you can solve this or not. The question is like this. Conductivity of AgBr. Conductivity is of AgBr. It's given to me as 8.5 into 10 raised per minus 7. Right? It is given to me as 8.5 into 10 raised per minus 7. Can you tell me the unit of conductivity first of all? Kappa, 1 by R into L by A. 1 by R is conductance. So Simon. This is Simon centimeter inverse, right? Perfect. So conductivity of AgBr is given. At the same time, some other parameters are also given. Molar conductivity at infinite dilution of Ag positive. That's also given to me. How much? That is 62. Similarly, molar conductivity at infinite dilution of Br negative. That's given to me as 78. And units already you know. This is Simon centimeter square per mole. And this will be Simon centimeter square per mole too. What are we supposed to calculate? We are supposed to calculate solubility and solubility product. Calculate solubility and solubility product of what? Of AgBr. Of AgBr. Can you give it a try? Can you give it a try? Can you give it a try quickly? Everyone. My dear students, it's a very simple question. First of all, you have to calculate solubility, right? You have to calculate solubility. So solubility, to calculate solubility, you can write molar conductivity at infinite dilution of AgBr, right? How much that is as per the formula? It's going to be kappa multiplied by 1000 divided by solubility, correct? This is the expression which you have to use somehow. But as per the question, lambda naught m of AgBr is not given to me. Molar conductivity at infinite dilution for AgBr, this is not given to me. But I can use Kohlrausch law. I can say molar conductivity at infinite dilution of AgBr. It is basically molar conductivity at infinite dilution of Ag positive plus molar conductivity at infinite dilution of Br negative. Perfect. I would say molar conductivity at infinite dilution for AgBr, it has to be equal. This particular value is given 62. This is 78. So how much the value comes out to be? 62 plus 78. That comes out to be 140, right? Simon centimeter square per mole. So you got the molar conductivity at infinite dilution of what? Of AgBr. So this particular term you got. Conductivity of AgBr is given. So from this particular expression, you can easily calculate solubility. You can calculate solubility, right? Perfect. Once you get the solubility of AgBr, you are done with one part of the question. The second part says calculate KSP. How do you write the KSP expression for AgBr? So first of all, if I talk about AgBr, it would have got converted into Ag positive plus Br negative. If it is solubility is S, this is also going to be S, this is also going to be S. So KSP expression is simply going to be what? It's going to be S square. S you would have calculated from here, put the value of S here and get the KSP, right? Clear? Perfect. So you can solve this question in this particular approach. Perfect. So my dear students, with this, our one more chapter is done and dusted, that is electrochemistry, right? And the next chapter, do let me know in the comment section. I want you guys to let me know in the comment section which chapter do you want the next, right? That you are going to tell me in the comment section. I hope your complete electrochemistry chapter is completely clear. Now, please and please do watch this particular session again, right? Because all the terminologies which we discussed at the end, you might get confused afterwards, right? So do this particular session again, once again at 1.5x speed, you can watch it so that all the important things, all the concepts would be in your mind all the time. Okay? And now you can solve whatever module you have, whatever study material, whatever book you are solving, right? I'm guaranteeing you, if you would have followed these 4 sessions of electrochemistry, I believe you can solve any coaching material, whatever you have, because I've not skipped a single point here. Okay? Perfect? Chalo. With this, I'll be taking leave. I'll see you guys in the next session. Do let me know in the comment section which chapter you want the next.
Unacademy. Let's crack it.